Hello. Welcome everyone to our cryptography day at Zuber. It seems that this is the whole people who came for cryptography. This is the coolest thing. I'm very, very, very excited for our today's cryptography event because I think that the topics are incredible and the speakers are incredible and the visitors are incredible. Thank you so much, everyone, for taking your time and coming, for giving some faith that it will be good event and good agenda, because I know that some people committed to come before we publish the agenda. I hope it will be interesting and exciting day for everyone. Feel free to feel quite chill, to take a chair if you want, or lie down if you want, or maybe sleep if some topic is not too exciting for you, it's fine. Feel free to feel at home. Our format is a bit loose, meaning that some speakers do like only talk, some speakers do like talk and Q&A. It's up to speakers, whatever they think or whatever you think is the most reasonable thing, go for it. Yeah, and there is a stream on Twitter. If someone wants to share with friends or someone the stream of the event, you are welcome. Or in case someone wants to jump in and co-stream for your Twitter audience, you are also welcome. Tell me on Telegram and we will set it up if someone wants. But yeah, just thank you so much for being here today. I hope you enjoy the day. And we welcome our first speaker, Nico, for the talk. Where is ZK today? This legendary human working for Bain Capital Crypto, but you probably hear him more at Zero Knowledge podcasts, co-hosting and discovering different topics and sharing with us a lot of knowledge. Welcome, Nico, and thank you so much for being here.
Thank you very much. Thanks a lot for that intro. Yeah, Nico, I work at Bain Capital Crypto and the Zero Knowledge podcast. It took a bit of creative license. I call this the state of the art of ZK in 2025 from a researcher's perspective. So I'll just start with a few confusing acronyms that we're going to use throughout the day and how I'm going to use them. So usually we use ZK to mean sort of any cryptographic proof. SNARK is most proof systems, usually elliptic curves. And STARK is proof systems that use hash functions. In academic use, ZK means zero knowledge. It's a very specific property, important for privacy. SNARK is anything that's a small proof and non-interactive, and it could be hash-based. So that includes sort of the common use STARK. And STARK means scalable and transparent, and I don't really want to get into that. I'll be using mostly those two on the right column, simply because I don't really care about the distinction between elliptic curves, hash, whatever. And I do care about distinguishing between private and not private. Cool. So the state of the art SNARK in 2025 is, it depends. Hopefully you're not surprised to see this. And so what we'll do to sort of see why it depends, we're going to go through a layered approach. First look at where SNARK's deployed, how are they deployed, so like what's the DevX for it, and then what SNARKs are deployed. I myself spend most of my time in sort of point number 3, so that's probably where I'll spend most of the time of the talk. But I did want to give you a bit of context with points 1 and 2. So where are SNARKs deployed? The company ZKV, ZK Validator, has this map of ZK that they maintain, and here we're back to like the common use of the word ZK. They list sort of a bunch of categories that you have here on the left, like payments, rollups, identity, gaming, and they list sort of all the teams that are under these categories. So this is a great way to see who deployed what. I recommend to go see the website. I won't go through everything. I do want to give you a few highlights that I think are important this year. One is the ETH proofs effort, which is get everyone who's been building a ZK VM, we'll talk about those in a second, and get them to prove Ethereum blocks. There's a bunch of applications for this, one being to do like Ethereum Lite clients. If you want to sync to the Ethereum network, you could just verify a proof rather than downloading the whole chain. We'll get back to this table in a minute. This table comes from sort of the document they use throughout the calls. The other application is what Google has been doing with our Google Wallet. And specifically, they released a spec called libzk. And the idea is to allow Google Wallet users to reveal that they're, say, over 18 without revealing their whole ID. And so this is what we call selective disclosure. I think there's actually a panel about this very, like this specific application, so I won't say much more yet. How are snarks deployed? Most of the time, okay, this is a fake graph, but most of the time we deploy like snarks for NP relations. So like you've heard snarks for circuits, for example. That's not the only thing we could do. We could be doing snarks for custom relations, like skip the whole circuit thing, do just, if I'm doing a proof of matrix multiplication, I'll make a snark for that specifically. We don't do this really, other than, I guess a signature can sort of be seen as that. Why would it be interesting to explore? There's a small overhead that comes with going for general purpose snarks. There's also a big security distinction. Snarks for all NP relations, there are sort of results telling us they don't really exist in the standard model without falsifiable assumptions. So if you're really, really keen on like super tight security, you might want to check the other category. So now that we're snarks for NP relations, we choose to do our snark for a circuit. What circuit do we want? You've probably seen debates between like ZKVM or custom circuit. And so ZKVM is constraints that implement a CPU, and we'll see which one in a second. Custom circuit is constraints that implement specifically the business logic that you care about. I've drawn this on a line as sort of a spectrum because there are in-between points, right? So you could have a ZKVM with what we call pre-compals, and these are specific circuits that are specific to your task, right? So now you're doing the CPU thing plus custom logic. You could also have, on the other end, a custom circuit, but that's not just like a sequential circuit and ends. It could be a state machine. It might not be a full CPU, but it's sort of in between. And so for the two applications we saw, ETH proofs is very much in this right end of the spectrum. Right, left, to your left, I guess, yeah. And libzk is actually very much custom circuit. So even within the state of the art, we still see a split here. If we go to the ZKVM, what CPU are we implementing? And this is where I bring back the ETH proofs table. And that second column, you see like which CPU people have implemented. They also have colors. So you have, in blue is all the RISC-V. This is an approach pioneered by RISC-0, who are also here today. And a lot of people have followed. The other approach is to use, for example, WebAssembly. That's some of the orangey ones. Or the purple one is to have like a custom CPU. You design something that's easy to prove in a VM, but it might not be easy to compile to from some high-level language. Yeah, I think that's where I'll leave it for today. I also wanted to point out that fourth column. Everyone is sort of being pushed to open source everything under a dual license, and that's great to see. If you are to write custom circuits, how do you do it? The approach, I think until maybe last year, has been to use Circom. And this is just like searching through GitHub's number of repos in a specific language. So you can see total number of repos, Circom has the most. But then if we filter on like January 2025, you see suddenly that Noir, this new language, takes the lead. There are many, many more DSLs. This is not a full picture at all. They're harder to search for on GitHub, and so I was just a bit lazy. There is someone who has a project trying to like get all these sorts of numbers. His name is Arman, and there's a link here to his repo. I really recommend checking it out, helping him out, because there's a lot of filtering to do. And I think he's also looking for internships, so if you like his work, get in touch with him. The next question is sort of, okay, we've written a way to write a proof. Who is going to run the proof? You could do this client-side on a phone, on a laptop, in a browser. You could do this through private delegation, and this is interesting if you're doing a ZK proof. There's a bunch of ways of doing it, and I won't get into those specifically. You could delegate to a single server, and that's how most Ethereum rollups operate today. Or you could delegate to a prover market, and I think we're starting to see those go live. This comes with a trade-off. If you're doing a ZK proof, so one that does have privacy, you have sort of a privacy to like proving speed trade-off. So we could first draw out like fully private, but kind of the slowest proving you can get is going on a client-side device. Or you could go sort of the fastest thing you can get. You get a competitive market of provers, but everything is public because you've sent your data to that whole market. You can also reach these in-between areas. You could do privacy-preserving delegation. So there, I'm not putting it as fully private because there are assumptions that come with this kind of delegation, either MPC or trusted hardware. And I'm not putting it as the fastest thing because you're also delegating to some kind of restricted prover. The other one would be to delegate to a single server. Yeah, there's a word missing there. Anyway, this could be not private at all if you don't trust that server, or it could be private if you do trust the server. And this is sort of what the angle Maiden are going for right now, is to call like these edge blockchains. And you can say like, well, my friends and I trust each other, so we can settle with sort of just one strong server and settle to the whole chain privately. So this is why it's not just fully public either, the single server mode. And yeah, I didn't really pay attention to draw this in a straight line. I don't know how the trade-offs work. Maybe we're like concave, convex, who knows? That'll be interesting to see. Cool. This is the part that I like the most, is what snarks are deployed and sort of why are we choosing specific snarks? What kind of design decisions are we making? And to evaluate these, we need criteria. So the criteria will be prover resources. This is sort of bandwidth, memory, computation, just in general, the energy you spend as a prover. Verifier resources, similar thing. Proof size, and security model. And in security model, include things like what kind of assumptions we need to make, or do we have a trusted setup or not? Yeah, that's kind of it. Cool. So it turns out we have a very large design space, like a seriously huge design space. The first thing you can ask is, what kind of cryptography assumptions am I going to make? Am I going to use hash functions, elliptic curves, or lattices? Next thing you can think about is, am I going to use what we call a monolithic snark or a piecemeal snark? And here I'm borrowing vocabulary from Dan Bonnet. We'll see in a second what I mean by both. But this usually maps to what you might know as recursion or folding. The next question is, do you want to use a univariate polynomial IOP or a multilinear polynomial IOP? And if this doesn't make too much sense to you, don't worry. We're now like in the deep end already. Next question is, what kind of arithmetization do you want to use? Are you going to use snark-friendly hash functions or standard hash functions? Are you going to have the zero knowledge property, or are you just going to call it a ZK proof anyway? What kind of field are you going to use? This is kind of the mathematical object that's underlying all our snarks. Are you going to use linear time codes? And this is specific to like the hash functions family of things. And another specific one to hash functions is, are you going to use proven or conjectured security? There are many, many more. These, I think, are the ones that have been front of people's minds for the past year and a half. And this is why I want to sort of evaluate them today together. So we can start with some quick ones, which is, if you're going to do a snark-friendly hash function over a standard hash function, you might have a faster prover, because you'll be proving things that are easier to like snarkify. But you might lose security, simply because we don't know much about these snark-friendly hash functions. Standard hash functions have been a lot more battle-tested. The next one we can do quickly is proven or conjectured security. So this is specific to hash-based snarks. The proofs we have for how secure these things are take us to like some number of bits of security. You could also conjecture that these proofs work in different parameter regimes and get to, I don't know, double the security. So in this case, you would get better prover, better proof size, better verifier, everything better, but you lose on security because there's no concrete mathematical proof that this thing is true. There's no like counterexample so far, so it's not like completely crazy to do this. The last one I'll do very quickly is linear time codes, because again, it's very specific to hash functions. these things are asymptotically faster than read-Solomon codes, which we like to use everywhere. For concrete instance sizes, like small instances, they're not that much faster. And so this is why I have prover a question mark. Like maybe we gain something, maybe not. Like, do we care about big instances? Maybe not. You do lose on proof size and the verifier simply because these codes have slightly worse parameters than read-Solomon codes. That's it for the quick evaluations. How much time do I have left? No one knows. 10 minutes, perfect. Well, now we can get into like the remaining 6 and dig a bit deeper. So the first one that's been a big debate on Twitter as well is like, are you going to use hash functions, elliptic curves, or lattices? So we're going to sort of review each of them with our criteria. So hash functions allow for a very fast prover because they're very cheap to do, and our processors are actually built with like instructions to compute standard hash functions. Similarly for the verifier, it might not be asymptotically the fastest verifier, but because the operations are so cheap, you can do this very quickly. Note that this is for like hardware. If we map this to sort of on-chain execution, the verifier resources here is a bit expensive. The proof size is great in terms of like objectively, but comparatively, they're okay. They're not the best we can do. The security model is great. If you use a hash function that you consider to be resistant to quantum attacks, then you have proven security in the quantum random oracle model. Note that I'm saying this on purpose because this is not security in the standard model, and this will come to bite us in a second. With elliptic curves, we have sort of an okay-ish prover because the operations are quite expensive. We have fast verifier because the proofs are tiny and asymptotically is amazing, but still expensive operations. On-chain, this is incredibly cheap because we have precompiles. The proof sizes are tiny. This is amazing. This is also why we've loved these and loved putting these on-chain. But these are broken by quantum computers. Right? So this is pre-quantum. And again, the security relies on some kind of mix of either weird knowledge assumptions or weird models, or the discrete log and the random oracle model. Yeah, but in general, like, if you're looking to make something that will still exist in 100 years, you might not want to go with elliptic curves. The last contender in our three-way battle is lattices, and this is sort of kind of the newer cryptography. You get fast prover, like a fast prover, faster than elliptic curves, not as optimized as something like hash functions. Verifier resources, I have this as to be determined because this field is evolving super quickly, and over the past 6 months, we've seen our state-of-the-art be like a linear time verifier, and now it's reduced to something like, I think, a log-log verifier. So similar to what we'd have in hash functions category. The proof sizes are small. This is also evolving a lot, but we now have proving schemes that yield smaller proofs than hash functions equivalent. Security is post-quantum secure, as far as we know. If you compile your thing in the quantum random oracle model, it's slightly different to the hash functions. So hash functions just say we have the quantum random oracle model, and that's it. In lattice, we're saying quantum random oracle model plus some lattice assumption. So this could also be broken in the future. I can't really give you a breakdown of like a very quick like plus minus for our prover, verifier, etc., because this is still complex and still evolving. What we do have is sort of known knowns and known unknowns. So what we don't know is when will we have quantum computers? So if you ask me, you know, when should I transition away from elliptic curves? I can't tell you. I have no idea. What we do know is that a quantum computer would only break the soundness property of an elliptic curve snark. It wouldn't break zero knowledge, and this is true for like all our snarks. So in other words, whereas with encryption you have this like harvest now, decrypt later attack, you wouldn't have this with zero knowledge proofs. So you're safe to put proofs of private stuff. Your privacy will never be compromised by a quantum computer. However, as soon as there is a quantum computer, they'll be able to make fake proofs. What else do we know? Well, we know that most blockchains still rely on elliptic curve signatures. So great if your proof system is quantum secure, but if the rest of your chain breaks down, what's the point? And even like government IDs rely on like non-quantum secure stuff. So that's all we know. I won't emit judgment. I'll just give you those facts and you get to do with that what you will. The next category I have is monolithic versus piecemeal snarks. And what do I mean by this? A monolithic snark is the one we know. We take a statement, we prove it, we get a proof. Piecemeal snark is we take a statement, we break it up into small statements, we prove each of them, and then we aggregate all these proofs. This aggregation can be achieved either using recursion, so a proof of a proof, or what we call these accumulation and folding schemes. So these things are rarely shown as being the same thing, but conceptually they allow the same thing, right? A piecemeal snark. You could aggregate sequentially, so take your substatements in order and do this in streaming fashion, and this is what we call IVC, or do it in a tree, and this is what we call PCD. Doesn't matter what we call them, the idea is just break into small statements, only prove the small statements. Quick comparison, the piecemeal snark allows you to treat substatements independently, and so you can either do this in parallel with a big GPU cluster, or you can do this in a streaming fashion if you have very resource constrained, you're proving on a phone. Each substatement obviously requires fewer resources than the big statement, and this is why I was saying well, do we care about linear time codes? Do we care that much about having great asymptotic performance? Well, maybe not, because we're breaking our statements down anyway. The downside is security. The security analysis of a monolithic snark is not super simple, but relatively simple. The analysis of a piecemeal snark is very tricky. Because you're taking these things that are proven in the random Rockwell model, making them non-interactive and physical in the real standard model, and now you're using this as a component. And so actually we don't have a security proof for the whole piecemeal snark if you're using it in this way. We have a sort of heuristic proof. We say all right, imagine we did have a snark in the standard model, you could do this. We have something that comes close to it. It's using hash functions, but we don't know. Is this a problem? Uncertain yet. But this is the kind of thing where I'd like research to get into, especially because we recently saw an attack on Fiat-Shamir breaking down for specific protocols. So, better prover, verifier time and proof size stayed the same, but maybe slightly worse security. Okay, 5 minutes, we are gonna speed up. Univariate or multivariate IOPs. So we love multilinear polynomials, specifically because of this equation, which you might have seen if you tried to read through a paper or an explainer like Spartan or SumCheck. What does it mean? I feel like we often don't grasp the real meaning of this equation. It's we're saying we can evaluate f at any point in the field by taking a sum over the evaluations of f. So if you're familiar with snarks, we have to do FFTs. FFTs are expensive. Why do we do FFTs? It's because we go from evaluations to coefficients, and again from coefficients to evaluations. Here this equation tells you can go from evaluations to another evaluation. And that's the key unlock for multilinear polynomials. The other nice thing is that this right-hand side here is a statement that is very easy to prove. We have a protocol called the SumCheck protocol for this. So it's great for the prover. The downside used to be that commitment costs were high. And recently, there's been a lot of work in this area, and the commitment costs are now pretty much the same as for univariate polynomials, especially in hash-based land. It's exactly the same. So better prover, approximately same proof. This is why people have gone for this a lot. Choice of field. You could choose a big prime field. You could choose a small prime field with its extensions. You can choose binary fields. These are fields that have characteristic 2. Or you can choose a tower of binary fields, just like a field within a field within a field that keeps getting smaller, like Russian dolls. I'll skip over this very quickly. The main thing is that large fields are inherent to elliptic curves. You can't really do elliptic curve cryptography without a large field. However, they are good for signature verifications. ECDSA signatures use large fields anyway, so you might want to use that. Small primes are great because they're quick in hardware. Binary fields are great because they express bitwise operations very easily. So in general, by being flexible about your field, you get a better prover. Arithmetization costs. I won't read through the whole thing. The idea is just look at the diagram. We have what we'd call the circuits with inputs at the bottom, outputs at the top. Some of the inputs at the bottom are private, they're marked in red. And all the intermediate wires are sort of intermediate and marked in orange. Some proof systems allow you to only commit to the bottom input, private inputs, and others force you to commit to everything here that's not in black. So where we kind of like to commit to fewer things. However, we have to be a bit careful because the protocols that allow this, like GKR, have been shown to break down under Fiat Shamir. So these circuits might contain a backdoor. So if you're going to go GKR, you're going to have to be very careful about what kind of circuit you're verifying a proof for. So better prover, questionable security. Cool. Zero knowledge. ZK is absent from most libraries, but it's present in all marketing. If you want privacy, you need zero knowledge. There is no privacy without the zero knowledge property. And we have a ZK hack puzzle about this, where we give you proofs that are not ZK, and we ask you to extract information. How to take something that's not ZK and make it ZK? Well, you can either rewrite the proof system, or you could wrap your proof in a proof that is ZK. And again, this is sort of the recursion, piecemeal kind of thinking. So you lose a bit of prover time, but without it, you have no privacy. So here we are. We've finished our little square. There's a lot of these you'll see have sort of positives everywhere except for security. And so these are the ones that we tend to go for, and we'll see later what happens. I just wanted to go back to the two applications I mentioned at the beginning, libzk and ETH proofs. These are the choices made in libzk. So it's a hash-based proof system. They use a monolithic snark because they want to be careful about security. They use multilinear and GKR, so those things go together, to commit to as little things as possible. They use standard hash functions, again, for the security, and we can skip straight to proven security as well. They really wanted the yes security. Zero knowledge, yes. The very interesting thing bottom left is they use two fields actually in their proof system, and they prove sort of two circuits in parallel. They use a big prime for signatures and binary fields. And they don't use linear time codes because their problem is quite small. For ETH proofs, I chose to look at SP1 hypercube. In blue is sort of the things that changed. So they kept multilinear, they kept RS codes. They did go to a piecemeal snark because of this parallelization that we talked about. They use snark-friendly hash functions, again, because you're doing this recursive proving. There is no zero knowledge. And they commit to the extended witness because, actually, I'm not entirely sure why. It would be interesting to chat with them. Small fields and conjecture security. So state of the art in 2026, where are we going? Here's a very quick wish list. Exploration of lattice-based snarks, and check on all these security questions that I asked. So security of piecemeal snarks, security of snark-friendly hash functions, scrutiny on error-correcting codes and the conjectures that come with them. And please, please, please add zero knowledge to your libraries. And that's it. Thank you very much. Do we have time for a few questions? No. Well, thank you.
Thank you so much, Nico. I think this is, if you ask me, this is the level of technicality that I think should be at all conferences. Our next talk, we welcome Cody, who currently works for EF, but used to work for Aztec before. And in Aztec, if you ask anyone, anyone loves Cody. And he goes, wow, Cody, he's so cool. So I hope that you will love Cody as much as all people in Aztec loved him.
Thank you. And I go on straight away. Okay, yeah, so I'll aim to speak for 20 minutes and then leave 5 minutes for questions. So yeah, I'm with the Ethereum Foundation, and we're thinking about how to assess the security of these ZK VMs. You saw the big table in Nico's talk. There are at least 24 of them out there, so it's a big project, and mostly I will be focusing on questions for the RISC-V based ZK VMs, which last I counted, there's about 15 of the 25, say. So yeah, I want to describe some basic challenges of fuzzing. Just tell the audience a little bit about fuzzing in case you don't know. Look at the snark pipeline and where you might fuzz it, and where we have other assurances about, or not assurances, but other techniques for security, and then show some kind of preliminary results and observations about about security of these things, maybe even prior to fuzzing, and then end maybe on some other kind of future directions it might take. So just to get right out of the way, what is fuzzing? Well, it's the art of throwing random inputs at a program to try to break it, right? But if you don't do this well, you won't find very interesting bugs. So maybe the most important consideration is the quality of those inputs, right? How do you produce interesting inputs, and what does that mean? Well, it's about whether the inputs go deep into the program, right? So you can maybe produce a lot of random inputs, but they might get rejected by the code right away, or they might not visit some sort of unlikely path in the code. And that's a problem because, well, if you're a hacker, you're looking for these kind of nooks and crannies, right? So you have to somehow use techniques that do the same. And it's also a maybe secondary point, but we want to have high throughput for novel inputs, right? If you don't fuzz well, you might be throwing a lot of code that isn't likely to create a bug, or to lead to discovering a bug. And another point would be the speed of input generation, right? Fuzzing is about volume as much as it's about quality of input, so you want to have fast fuzzing pipelines. So what is fuzzing not? It's not a formal technique. And I raise this because we have a major initiative going on. We're investing heavily in formal verification at the EF over a 3-year time period. And I recommend following the project. There's a lot of very interesting stuff going on, very nerd stuff. You can look here. But fuzzing, I see it as necessary and complementary to this, not sort of just a pre-step that will be overtaken by the formal stuff when it's ready. Because even formal verification is not foolproof, right? I mean, your formal verification system is only as good as the specification. I mean, the idea in FV is that you write a formal specification, and you try really, really, really hard to be correct there, and then you use that as a baseline for measuring the correctness of your code, like to show that it conforms to a spec. And you use software techniques to reduce the compliance of your code with this formal description of what it should do, to other statements, which are also just you hope are correct. That's a common technique, is to reduce it to a small list of sort of axioms that have been checked by hand. So we need something that is, even if we had this for everything, we would still want other techniques. And also formal verification has it gives you a high bar. Like if it's working, it's very powerful, and but it has very high startup costs. Maybe there's a lot of custom code. Maybe it'll take a long time for us to even have the toolkit that can be used for formal verification. So we need something else. And we want tools that are easier for the projects to implement, especially as the EF. We're trying to make tooling that's broadly applicable. And we want to find bugs now, or at least sooner than when the formal verification's ready, so that there's time for the projects to fix those bugs, and so that the formal verification can find the sort of harder, deeper stuff. So that's our goals. Here's what the generic ZK VM pipeline looks like. And I'm sort of abstracting away. Implementations may fuse some of these components for performance, but at least from a security perspective, this is how I think about it. So we start with some code in the upper left there. You can think of that as being Rust code. It's going to be, in the examples that we care about most right now at the EF, it's going to be code that describes the execution of the Ethereum virtual machine, something taking like revum from Reth, right? So you have that code. And what you'll do is you'll compile that using a traditional compiler tool chain, like the Rust compiler, which will use LLVM, to some kind of target language. So you produce a binary, and there's no cryptography yet. This is just a program you can run somewhere. And then when we want to run it, we're going to run it in a virtual kind of environment. And these are provided by the ZK VMs, right? So that will, so the binary may represent, it's like a version of the Ethereum virtual machine. And the inputs in this case that you'll plug into your program and then attest to its execution will be like an Ethereum block, a big list of Ethereum transactions, right? We want to prove that those were executed according to the rules of the Ethereum execution spec. Okay, so you put these things together using code which is not really shared. The projects have their own code for doing this, and it can be quite complex. And you produce an execution trace, which is like, okay, this is all of the steps in the computation for the given set of inputs. And from there, you want to produce, you want to now attest to the execution in a cryptographic sense. You don't just want a big list of what happens, but you need to record some kind of intermediate and auxiliary information to actually prove that the computation was done. And this will result in, so that's this step here from trace to polynomials. That's what I'm calling the witness generation step. And inside of that is the correctness of those circuits, right? If your cryptographic description of what the computation did is wrong, you can prove statements that are not what you intended. And that's a very, very serious problem. So that's where I'll focus in this talk, mostly. We'll return to these later steps at the end. Yeah, I focus mostly on the first piece so far in my investigations of the existing tooling, because I think there's a bit less attention put into some of that, especially on the executor side, that binary to trace step. People are maybe just been more interested or more concerned about the circuit security, so I thought, okay, it's good to do something complementary there. But yeah, we'll return to these pieces toward the end of the talk. So yeah, and I'll also focus on risk 5 just for concreteness. But as we saw in Nico's the big table that Justin and the ETH proofs people produced, there are some alternatives and they have some trade-offs. I meant to say, by the way, that this code to binary step, that is a security concern. And one of the benefits of using risk 5 is that we're using very, very common tooling. So bugs will be discovered by other people searching for bugs. On the other hand, LLVM is incredibly complicated, is known to have a lot of bugs in it. So there's kind of a trade-off space there. But if we're using a very custom target, like if the binary is taken from Valida ISA or whatever Petra is using, I mean, those are very powerful systems. Maybe those will eventually become what we want for ZK. But at the moment, the compiler itself is then a problem. It's something that we have to look at very carefully. But let's focus on risk 5 for most of the rest of the talk. So let's just say risk 5 is a family of ISAs. ISA stands for instruction, why can't I think of it? Sorry? Instruction set architecture. And you specify some parameters to say what exactly your ISA is. So you have to say the size of a register. You have 32 or 64-bit registers, and then you have a list of numbers describing available structures. So one that is very common, say that like some of the most advanced or farthest along mature projects like RISC-0 and SP and Succinct uses this RV32IM. It's very minimal target. So I is just the base instruction set. It doesn't even have multiplication, but they put multiplication in, and that's the M part. So I is just the base set. You want multiplication, so you add the M. And this is often called like an embedded target. It's something that can run in a very kind of low power device. And maybe it's good for security because it, there's not as much to attend to in terms of all of the operations that can be done. But on the other hand, there's a part of the trade-off space I want to call out, which is that it's not that easy to compile some of these other languages which are used in our clients to this target. So these like Go and Geth and the clients that use Java and I think maybe also C#, they want a more complete target, which would be this GC target. And that has a lot of other stuff in it. You would have to implement floating points. You would have to implement compressed instructions and atomics, and maybe one other thing I'm forgetting. So it's like, okay, that's sort of bad for security. You have more surface area. But on the other hand, an aspect of security is client diversity, right? So we want to make sure that we can compile all of the existing, I mean, it's a real strength of Ethereum right now that we have so many different clients, and it saved us from bugs in the past. So yeah, there's an interesting part of the trade-off space there. Right, so I've just begun looking at how do you fuzz the execution part, just taking the RISC-V opcodes and plugging stuff in, and how do we know that that's done correctly and that the projects haven't accidentally made a mistake describing how RISC-V is supposed to execute. So the naive thing you would do is what we call differential fuzzing. So you want to generate a random RISC-V program. And this is where we're a little meta, so let me just call this out for the audience. We have our program, which is like the compiled version of the EVM. And now we're trying to test, that's in RISC-V. And that's going to be an example of the sort of thing that we want to make sure is executed correctly. So the program that we're testing now is the executor. And I switch between calling it that and executor, depending on how fancy I feel. But that is going to be something inside of one of these ZK VM libraries, and we want to test that by throwing other random programs at it, right? So these are what we want to generate, is random RISC-V programs. And what you'll do is you'll execute on a trusted reference and then compare. So you'll kind of execute on something that you believe is correct, record some kind of state along the way, and then do the same on your the device you're testing, the program you're testing, and then you'll make sure that all the checkpoints were the same. And we do have a very high quality reference model in the case of RISC-V, okay, which is a SAIL. So there's a formal language for describing these kinds of systems, SAIL. And it's widely in use in the RISC-V community, and there's even a way to compile it to produce a C program that will execute. And this is sort of the highest bar for security, of a formal description of the system, which has been scrutinized by a lot of academics. So that's a big plus for RISC-V. Yeah, so you'll just kind of do this in a loop. You compare, and if you find a difference, you believe that SAIL is correct, and then you look at the random program that led to the difference and search for a bug. But before we fuzz, we ought to test. I mean, fuzzing is just a very automated, high-power way of testing. And what I found was that, and I also wanted to look at testing because I thought, okay, there's some canonical way of testing these RISC-V things. That's one of the strengths of RISC-V, is it's this big ecosystem. So I looked to see what was available and what the projects implement. When I say the projects generically, I'm meaning like the ZK VMs. And so there's this unit test suite, which is implemented. And there's a fun little anecdote here, is that actually even the base instruction set, if you just do RV32I, that has changed in 2021. So even what was in there has changed. And this standard test suite was written before that change. So actually this test suite will not execute without some additional work for these projects that implement RV32IM according to the current standard. So I found this issue and I asked them if they, how much work is it to fix this? Maybe this is something I can do at the EF. And they were like, we don't really want to fix that, which is kind of funny. So it maybe shows that they have certain uses in mind, and that we won't get the full benefits of this ecosystem, but it's okay. It's not. I think it was a good faith answer, and it was not so hard to make it work, but worth calling out. But there's this higher bar test suite called the architecture tests, where I found that few projects actually implement this. It has a standard, it defines maybe a standard API for doing this checkpointing mechanism, so that's why it's interesting to me if we want to differentially fuzz that way. And I implemented it for some projects, and mostly the results are very good. Like, for instance, there are over 500 edge case tests of the addition opcode in this, so it's very thorough. But there are some points of non-compliance. And actually, to use the RISC-V trademark, you have to pass this test suite. So at the moment, a lot of the projects couldn't do that. But there's missing instructions that are not really relevant, and so you can just kind of implement them as no ops, and you'll have compliance there. I did find one circuit bug along the way, though, implementing these, which I'll say more about maybe in a blog post in the future. Yeah, so then how do we actually produce these test binaries? Right? We need to make random programs, and that to me sounds complicated. Programs are these structured things, there's a large space of them. How do you actually do this? Well, people have thought about this. So there are some standard tools. There's one called CSmith, which will just output random C programs. And you could then compile those using, if you like, Clang, or you could use GCC. You could produce random programs this way. But I don't know, maybe that compilation step could be a bottleneck in our pipeline. So it's worth considering alternatives. There's a framework called RISC-V-DV for doing this, which seems to be very much in use in the hardware community, but it actually assumes a lot about your implementation. So it assumes that your system is not some cryptographic system like we have, where you've implemented the proof system to describe RISC-V, but that you have a system Verilog description of hardware. This is a language that's used for describing hardware in code. And it assumes that you have that and that you want to simulate that, right? And there's some nice, there are some nice tooling for producing random instructions, but you need to have some stuff to plug in, and it's typically stuff you have in hardware. And so I thought, okay, well, maybe I can rig something up, but there's an issue on the RISC-V, the RISC-DV, RISC-D5 maybe, repo that says that it's not, so almost all of the tools that you would use to simulate executing on your system Verilog code, those tools are called RTL simulators. Almost all of those are actually not freely available. So there's one that is, which is called Verilator, but it's not actually compatible with RISC-DV yet, because it's sort of somewhere deep down, Verilator doesn't use a library that they use, and others have called this out. I didn't make this issue. And it's something that they're working on. Sorry. It's something that they're working on, but even in October, they said, yeah, we're working on this, but it's going to be a while. So that is not quite available to us yet either. So we have a tool called, a paper called Cascade, which I'll put a reference at the end. That's, I think, a very nicely written paper with some interesting ideas in it I can recommend reading. And it's from last year, and this is another, it's describing how to fuzz RISC-V emulators or executors, whatever you call them. And it also solves this throughput issue. So they claim that if you're using traditional fuzzing, and we should take this claim with a grain of salt, but if you're using some traditional fuzzing tools, you'll end up pushing a lot of boilerplate code through your simulator that you're trying to test. Like there's going to be some setup code and some teardown code, and then in the middle you'll have your random instructions. And they claim that like at least 90% of the code that the device you're testing will be just this boilerplate. So you have actually very low throughput for novel inputs. And they claim to solve this in a cool way, which I'm like very tempted to outline, but maybe with 3 minutes, maybe I don't. So yeah, so what about input generation? I mean, I've just described producing the inputs to our programs we're testing. And, but we want to say, you know, how can we make sure that the inputs penetrate deeply into the RISC-V emulators? So what I've described is robust, but kind of course, you just generate some programs. You don't actually know what's happening inside of the code when it runs those random programs. So, you know, the thing that's done in industry, and there's some very high-powered tools available freely, is an introspective approach where you watch your code as it's executing these random inputs. So you can take coverage and say, like, okay, this line is executed by this example, and it's maybe this example is the first one ever to execute this line, so maybe we should start from this example and try to perturb. And they use some cool like genetic algorithms, probably a lot of approaches to actually sort of drive the random input generation toward interesting lines and have a lot of like coverage, you know, so make sure you're not always just executing the same piece of your code. But that's a harder thing to do because, well, how do you actually drive, like I need some kind of continuity property, right? Like I need to know that when I'm generating random programs that I'm not just randomly hopping all over. If I have an interesting input, I need to sort of produce a nearby interesting input to sort of stay in the region of that interesting input, right? So, so to do that, I don't actually know of any tools that exist right now. We need to sort of produce random RISC-V templates and then have the kind of standard fuzzing library change pieces of the template and then sort of add templates to the corpus and fuzz in the vicinity of those. But I think we'll be able to use some existing tools like HongFuzz does coverage-guided fuzzing for Rust. One caveat is that if your code is using a foreign function interface, like maybe you're calling out to C or you're calling out to CUDA, then I think these things break down. Maybe people have solved this, but no one I've talked to is optimistic about having coverage across those boundaries. So yeah, so here we are again on the pipeline. We've talked about everything up to this, a little step here, up to this polynomials piece, yeah? And so let me just blast through in the last, maybe I'll go over a minute or two, some of the other considerations that I haven't looked at very closely yet. So, I mean, maybe the biggest one is circuit correctness, right? If your circuits are incorrect, you can prove something is true, and it doesn't actually pertain to what you want to prove is true. And this could be totally disastrous. But there are a lot of sophisticated tools in development that the security firms have. I'm optimistic those will get us really far, and probably will build some stuff that's more freely available as well. I want to say though that a lot of people will tell you like almost all of the bugs are soundness bugs, and those are the worst. But actually, Ethereum cares a lot about completeness bugs, right? If you can't prove a true statement, that's a big problem for us. You have to be able to prove that you can withdraw your money from the pool. You don't want to sit around and wait for people to fix the proving system so that you can do that. So it's quite important to have totally correct circuits. Yep. And also I'll add that you can find sources of soundness bugs using fuzzing, and this paper describes some pretty interesting results in that direction, which I'll also put that as a reference at the end. And then there's prover correctness. You know, here there is maybe a smaller diversity of libraries at the moment, so that's kind of a benefit. We can just take the programs that I described generating before and then prove and verify them. That'll be a slow pipeline, but we'll definitely do that. And you maybe also can focus on the components of those. Like you could just fuzz the PCS, the polynomial commitment scheme in Plonky 3, for instance, and get a lot of mileage out of that. Similarly for SumCheck, these libraries are often quite modular. And verify correctness. To me, it seems easier to fuzz because the space of inputs is just a big concatenation of field elements, roughly speaking. And I think that the semantics of that is a bit simpler. Like there's a handful of interesting inputs in your field. You have 0, 1, modulus minus 1, modulus over 2, modulus over 2 minus 1 plus 1, these kinds of things. So maybe it's easier to take off the shelf tools and kind of seed them with an interesting corpus. Probably you just take some correct proofs and then expect them to break whenever you fuzz them. And if something doesn't break, then you have a problem. So they shouldn't verify once you perturb them. And also verification will be very fast because the verifiers are very fast. And the code is going to be less optimized. So maybe it's simpler, maybe it's all in one language and coverage guidance works better. So thank you all for your attention. Here are a couple of references that I mentioned during the talk. And we have a few minutes for questions still, right? Yeah. 5 minutes. Yeah, 5 minutes. Matan, yeah.
If you found an input that goes deep, gradient descent.
Yeah, I can repeat the question. So the question was, is it useful to use neural nets for fuzzing? Did you have more?
No.
Yeah.
That's it.
You know, if you Google about this, you will, or DuckDuckGo about it, you will, you'll find that the fuzzers are being used to produce harnesses, which is cool. So, but I can't find, and I haven't looked super deeply, but I think maybe the LLMs are just too slow to be used in this kind of pipeline.
No, not LLMs, just neural nets.
Neural nets.
I mean, you do a gradient descent, it sounds.
Yeah, I see. It's interesting. Yeah, we should talk more about it. I don't know. Yeah.
So could you please go back to slide 10? Yeah, you went very quickly on honk fuzz and FFI, so I just wanted to know a bit better how it works, because this seems to be where you can really speed up the process by basically generating smaller inputs for your fuzzing. So how does honk fuzz work exactly? Do you have to do it manually to sort of, do you have to like monitor the code manually and then from there look at the example that triggered a specific line, or can you actually automate this process? And I guess you could perhaps also use neural networks for this, but
sure. Yeah. I mean, honk fuzz is generic tooling that sort of automates the process, but you have to do some manual setup. You have to provide an interesting initial corpus. You know, you have to investigate bugs, and I mean, you kind of, you know, you'll want to check in and steer the process and make sure that it's not just finding nothing. You know, make sure the coverage is expanding. But yeah.
Okay, so it's semi-auto.
Yeah.
So in your work, do you expect to spend most of your time there or somewhere else?
Well, for me at the EF, it's kind of like I want to accelerate what's not being done. So, yeah, perhaps if the projects don't focus on fuzzing the emulators, I'll spend a lot of time there. But if setting up this kind of stuff, if maybe grantees will do it, I'm not sure really. Yeah.
Thanks.
Hi, do you do any like guided fuzzing for ZK VMs? based on things, you know, from ZKVMs that are different from usual fuzzing. Like ZKVMs are known for having like odd memory and having, some of them had bugs like alignment and memory accesses or different things, like they're based on prime fields, which is different from CPUs. So do you do any of that kind of like domain specific knowledge from ZKVMs for fuzzing?
So far, no. I think with but just focusing on the executor, maybe you don't expect to use that knowledge so much. But maybe with the circuits, yeah, I think that'll be very much ZK domain focused, right? And maybe in the verifier as well, like, you know, if you're fuzzing the Plonky 3 verifier, yeah, thank you. And you know that maybe the field has a certain structure, or certain field elements are in use in the protocol, then maybe you add those to your corpus, for instance.
Yeah, I think maybe in not the RISC-V executor itself, but like in TraceGen, which kind of like translates all of this information to the actual circuits. Things might get odd when you do like byte decomposition of the prime field and this kind of things.
Yeah.
And you may have some edge cases, so I was just wondering if that applies here as well in this context.
Yeah, I would think so, but I haven't dug in.
Thank you.
Yeah. Is that all? Yeah, okay. Yeah, thanks very much.
Thank you so much, Cody. I think it was a very, very exciting one. Now we are transitioning to the panel about ZKID. I think it was very, very interesting moment when Google announced their ZKID and the ZK community split into two parts. Some people thinking that this is the coolest thing ever because it means that the world has adopted ZK. Other people thought that it was like the worst thing ever because it means that Google took our ZK from us and we are done. So today we are having three amazing speakers, a panel moderated by Yin Ton from EF. Oh. Welcome. And to our participants, Theo Madzu from ZK Passport and Obsidian, and Alexander Kurbatov from Distributed Lab and Rarima Protocol.
Thank you, Lisa. And thank you, Theo and Alex, for joining. So yeah, as you mentioned, Google recently announced the integration of zero-knowledge proofs into Google Wallet, and this is deployment adoption at scale, far beyond anything I think the ZK industry has seen. But at the same time, Theo and Alex here, they have been working on ZK ID solutions for long before this announcement. They have deployed already in multiple real-world contexts. And so today I want to understand some of you guys' learnings and experiences from real-world deployments, and I want to get your take on this Google deployment, what it means for us, and then also some thoughts on open problems and future directions. So let's start with introducing your projects. I want to understand your projects in the real-world context, so I want to understand which locations you've seen the most adoption for your projects, for which use cases. And I also want to understand how you're learning about the requirements that are specific to these contexts, like the security, privacy, efficiency requirements. How do you gather these requirements? How do you integrate them into your deployments?
Hi. Hello, everyone. I'm Theo, so from ZK Passport. So just a rough explanation of what ZK Passport and Rarimo do is that we use Passport and national IDs. So they have a chip in them. We read the data through NFC and we generate zero-knowledge proof from that, all on the client side, so it remains fully private. And you have the guarantee from the cryptographic proof that it is a valid ID by verifying those signatures from the state, because this data is signed by the issuing country. And you get from the zero-knowledge property the privacy that you need by keeping the rest of the data fully private, and you only reveal what you want, such as, for example, being over a certain age or being from a given country. Now, when it comes to where, for ZK Passport itself, we were particularly deployed in which country, for us is something that we mostly got integrated in like Web3 context. So like, for example, DevConnect or DevCon, we've done, like, for example, the integration for ticketing. We mostly got to test with like Southeast Asian and South American passport. South American being the most recent example. It's been great for us to test out, because one of the most common issue in this kind of project is because we are about privacy, we cannot collect the data. So debugging is very hard to do remotely without having someone with the actual passport. Now, there's some kind of standard around this, but there's always a lot of variety in this. Outside of Web3, we had some interaction with authorities a few times, mostly the French authorities. And when it came to gather requirements, essentially they started to have discussion with us and others in the field of identity on what should be respected. And they were pretty adamant about respecting people's privacy. So the requirement was that none of the parties, like the website needing to verify the age, nor us or anyone else involved, shouldn't learn anything else beside the fact that the user is over 18. So that was part of the requirements. Regarding security and auditing, they were a little bit more flexible, but I guess that may depend from country to country.
Okay, good. Yeah, we started like Zero Knowledge Passport not as isolated product. We tried like to launch several solutions for digital protests. So that's like the reason why we have like very specific audience. And our like main requirement was like to keep people safe, because we have launched like the first pool for Russian oppositioner, and almost 40,000 people like supported like this movement. And definitely for their conditions, we had like only one requirement: to keep all data private. So you shouldn't be able to recognize who exactly voted, who exactly supported this like specific positioning option. Yeah, the biggest problem was we have standards for passports, but very often they are not like supported. For example, standard says you shouldn't use SHA-1. We are analyzing Russian passports, they use SHA-1 function. Data, so also like standards say which data should be present in the passport, but they don't like specify the specific sizes of specific data groups. Sometimes some data groups can be missed, some of them can be larger than they should be. And if you're working with like circuits, it's like better to have like all data are constant and like known in advance. So probably we have a kind of standard, but it's very like difficult to work with a standard if you're trying like to keep the privacy.
Yeah, I mean, Raramo has a very unique use case because it's not as simple as, let's say, age verification, where you can prove multiple times that you're above this age. It's for voting, so you are only allowed to vote like once or whatever n times. So yeah, can you say more about how you achieve this kind of rate limiting feature while keeping people private?
Yeah, that's a very good question, and that's like a huge another problem. You cannot derive uniqueness from the passport like without additional empathy protocol, because there is an assumption that government knows everything. So government should know all data which is included into the passport. So you cannot rely only on like on the passport as like for uniqueness criteria. But it's like very crucial for digital voting. But for digital protests, we have like no such a problem, because we need only like to calculate how many people supported something. In this case, yeah, some people can have like 2 passports, probably more. Some of them can be expired. But anyway, it's like very difficult to have, I don't know, 100 of like passports like for one person. So that's like the reason why we didn't launch a voting solution. We like launched the kind of the solution for digital petitions, the solution for like for the people when you need like only to prove that you are eligible. And yeah, so I'm for example, I'm Ukrainian, I'm adult, and I wanna like to reveal what exactly I'm thinking about specific object, and that's it. So like, yeah, there is like a huge problem with uniqueness. So if you wanna like to launch the digital voting solution within some particular country, you need to dedicate some responsible parties and build an MPC protocol between them. In our case, we couldn't allow that.
So if I express support for a petition, couldn't I, with a single passport, do it multiple times?
You couldn't, because we have built registries. What the registry is, you can create an association between the hash value of the passport and additional secret. And you need to do that in advance. And when you're starting like this petitioning process, you are using this additional secret as a source of your uniqueness. So you need to leave a nullifier that corresponds to the specific like secret. So yeah, it's how it was.
Yeah, that was my understanding that, yeah, basically the problem is you do need this source of entropy to sort of enforce rate limiting, but still preserve privacy, like make the action unlinkable to the passport. Theo, do you guys also need that for, let's say, ticketing? Because you don't want a single person to get multiple tickets?
So in our case, we thought about this. So the problem of uniqueness. Indeed, you can have multiple IDs. Myself, I have a national ID and a passport. Both work with ZK passport, so I have two unique identifiers, but I'm a single person, so I could cheat the system as well. But we derive a unique identifier directly from the ID data, and there is no registration process. Now, the reason why we did not want registration process is because we care a lot about UX, and from a UX perspective, it's really hard to have a system that allows you to use a secret, but at the same time not being able to retrieve it if you lose your phone. Because that secret, you need to keep it secret. How do you keep that secret? You need to store it in some device, your phone most likely, that will not leave it. And so if you lose your secret, then you will lose access to your passport because it's registered and you cannot re-registered. You could have like a registration system, but then if you do have a registration system, what condition do you have to registered to prevent like registering all the time and generating a new secret and having a new unique identifier every time? So this is a very big problem. You could use something like OPRFs, but that adds a bit more trust assumptions in the systems, and if we go offline, if all the parties go offline, then you cannot use the system anymore. So we preferred for now to remain fully stateless and just derive this from the ID data. And for use cases like ticketing, age verification, name revealing, this is pretty much enough. And yes, we cannot, voting is a big problem. Like that system cannot be used for voting as it is, because you can cheat it too easily. Like just owning a passport, for example, in an ID card, that's like beyond the registration process. I could vote twice for the same country because that's from the same country. We thought maybe you could think about ways to kind of link the passport and the national ID to the same person using like names, birth dates, or like face fingerprint, but this again is not great accuracy and you could get it wrong many times.
Yeah, I mean, this is a really good point that the security model, the threat model, is very much specific to the application, and like buying tickets and voting look very different. So you guys, like, if let's say I was like a state level adversary and I knew every single passport, by looking at the, do you guys derive some kind of hash from do you guys hash the passport number?
So we derive the unique identifier from hashing inside the circuit some of the data of the passport. That would include the signatures, among other things. So yeah, this is fully deterministic from the data of the passport.
Right.
So yes, any parties, which would include the state most likely, that knows all the data could derive the unique identifier again.
I see, yeah. And yeah, the point here is that like a state level adversary is very likely not looking at DEF Connect or DEF CON tickets and trying to de-anonymize its attendees. But yeah, a state level adversary like in Russia or Ukraine or Georgia is probably would be more interested in performing this dictionary attack. So yeah, on that note, I wanted to ask you how you guys approach threat modeling, how you guys figure out the security requirements, what trust assumptions are acceptable. How do you think about reason about the adversaries you're up against? Yeah, I want to understand like when you're deploying something in the real world, you have to be accountable for real world consequences. So how do you approach modeling privacy and security holistically in your application?
Yeah, in our case, we had a concrete adversary. So this like it wasn't imagine if we like had all assumptions what exactly their like I don't know their government can do. There is assumption that it knows everything. There is an assumption that, for example, government can take your passport and like try to define if you participated in some pool. Additional assumption that government can print these passports, I don't know, for free, almost for free. And it was like additional problem that people ask it how you can prove that you are an owner of this specific passport, because somebody can steal that and use instead of you to participate in the voting solution. And that's the reason how we came to like more probabilistic proofs. That's the reason why we started working on this kind of ZK ML stuff, when you can privately prove that you're the same person as defined in your passport. So you can take a photo from the passport, you can scan your face, and like create a proof of proximity that's the distance between these like two vectors under a particular threshold. So that's like
country and the fact that they signed this data, and do you trust that state from not issuing a bunch of fake passport? Do you trust them in holding their private keys correctly? That kind of assumptions, which you can get from like most developed countries, like democratic ones, but autocratic ones maybe less so. So I guess for us, when you use our solutions, it's like how much trust you put into the state that issued that country, the passport. Otherwise, regarding not stealing someone else's passport and using it with our app, that's also something we're going to work on. We're going to get a new feature soon, which is like similar to Rarimo. We're going to check the face on the passport is the same as the person generating the proof with the camera. Although we do not believe yet that ZKML is necessary, because you already trust the hardware of the phone to get the image, the video. So if your level of trust is already the device, we can just trust the execution environment of the phone and use the Apple or Google's attestation service to attest of the execution of that comparison and the liveness check, and then verify the signatures resulting from that into a zero-knowledge proof that we can add to the rest of our proofs. So this will be soon out soon, so we can have like higher guarantee in our proofs.
Okay, so the face recognition is like completely local in the device.
Yeah, completely local and attested by the Apple Attestation Service on iOS and Google's Attestation Service on Android.
Yeah, that makes sense. Alex, do you have thoughts on whether we need ZKML?
Yeah, so trusted execution environment is like a very good trade-off, like under current conditions. But finally, we need like to came the solution that doesn't require any like trusted model, because trusted execution environment always is worse than some permissionless and trustless model. So ideally, it's like the problem that, for example, this like neural network that we launched, it, for example, doesn't recognize me, because me in my passport and me right now, these are like totally two different people. And I have the same problem in like each aviation service. So this model definitely works how it works. And we're gonna like move to, like, we're gonna increase the accuracy of this model, et cetera, but I believe finally, I don't know how many years we need like to do that, but finally you shouldn't rely on some model, like, yeah, even in the case if that's attested by Google, I don't know, NVIDIA or somebody else. But yeah, trusted execution environment right now, that's a trade-off, and it's a very good trade-off from efficiency perspective.
Right. Yeah, I think this brings me to the elephant in the room, which is Google. So, yeah, I guess we've discussed threat models, like we've discussed the issuer as the adversary, the nation, state, country. We've discussed kind of the holder as the adversary, like if you steal someone's passport to try to pass it off as your own. But we haven't really discussed the wallet provider as the adversary, so namely Google Wallet. Yeah, I wonder, what a motivated wallet provider adversary could do. And so another thing that made me think of Google Wallet is, they're very much also relying on the device's trusted hardware for liveness. They call this device binding. So at the time of presentation of the proof, they need your trusted hardware to do an ECDSA signature. But this is a weaker than requiring your trusted hardware to run an ML model, let's say. Because this is requiring the trusted hardware only to prove knowledge of a secret signing key. So you're only relying on it for confidentiality and not integrity. But yeah, I guess I wonder how much you guys have looked into the Google Wallet architecture and what details of their architecture would you be the most curious to understand and that you think it's important for consumers and for users to pay attention to?
I had a quick look at it. So I didn't read the actual full paper, nor did I read a lot about it, but I did listen to the ZK podcast, which was very helpful on this, the latest one, where they actually talked about it. And from what I understand, this is very much modeled after the mobile driving license system, which is kind of US-centric, because the thing about the US is that compared to Europe or like many other countries, the driving licenses are the most common way of identifying yourself. In Europe, it's not really. It's actually legally most of the time not recognized as such. It's either national ID or passport. But like driving licenses are not using the same standard as passport and national IDs. So you need to go about it a bit differently. And the way some companies also tried that before, the way you need to do this is that this idea of like digital driving license is you bind it to the phone. So you have to go to the DMV office, and that was not physically until now, I guess, until Google like made it possible online. But like you go to the representative, the public servant, and then they would issue it directly on your phone, and then you would get like a public key derived from the private key in the secure element that doesn't leave the secure element, but then it identifies your phone and it binds that digital driving license to your phone. If you lose your phone, then you need to do it again, issue it again. So that seems to be the same process, but online, and that you have to go through Google system to do that. They act as some kind of proxy, and then it's an active issuance system. And from what I understand, they also support passport, but they also have to do that same system rather than using the kind of system we use where we directly scan the NFC chip and we just get like the guarantee directly from the state, rather than having to reissue it again or interact directly with the authorities. So it's a bit more of an active system where you need to cooperate directly with the authorities rather than passive where you just use an already established standard for like decades. Because in the case of passport, that standard is international, set by the United Nations, and we only need to read the data. We don't actually need permission to read the data. We just need the user to give us permission in some sense, but not the actual state. I guess it's easier though to optimize for, because they derive their security directly from the ECDSS signature of the secure element. So they just need to optimize for one specific signature algorithm, so they can optimize as much as they can for that, while we are kind of stuck to support a myriad of different signature algorithms from RSA to ECDSA. So performance-wise, obviously they have an edge because they do like a more custom circuit. We do have custom circuits, but for different kind of signature algorithms, so it's quite challenging. But I think we're playing on different grounds here. So, but I'm kind of interested to know how that's going to go and how things will evolve.
Yeah, they have built like a verifiable credentials. One more verifiable credentials infrastructure. And additionally, if I remember correctly, you need to prove that you need like to record kind of the video and also provide that to the verification service, and it leads to potential data leakage. So yeah, ideally, how Theo said, we need like to keep everything on client side and like not to dedicate any verifications and like this like issuance processes to some trusted authorities. So yeah, we're playing totally on like different areas.
I guess the interaction with the authority, like either through this signing with your device or recording a video, that's only at the time of issuance, right? So their idea is like, or you trust the issuer already anyway, to know everything about you anyway. So it's no problem. They get a video of you, they get a signature from your phone, that's fine. But their point is that like later at the point of verification, when you're presenting this credential, the verifier doesn't need to talk to the issuer. That's the main I think security assumptions that they're working with.
Yeah, but that does require like harder work for the rest of the world. I think the EU and the US will do just fine integrating that, but the rest, because the EU is already starting to establish this identity framework and they want to have this kind of wallet as well. Although I doubt they want to have Apple and Google take over everything. That's probably not in their mind. But that will be harder for like other parts of the world where it would be easier to just use like the already established standard.
Oh, so you're saying like issuers in other parts of the world, it'd be harder to modify their behavior?
Yeah, you have to convince them to follow the same model. Like for example, like because like East Asia, for example, is interesting. They have national ID, but quite often they don't support the international standard that we use, and they have their own thing. Some European countries used to have their own thing, but then they switched to the international standard because of EU regulation. So that can be done, but that will take a bit more time.
I see. How do you guys deal with revocation if, because one advantage of requiring issuer interaction at time of registration is that you can let the issuer like revoke, like they can refuse to issue. Whereas if you guys, I'm always just presenting my passport physically and you scan it, it could be the case like my passport hasn't expired, but it was revoked and added to a blacklist.
Yeah, that's the issue, because those blacklists, they're not available. Those so we do have the only revocation list we have access to are the certificate one, but that will only get us so far. The actual document revocation list, that's I think managed by Interpol and others. That's definitely very permissioned, and so I don't know if we ever going to be able to have like authorization to access to it. But like that's definitely a problem. That it's not a technical problem; it's like a legal and like problem, I guess, at this point. And yeah, having like directly talking to the issuer in that sense, yeah, you're gonna get that guarantee better regarding the revocation that we probably won't be able to.
Yeah, and we don't want to have to talk to the issuer at time of verification. Like, yeah.
Yeah.
Yeah, there is the biggest problem that the infrastructure with these certificates is totally public, but your verification mechanism is like local, and you cannot access to that. So only thing we can use right now as like revocation criteria is this expiration date, and that's it. We are limited with it right now.
Could you periodically sync the list of revocations? And
They are not public.
okay, they're not public.
We can track revocations of appropriate authorities, but we cannot track revocations of specific passports, and that's the biggest issue.
I see. Okay. So you can tell like which authorities like you can no longer trust, but for trusted authorities, there's no way to tell which passports they issued or revoked. Yeah, that seems like a problem. Yeah, what other interesting, like possibly subtle open problems have you run into that you think are important to focus on, that you think we don't have satisfactory solutions for, and that someone interested in privacy preserving digital identity could look at?
We've mentioned quite a bunch already. There was the issue of the uniqueness. There was the issue of like matching the person with the passport, and maybe trying to match different passport from the same person. Those are very big issues. Others that are more technical is like optimization for mobile proving. That's something we've all been working on. We've been more specifically using Noir, Brattenberg for Mastic. At first it was quite challenging, but a lot of improvement have been made, and now we're able to use it to generate proofs direct all on mobile. But that is depends a lot on the device and the ID used. So it's a very difficult mapping, and the issue with that is that most of the time we can't really predict how much memory we're gonna be needing, and it's just gonna be, well, let's see if the application is gonna crash or not. And UX-wise, this is not good. So that's something we can maybe fix with like trying to analyze like what threshold are over time by getting feedback on like at what point it crashes and on what device and how much RAM it is. But for now, it's like a bit of a pain. Otherwise, optimization like for the RAM consumption, if that comes, that could definitely help. Essentially, on mobile, what you want with the current configuration on the market in terms of like device you have, we have like about the average RAM of a phone right now that's being sold is 5 gig. A low-range phone is going to be 4 gig of physical RAM. A high-end phone is going to be at least 8. Like I have some phone that's going to be up to the 20s, but you can't expect everyone to have high-end phones. So you need to aim for whatever the low-end average is, which is 4. So what you want is like a proof that doesn't take more than 2 gig, optimally 1 gig of RAM consumption. We're not quite there yet for all our proofs, but we should be getting there fairly soon.
Cool. How much time do we have left? Like 5 minutes? Okay. Yeah, I have a lot of questions left, but I also wonder, I want to hear from the audience as well, because we have a very expert audience. So yeah, let's open the floor to the audience. If you guys have no questions, I have like 10. Okay, Patrick.
Yeah, I wanted to ask if you're familiar with IDMix, which is like a dead project from IBM a long time ago. Well, not too long. It failed, basically, and I would like to know from your perspective why you think it failed and why you think that the endeavors today that we're seeing might succeed and avoid the same traps.
IDMix, you said?
Correct.
I have unfortunately never heard of that, so I cannot give much of a reason why it would fail. I've heard of other projects that may have failed before, like, for example, I think Outdid would be an example, but that was more like a business model problem, I guess. Trying to have a business model on top of a public good like this can be quite difficult, so it's always hard to find, beyond like just a technical problem. So I'm not sure what they went through, but maybe the business model was the issue. I'm making just like a wild guess here.
What is the business model of ZK Passport?
Yeah. So the great question. I've had that question coming up a lot of times. So business model. So ZK Passport is an open source, credibly neutral project. So there's open source. So we don't have a business model on ZK Passport itself. There's no revenue generating. The point is that everyone should be able to use it, integrate it into their tech, and they want to modify it, they can do it. Although we do have like a lot of logic in the mobile app, but like the circuits and like some of the code we use between the circuits, the SDK and everything in our mobile app, this is all open source. When it comes to actually generating revenue, this is more about the kind of product that ourselves we can build with the ZK Passport. So we have, for example, Obsidian, which is a wallet we're building on Aztec, which is integrating ZK Passport for compliance and identity, because you're talking about a privacy layer 2 of Ethereum, where you are going to be transacting fully privately. So you want to be able to have some level of like guarantee that people are not going to try to launder money or some stuff. So that's the kind of thing we can use. Or otherwise, like abstracted from Obsidian or like financial things, we could do like useful tools on top of ZK Passport that could generate revenue. But ZK Passport itself, that is not meant to be a business generating like entity.
Yeah, this is like really good point because users aren't ready like to pay for their identities right now. So ZK Passport isn't for Web3, unfortunately. What the idea we came to, that's like additional reason why we started building this like registries, because to use ZK passports, ID cards, etc. properly, you need to have this infrastructure. You need to have an infrastructure with certificates, with probably some additional data. You can build kind of sanction list. You can like different Merkleized registries. And we have launched a blockchain-based solution that is like L2, where you can manage all these registries and of course, yeah, by transaction and paying fees. So it could be a business model, but in any case, it requires a lot of involvement of existing services and authorities like to use this anchoring platform.
Cool. Do we have time for one more question?
Yeah, maybe someone has one more question.
Yeah.
Do you have any thought about proof of innocence and Aztec in particular?
Proof of innocence. Yeah, that's. I mean, the current way proof of innocence are done are a bit naive. You just check a bunch of very small blacklist, I guess, of addresses. So the way the kind of thing you can directly derive in terms of compliance from ZK Passport would be like sanction list check, like sanction countries. That's nice, but that will only get you so far. You will probably need to add some stuff on top of that. still something that we're thinking through about, because you need to know what are expected in terms of compliance with the current systems and try to apply it in a way that would be more privacy preserving nowadays, and try to see how much of it you can actually do client side and really push for doing as much of it client side. Right now, the current proof of innocence have been insatisfactory, but I'm pretty sure we can build something that will work while still being private.
Cool, thank you.
Okay, and I think this is a good moment to wrap up this incredible panel. Thank you so much, guys, for... And I guess for the next panel, before we start announcing it or anything, everyone should leave Wi-Fi. Oh, okay, technology helped us. So it might take us a few minutes to bring the online speaker. But while we are bringing the online speaker, I think we can also bring offline speakers, or start bringing offline speakers. And the next panel is dedicated to ISA, to instruction sets that Cody started covering a bit, and we will continue on it. I think it's a very interesting and funny and contradictory topic. Like we are on the spectrum. Some people or some entities say that it's too early even to think about like coming up with alternative instruction sets. Other people say that we should start immediately inventing ZK custom ISA. So our next panel will talk about it. Whom we have here? We have Leo from Powder Labs. We have Carlo from Lita. We have Jacob from Risk Zero. And in a few minutes, we will have Lev on the screen, who unfortunately couldn't make it to the event. But he's so cool that he's the only speaker we are bringing online, because this discussion couldn't happen without him, if you ask me. And I will be moderating this panel because I love weird topics. And I love instruction sets and ZKVMs.
Can you hear me, by the way?
Do we still need to wait for technical? Yes.
I just wanted to check if you can hear me.
Yes, we can. Can you hear us?
Yes, and I also can hear myself, but that's not a problem.
Are we good? Wow, it was very fast. So again, welcome everyone to the panel on ISA. Most of the time, I saw conversations about ISA. They were on Twitter, and they were mostly like risk V is very bad, towards risk V is very good, and like no real middle ground, and very often no real explanation why. So today I hope that our panel and our convo will shed some light for people on like why we are even thinking about this. So let's start with some basics. First, several questions. I won't address them to like a particular person, just if you feel like answering, take it. Let's start with some basics, like what is the instruction set? And like in our blockchain world, like where is it placed?
So instruction set architecture is basically the language that the machine that you want to use speaks, and it has the commands that allow you to write programs. So it's basically that. And in Ethereum, we think of it in terms of the EVM, for example. So the EVM is a set of opcodes and memory regions that allow you to compile or to run smart contracts. You can write EVM assembly by hand if you want to. Some people do. But most people compile Solidity or Viper to EVM, and that's what the ISA is, just the EVM language, pretty much. And not only the EVM, RISC-V also has an ISA. WASM has a specific ISA. There's x86, MIPS. There's a lot of different instruction sets out there that are used by different virtual machines or physical machines or, yeah, and so on.
I think not everyone in the audience to computer science. Maybe you can like take us through the workflow. Like you have some, let's say, high-level program. How its life cycle going, and at what point we arrive into instruction set.
Yeah, so we started the high-level program, which is what programmers use: Solidity, Rust, C++, Viper, and so on, to write smart contracts or systems programs. And this is pretty high level. It's readable, readable code. And you use a tool called a compiler to transform this code into low-level, what we call low-level, weird-looking programs. They're still programs. You can open them, you can read them, you can change them, but usually you wouldn't have humans writing or reading these. They're supposed to be read and executed by either hardware, actual physical machines, or other programs called virtual machines.
Okay, thank you so much. Our next question is, what instruction sets, except for RISC-V, exist in the world and maybe existed before blockchain and before we started building the KVMs? And how, in general, we think about making a choice, maybe like when RISC-0 did a choice like 5 years ago, 6 years ago, a while ago. How you were thinking about like which instruction set to go with?
Yeah. You know, 5 years ago, like, right, founders were hanging out at a bar in Seattle, and they were like, oh, maybe we can do this thing. I think, you know, for the first few years, it was like, okay, can you actually just make a general purpose ZKVM, you know, work? Which fortunately it has. You know, nowadays, I think our thinking has changed a little bit. When you think of just like, what does the user actually care about? I think there's like 4 topics you can kind of break it down. One is usability. So like language support, how easy, you know, existing tooling already exists. Performance, so you can think latency, cost, security. So, you know, conforming around like an existing standard is quite helpful there. And then the last one is privacy. And I think with the ISA in privacy, it's less about like, do you have the capability of doing ZK? Because pretty much all ISAs do. Really, to me, comes down to like the type of machine this ISA allows you to run on.
We will circle back to that later on, like if all ISAs can do ZK. But maybe taking a step back, what ISAs in general exist in the world?
I think Leo mentioned a few, x86 and MIPS and RISC-V.
Yeah, maybe you can comment a bit like on difference, like small historical note.
I actually don't know much about that part. I know that there have been projects that, I mean, like the ISA, it's basically the instruction that your CPU takes to operate, right? So, and it has some semantics and some operands that it acts on to perform computation and be a CPU. I think during the history of computer science, there have been a lot of architectures for many different reasons and for many different usages. And like I would like computer architecture, it's a science itself that precedes blockchain.
I think some interesting historical context here is personally wasn't alive in the 80s. But we sort of had the same sort of architecture wars we're seeing with ZKVMs right now. You had 15 different chip architectures, and now we pretty much operate on x86 or RISC-V most of the time, which I think,
ARM.
or ARM, yeah. Which I think is some history that'll probably repeat itself with ZKVMs as well. We'll probably see consolidation to 2 or 3 standards.
We will also circle back to it a bit later. I want to.
Yeah, I just wanted to say, I'm sorry. Can I? Yeah.
It's very weird. You are like behind my back, but I'm talking directly. When we think about ISA for regular computer and ISA for ZKVM, what is the difference in general between mental models? And is it a good idea to take ISAs that were designed for like regular computers and apply them for ZKVMs?
Well, this begs the answer, but I would actually agree that it's sometimes a good idea. But let me, can you hear me, by the way? I'm a bit confused. Okay, so first of all, I just wanted to cycle back to the definition of ISA. I think it's like the proper understanding. It is just a very simple language, and this very simple language should not have undefined behavior. So it should have fully specified behavior. And historically, there was a lot of languages which were rather abstract, but satisfied this. For example, every functional language such as a Lisp or a Camel have an abstract machine, and this abstract machine counts as an ISA. So I would say that there is definitely a lot of like languages which would qualify as ISAs, but they are not, or even EVM is an ISA. So so there is definitely some diversity of things that are not embodied in actual hardware, but still count as an ISA. And like considering like using something made for real world, I think there are advantages and disadvantages. First of all, like obvious disadvantage is that maybe like the thing that you're trying to simulate is not exactly the same thing as physical world and has different set of constraints. And second thing is advantage might be, for example, better compatibility with existing hardware or with existing tooling such as Chemo. So yeah, that's my answer to the question.
Might be different for ZKVM and for regular computer?
I did not catch the first part of the question.
Can you give the example of the first point you mentioned, the constraint that might be different for ZKVM and for regular computer?
Well, for example, we operate over a field, so we have operations over a field faster. This is like the most obvious constraint. Another constraint is that we generally are better at things like imagining circuit out of our like making a circuit and then like making a proof of this circuit, and this is somewhat faster than actually making a physical circuit. So probably things related to like dynamically constructing circuits, the thing that I'm research is actually like I'm betting on that as one of the significant amplifiers of performance.
Okay, we collected a bit of context on ISA all in all. Now we are ready to jump to more concrete things. Let's talk about ISA in the context of general purpose ZKVM. Not ZKVM that proves Ethereum blocks. General purpose ZKVMs. So we will just, we have here the diversity of opinions. That's why we are having this panel. My first question is, okay, why RISC-V is a good idea for ZKVM design? And why it was chosen for so many ZKVMs? So people who are pro RISC-V, it's your moment.
I like Leo's answer here.
I knew you were gonna say it. I think the reason why most KVMs chose RISC-V is because of the language tooling support, basically, and because RISC-0 did it first, and they basically wrote a lot of tooling that everyone can just use to then start from a much, like you start from not from the same place. You have a lot of stuff already build a target, like a Rust target, where you can compile Rust to some sort of fake STD target, which is a lot of work, and it's merged upstream in the Rust repo as a tier 3 target, and you can just use it. You can fork it or you can use it. A few teams have forked it. We personally decided to just use it as is and then change it later on. And I think it's like, and there's a reason why RISC-0 chose RISC-V back then, which I assume is a simplicity to represent the instruction set in a ZK context. But yeah, I think the reason why we have 20 plus whatever RISC-V ZK VMs nowadays is because of simplicity plus existing tooling also pioneered by RISC-0.
Yeah, and then I can give some context on why we chose RISC-V. You know, a cool background of like the founders of RISC-V is that they've been doing chip stuff for like 20 years now. Actually, their last startup was a compiler for ML stuff for x86 that they sold to Intel, and then worked on x86 and actually TEs at Intel for a few years as well. Why did they choose RISC-V? When you think about why RISC-V is so popular and where you see it, you know, sort of in the modern world today, you find it on really tiny computers. A great example is like a Raspberry Pi. Why is it popular on tiny computers? Because there's not that many opcodes. I think I looked it up this morning, so take it with a grain of salt, but it's about 100 opcodes, which is hilariously simple for an ISA. And the nice thing that you don't have many opcodes is on tiny computers, you physically have less silica that you can put opcodes on. So it makes it, you know, really efficient for tiny computers. And what have we built with the ZK VM? We've sort of just built a tiny ZK computer. And a really nice relationship you see this with the simplicity is in ZK systems, we have these circuits and they're built with these things called constraints. In general, the more constraints you have, the less efficient your prover is going to be. So if we use a really minimal ISA that already has less opcodes, you get less constraints, and ideally you get more efficient proving. I think there's also another, you know, a bunch of other reasons. It's fully open source. The adoption over the past 10 years has been really phenomenal. We get to inherit so much great tooling from like chip manufacturers actually at RISC-0 to do performance engineering and whatnot. The spec is formally verified. Yeah, and then you get good, you know, language compatibility with Rust.
Okay, I want to think about the same question once again. We, as an industry, claim that ZK will eat the world. Whatever it means, I think we somehow mean that we would love to, there will be demand and we would love to prove many different things in the world outside of Ethereum blocks. We will want to prove execution of different programs, different signatures, different cryptography, and so on and so forth. You've mentioned 2 points, existing tooling and simplicity. Do you think that long term, like thinking 10 years forward, 15, maybe 20, optimizing kind of for simplicity and tooling will bring us to the goal of efficient general purpose proving of different things outside of blockchain?
Yeah, I think we'll see general purpose like ZK applications even using a RISC-V ZK VM in the next 2 years. This is going to be like client-side proving in general is like going to be a heavy focus on for us just the beginning of next year. For example, like it's not terrible today. We can generate a proof of like an RSA signature on an iPhone in 1.5 seconds, which has like real applications for like big tech companies. When we think long-term, 10, 15 years, I think we're totally open to approaches like Lita. You know, we're sort of like living in the now, right? We have limited runway. So we need to like build applications that people are willing to pay for. But long-term, like 10, 15 years, you know, you could totally see something Alito take dominance, something like Noir that is specifically ZK friendly and do cooler things. You know, blockchain applications are today. It's quite a big opportunity. We're focused on that. We view client-side proving as important to the world as like key pair cryptography.
Okay, let's switch to another side and ask the opposite question. Why RISC-V is a bad choice for general purpose ZK VM? And what is more important, what are other options to go with, maybe that we have today already, or maybe something that we could potentially create or design? I guess this is the question would be to Carlo and Lev. Yeah.
So I guess like the question is not why RISC-V is a bad choice, but whether like
It's speculation for the panel to be entertaining.
can we do better? And I think the answer is yes. And the answer is yes because what Lev was saying, that ZKVMs are different from hardware machines. So if you think that there is some juice to be squeezed on optimizing an instruction set for a ZKVM, then you should do it, I think. So if you think about like the history of writing circuits, it used to be like, I think ZKVM also came out because like people were trying to write Halo 2 circuits and it was horrible experience. And the industry moved on thinking about how can I simplify that for the user, and then like ZKVMs became a very natural solution for that. But it is like a mental model and abstraction that it's helpful and it works really well, but can be optimized to death. And yeah, and if you think about having long-term usage of ZKV or of proving computation, then that's something that I think should be done. And I think we already see now for practical application on blockchain space right now that a custom ISA gives really big advantages. So yeah, I would say that it's at RISC-V. It was an incredible starting point that can just be optimized.
To complement on that, I do agree with that. I think RISC-V is a good starting point. It gave a lot of people and a lot of teams a path to like the fastest way of building maybe the first, or depending who we want to consider, but first or second iteration of general purpose ZKVMs, but with like true performance. But the bottleneck is just tooling. So Lita's working on Valida, we're working on WASM stuff, different teams are working on different pieces of tooling that when you put it together, it should be more performant. And I think no one is really surprised by that. It's more work, but it's work that once it's done, it should pay off. So, and I think it's nothing special about this specific topic, it's just how it works.
For the record, Starkware was the first ZKVM, or general purpose ZKVM.
That's true.
We'll take second.
Lev, do you have something to add?
Yeah, I actually totally agree with pretty much everything that was said. Basically, I think like right now we're in the place where like RISC-V just has large head start because of the fact that all the compiler infrastructure is already working for it. But I think medium term it will likely be determined on like whether compiler infrastructure for a custom solution. So there is no doubt that custom solutions can be faster. Just like not from engineering standpoint, like from mathematical standpoint, if you like optimize everything to the same level, they likely will be faster. So the question is basically if we can make compiler infrastructure catch up or not. That's at least my opinion.
Okay, the next question is, should we design a custom ZK ISA today? Or if we shouldn't do it today, should we do it somewhere in the future? But I want to think about it from a very pragmatic perspective. So like you are ZK VM companies, or ZK VM library company. Like from the point where you are today, thinking that this is like a venture company, this is like mostly blockchain company, I think, does it make any sense for you to think about designing ZK ISA all in all? And if it's not like on your roadmap and perspective, who you think in the world should work on it? What is the right way to approach it?
I mean, we have a custom ISA. We've got the Valid ISA that was designed for improving processes.
Can you share a bit how you made this decision? Like, it's way more complicated. What was your motivation?
I think that the motivation was for exactly because, like, when you're designing a ISA, you've got some trade-offs that you can optimize, like the number of instructions versus the complexity of the instructions you want to make, and then normal computer have got problems of memory locality and like how close physically the CPU is to one cache or the other, or et cetera, and like which one should you access at what point. And the idea was to optimize these trade-offs for proving, and just don't get rid of the constraints that you're not having in your problem space. And then you've got, as I was telling you, you've got a tooling problem, then because you have to write your own custom compilation toolchain, which is painful. But I think, I mean, we've done it, and it showed great results. And like, I think if you think about it more broadly in the space, like, there are people that are building actual VPUs, verification. Like, if you think about projects like Fabric, then a custom compilation tool chain sounds like very a low-hanging fruit, I would say. So I think the process there was just to pick the best choices to optimize proving and to optimize ZKVM, and that came at a cost of having to develop some tooling. And I personally think that ISA should be ZKVM should be quite modular, and ISA should be extendable, which is also comes at like a practical cost. And I think I'd like to go back to what you were saying before, like what can you use ZKVMs apart from block proving? And I guess it's like we don't really know yet, but the fact that that the ISA is extensible, I think it really augments the use case. Because like if you think about, maybe tomorrow I find a really cool way of proving the function inside a neural net, and it's very optimized, and it's really cool, and it's really fast. And then I want to use a ZKVM for proving that. How do I plug those things together? And I think that is via a custom ISA that allows you to just make the product that you have more flexible to different applications.
That makes sense.
Yeah, we're probably sticking with RISC-V for a while. One, we'd have to change our name, and that would be a shame. We are very appreciative that more people understand the name over the past few months as we've been talking about this. I think this debate between ISAs always comes down to performance. And I think there's so many performance gains to be just had otherwise. To give you guys a bit of context, we proved our first EVM transaction about a little under 2 years ago. To do one transaction, just a token swap, $1. Pretty expensive. Today, we're proving blocks, whole blocks, so like a few hundred transfers, under 10 cents. I think, so that's a few hundred multiple down. I think we see just from a software side and just optimization side, possibly another 100x this year. And that's without even touching the proof system. we're currently doing the first rewrite of our proof system since we launched in like 2021 when we formally specified it, which we'll see like, a decent bump, like you could expect like maybe a 3 to 5x. But really it comes from like these optimizations, flame graphs, visualization tools. And the cool thing is we haven't had to build any of them because the RISC-V community gives them all to you. So you'll constantly see like internally in Slack, oh, here's a 20% bump, here's a 30% bump. And we're still getting so many performance bumps there, and there's so much low-hanging fruit that we'll probably stick with a while. I think we're aligned long-term. There's cooler things to do than just prove Ethereum blocks. But for now, that's like one of 3 use cases that we see, and it's quite important. I could also see the point to where like a RISC-V ZKVM, it gives you this like nice security and stability factor. And if we can prove a block for 1/100th of a cent, is it worth, just for that use case? I still think, client-side stuff is really cool. Is it worth, building all this tooling? Because you not only have to build like a new compiler and a new ISA and formally verify that, to get to the same point as you also have to build all the performance tooling that we just get to take from other people's work that, work in the chip community.
Okay, so far we are talking mostly about efficiency, but I want to look from another side and to talk about security. Because again, we talk general purpose ZKVM, but then this general purpose means that if we want to prove something specific, we probably have to add precompiles. And even though very often we can hear that, oh, just add precompile for that, or like, whatever, like it often circulates as something like easy, just add precompile, but maybe it's not like that, like adding a precompile is quite a heavy workflow, and adding more and more precompiles also affect, precompiles affect each other and affect ZKVM overall. So I would address this question to Lev. What is the potential security problem with just adding precompiles to whatever we want to prove?
Okay, I think these are like 2 different questions, like precompiles and security of compilation process. But let me address precompiles. I think that there is no security problem with adding a well-audited precompile. Problem is more or less that you are adding more stuff on your chip. So basically, this is the same story as I guess hardware, like in hardware frequently, like there is a story that bunch of functionalities get added as coprocessors, and then they get integrated on the main chip. So basically, just from design standpoint, having your main chip like more capable of doing things is better than trying to add something by hand. Also, as an end user, you might just not have the expertise to add a precompile, or verifiers that you set up might be not for the machine that uses these precompiles. And of course, yes, auditing process is important, but fundamentally there is nothing, it's not more, it's not harder to audit precompile than to audit just some complicated piece of code written in Rust. But more like integration problems, I feel, like sort of become bottleneck if you like bet too much on precompiles. Of course, for Ethereum, we basically make one precompile for one like heavy opcode, and then we get to pretend that we are doing EVM very quickly, but actually we are doing a bunch of circuits that that do the opcodes and just use whatever ISA for glue code, like be it RISC-V or any other, and that's it.
Going to slightly disagree with Lev. I do agree that fundamentally there's nothing more complicated about precompiles than the rest of the chip, but in practice, the precompiled chips, they do end up being quite a lot more complicated. then it depends how you implement, of course. If you make everything nicely, then maybe there's no difference. If you make everything a mess, there's also no difference. But usually in the ZKVMs that you see now, the core chips, they are usually quite minimal, they're modular, you can read them in separation. Raspberry compiles are like massive beasts, especially when you take into account that the precompiles we're interested in for Ethereum are Ketchuk, SHA, ECDSA, all these like massive things that turn into pretty crazy precompiles. But I think, and I mean, I guess both me and Lev are working in that direction of not needing to write manual precompiles anymore. So we work in this technique called auto precompiles, which is when the compiler analyzes the guest and basically automatically generates a bunch of precompiles that will accelerate the guest code. And I think this is a safer and, I mean, more efficient for sure, because you don't need humans writing precompiles. But it's also safer from the perspective of if you audit one system that scales to the rest of the precompiles, they're more suitable for firm verification and so on. So I think precompiles do somewhat generate a larger attack surface, but I do think that it is also bottlenecked by tooling in a way. And when we have custom compilers that improve that, or custom proof systems like Morgana from Lev that improve on that side, I think, yeah, it will become less of a problem.
I think it might be interesting to open the opportunity for questions if someone have questions in the audience.
Yeah, we heard a little bit about hardware in terms of like ASICs or maybe use of FPGAs to accelerate. But one ingredient that I think is important in this conversation that we don't hear as much is this future direction of just general hardware. Like for instance, I think it's true that 1 billion RISC-V chips were produced last year. Maybe they're low power kind of auxiliary chips. There's also the question of, you know, phones and so on are getting accelerators for AI, and GPUs are getting cheaper and more available, or at least more powerful. So yeah, how does that factor into when and how we make decisions about an ISA?
I think the funny thing is that like I feel like the hardware part doesn't really matter too much, unless you want to run these provers in the specific hardware. I think one specific example, like you mentioned Fabric, and then there's Irreducible as well, that is a hardware company, and they're building PetroVM, which is a ZK optimized ZKVM. But like I think for the RISC-V example, I don't think RISC-0 is planning on using RISC-V hardware. So it's more like RISC-V is kind of just a language. So I do think you get better tooling and everything by having a RISC-V ecosystem that's alive and everything. But I think the hardware part doesn't really affect. And I think it's also a matter of like what are the priorities that you're trying to focus on with the ZKVM. I think usually execution of the ISA that you have in the ZKVM is not necessarily a massive priority, because it's somewhat, but like you're not going to be executing you have to execute it for the proof, of course. But it's not like you're going to be running Ethereum transactions in that hardware. In the Ethereum case, you would be running it once just to make the proof, and then all the validators just verify it later. So you don't necessarily need that ISA to be just like run again. I'm not sure if that answers the question, but
I can add a little bit. Yeah, for proving, much means more about like the proving system. So like with the FPGAs Fabric is making, right, they'll be able to like support like binary fields and, you know, certain prime fields. For RISC-V compatibility, it might be interesting in the long term to run our executor like on a RISC-V chip. For context, our executor currently runs at like 100 megahertz. Jordi Bailina's team that is building Zisk has done some insane work the past few months where they've gotten a RISC-V like emulator up to like 2 gigahertz.
And they're jitting it to native.
Yeah. But much faster, right? If you use a native RISC-V chip, they can operate at like 5 gigahertz, so like a 2.5x. I think if we can actually get a 2 gigahertz executor in, you know, working, there will be other bottlenecks that we'll have to tackle.
Lev had a comment that we didn't manage to read because.
Yeah, there is a thesis that long term, if witness generation is the main bottleneck, then hardware-friendly ISA might be a very good choice because basically you could, of course, you cannot really just straight up use RISC-V chip, right? You would need some custom chip which is able to do some memory snapshots or something like that to be able to efficiently generate witness. But it's technically possible future that long-term hardware friendliness of ISA becomes important. But on the other hand, you could say, okay, what if witness generation is actual bottleneck, why don't we get to parallel programming and use ISA, which is more friendly for vectorized or parallel operations, or just proof of some multi-threaded computation even. So I would say that this is sort of a subtle thesis that we always will have a single threaded witness generation, and so it will be a bottleneck, but it might not be always the case, I guess.
I think Lev makes a great point, and something we're exploring is currently we all do single-threaded execution, which we think we can get up to 2 gigahertz. There's definitely ways to do multi-threaded execution, where you could start going even faster than a single, RISC-V chip. And for context, we're at 100 megahertz right now. If we were to do a 2 gigahertz executor, we're executing a mainnet Ethereum block in 100 to 200 milliseconds, which is pretty fast.
Okay, maybe we can take the last question if someone else has.
I wanted to ask the panel's thoughts on non-hardware ISAs. So I heard this interesting thesis from the argument guys that the most efficient and secure ZKVM is going to be one that directly snarkifies an interpreter for a high-level language, because you eliminate the need to simulate a maybe not so ZK-friendly machine. And I wonder what the panel thinks about this.
Yeah, I think that somewhat makes sense. I think one of the ideas in the recent storm of discussions after Vitalik's blog post and RISC-V for Ethereum was that if you have the same ISA on Ethereum and the RISC-V, or the ZKVM, then you don't have to have this interpreter to make EVM proofs, so you can do native and it's a lot faster. Which this is the EVM case, but of course if you're making for RISC-V proofs, of course that's in the current ZKVMs, it is kind of native, right? So there's no interpreter overhead, you just transpile and can be almost one-to-one, but yeah, ideally you would make that provable as well, which can be done once and then cached somehow, and but this is already the case with the RISC-V ZKVMs. I do agree that if you have some interpreter overhead, then sure it's going to be slower. But I mean, I agree with them, but isn't it already like this?
I more meant to ask, what if the ZKVM itself was an interpreter for a high-level language? Let's say, as an example, for Ethereum, what if instead of being ZK RISC-V, what if it was ZK Solidity? You took the Solidity AST and directly proved an interpreter for that. So you remove the overhead of simulating a hardware-like machine, and you just directly prove a high-level.
So it's kind of the opposite of what I was saying.
I think
that sounds cool.
Yeah, it sounds cool. I would love to see how big that circuit actually ends up being, because the EVM is much more complicated than RISC-V, and like I said,
that I disagree with.
You disagree?
Yes.
Oh yeah. But yeah, it sounds interesting.
Can I say something?
I think we will wrap up the panel. Thank you so much, all our panelists who have joined us. It was very, very interesting, at least for me. Thank you for questions. And now we give a round of applause to our speakers and panelists.
Bye, love.
And now we are having one more talk before we will have the break, and we welcome Dominic from Maiden with his talk from ZKVM to the edge. I think most of us have heard that Maiden has made quite a number of changes within last month, and very excited to hear what is happening in the Maiden world these days. Welcome, Dominic.
Thank you very much. Yeah. Oh no, we can use yours. Fine.
Welcome, Gaylord.
Yeah. Yeah, yeah. You don't want to? No, this is the game playground. Hi guys, how you doing? Do actually any of you know that guy? I guess some people do. Yeah, I'm there. So this is Bobin, and why am I showing his pretty face here? It's because the Maiden story actually ties a lot with this guy, this small winker. So I'm going to tell you the origin story of Bobin into ZK in a way, in 5 minutes. I don't want to be too long, because it relates a lot with the Maiden origin story. So funnily enough, and I'm pretty sure it relates with a lot of people in this room, the story of Bobin getting into blockchain is actually the story of Bobin getting ZK pilled. So instead of trying to figure out how to make blockchain more scalable and the next billion user, blah blah blah, he really learned about ZK because he thought that was cool. And more specifically, actually, he learned about Stark because there are quantum resistance property, and I don't know, I guess he just loved hash functions. So he was originally working on this kind of the OG of the ZK VM. So I don't know if you guys heard of this stuff in this room, maybe. Who heard of it? Oh, wow, only you. We should hire you. So this stuff was kind of the one of the, I don't know exactly if it was the first, but one of the first ZK VM to be built. It never see the, I guess, the light of production, and never went live with you, so it was more like for research. But that was back in 2020, so before the RISC-0 or stuff like that. It was actually not a RISC-V ZK VM. Then he got poached by Facebook, and as many people, I don't know, any of you worked at Facebook at some point? I know like a lot of ZK people did, or blockchain people, but yeah, there is the Aptos guy, I don't know, David Wong from ZK Security, kind of people like that who worked at Facebook with Libra and the DM project, etc. So that's he was part of that cohort, I guess, and then they fired everybody because the project was, given away. And then he got acquired by Polygon with their big, ZK Arc, where they had like so many teams. They hired Jordi Bailina. Actually, this is Jordi when he was young, by the way. They hired Bobin. They did like Polygon ID, which is now Privado, a bunch of stuff like that. All these companies are actually spinning out these days, which we did at Maiden a couple months ago. We announced that we are not part of Polygon anymore. So please do not call us Polygon Maiden anymore. These days are behind us. And in this talk, I guess we will focus on what's specific about the ZK VM, but also what's interesting is like, although he started with ZK, and as I told you, he was really ZK pilled before being blockchain pilled. The idea is like, because this ZK VM was built, he was like thinking about how to find a way to actually build a blockchain with ZK being like centric to the design. Now that we have the tools, the idea behind it is like, if Vitalik or Satoshi were building a blockchain right now, how would they do it? And well, we think at Maiden that they would do it kind of similarly to how we've built Maiden. Interestingly, and it relates to probably the last question we just had before, but I think at first Bobin and the team were exploring into ways to make it EVM compatible, with the ZKVM. And because they wanted to enable client-side proving, because of the new design that we have at Maiden being like based on the actor model, the ability to do client-side proving was very key. Well, I don't have the exact details, but apparently doing client-side proving with EVM compatibility feature is close to impossible, but happy to hear your thoughts on that. Funnily, I digged a bit in GitHub and found this GitHub discussion from, when was it from? 2022. So yeah, a bit more than 3 years ago, where for the first time he kind of put on paper, so to speak, the key components of this design based on the actor model, where every single client basically becomes its own validium, so to speak. You basically execute your transaction, prove it locally on your device, and then just send it to the network to be verified. So yeah, if you're curious about it, this is still live. This is public on the Maiden repo. So as I said, we just wanted to show that because I think the video is cool. But we announced a couple months ago that we were spinning out from Polygon, because now we are almost to the point where the blockchain is usable and ready to be brought to market. Sorry, videos don't work so well. So that was kind of the context, kind of telling you about what we're trying to build, why the ZKVM to the blockchain actually makes sense with this actor model. Now we will take a step back and I will give the mic to Dominic to, first remind you how the traditional ZKVM works, to highlight how Maiden is actually doing things differently. And this is your turn, Dominic, to speak.
Thanks. Yeah. Basically, Maiden VM is a zero-knowledge virtual machine, one of these like 25 ZK VMs out there. We are building this since 4 or 5 years now, and it is quite different, so to speak, because we use our own instruction set. The goal is to enable client-side proofs in a virtual machine, like not circuit-based, quite efficiently, and that's why we do not target RISC-V, for example, and I will explain why in my talk. So we have our own instruction set, and this comes obviously with pros and cons, as you know. We need a compiler, and somehow people need to be able to write programs on it. But like a normal zero-knowledge virtual machine, or like a normal virtual machine, basically is like, when you think about it as a black box, it gets some initial state in and some programs, and it returns a final state out. This is like a normal virtual machine. A zero-knowledge virtual machine would not only output the final state, like the result of your program, but also a proof of the correct execution of this program. And you can also inject a witness, or what you can call a private input, something that you can inject alongside your program, and that is not needed for the verifier to know, and this allows you to get privacy, so like the private execution of a program. So the witness you do not need to submit when you verify the program. And so in our case, we could inject state commitment. In our case, it could be the account or the smart contract in the initial state, and we can verify that this is the state on the blockchain. We can inject a program and like a witness, as I said, like the real state, not only the commitment and the final state. So, and then we get a final state commitment out together with the proof, and we can even like commit only to the program. So I can prove to you that I run a program with a certain hash, but you never see the real program, basically. And the thing is, like, there's this asymmetry, as you know, that proof generation might take some time, but proof verification is very fast. And so there are different approaches how you can build a ZKVM. You could go for a mainstream, or like for a more common instruction set like RISC-V or WASM. You could build a ZK EVM and use EVM bytecode in the end. Or you could say what we try to do is like a ZK optimized zero-knowledge virtual machine, and you build a new instruction set for whatever purpose you want to achieve. In our case, client-side proving. And so there are pros and cons of these approaches, obviously, but if you go for RISC-V, it's way easier to, for example, code in Rust, or you have a lot of tooling available. EVM, like or ZK EVMs, they are a bit harder to build, and there is less tooling, but it gets better. For if you build a completely new custom ZK VM, there's basically little expertise in the market and not so much tooling, so you need to build a lot on your own. But you get a very optimized zero-knowledge virtual machine. And the thing is that RISC-V, for example, would not be blockchain focused. Like, for example, like a Merkle inclusion proof on the Maiden VM you can do in one cycle, whereas if you target something like RISC-V, you need way more cycles to mimic this or to compute this. EVM bytecode is somewhat blockchain focused, obviously, and the Maiden VM is as well. And then the question is like, how performant would that be? And our goal is that, like on a consumer laptop, you should be able to create a proof very fast. And this is like possible with when you target RISC-V, but it's not not as performant. EVM is obviously not very performant, and we claim that Maiden is more performant because we basically, we own the instruction set. So how does it work? So basically the Maiden VM is Turing complete, so you can run any arbitrary program on it. It is blockchain focused, as I said, so the instruction set is optimized for blockchain specific applications. As an example, this Merkle inclusion proof we can do in one cycle, and there are some other instructions or opcodes that we have, specific for the blockchain use case. It is relatively easy to arithmetize, like it's stack-based, and we can execute untrusted programs, so to speak, because we have this, like the core structure of our programs is like a Merkleized abstract syntax tree, so we can basically hash or commit to certain parts of the program and only inject the real program code via the advice provider or the witness. So and you have isolated contexts in the virtual machine itself. So you can run only specific parts of the code as well. And what we want to have is like programmable privacy. So like because of this structure, as I explained in the beginning, you have this public input and the private input. You can inject the program or the full program and the inputs to the program in the witness, and you can have, in that sense, private programs or private smart contracts. So I can prove to you that I execute a program correctly, but I don't tell you what kind of program I did, only I tell you the commitment to the program. And it is a stack-based virtual machine that has some memory, which communicates inside the VM with the stack. And we have certain chiplets for more compute-heavy computations. For example, we have a hash chiplet that does Rescue Prime Optimize or Blake 3. We have a ACE chiplet, like an arithmetic circuit chiplet that helps us for recursive verification, and we have like a chiplet for like RAM or random access memory as well. And we have a host interface that helps us to read the witness or the advice provider basically, and all the data that we commit from there. Using the host interface, we can also like emit events during execution or debug a program basically, and the program will halt at certain debug commands or tell me where they're like at the current state of the stack, for example. And this is how the whole execution trace looks like. As I said, the goal is to have it optimized for consumer laptops or maybe even mobile phones. So our trace basically is very small, and we only have 64 columns in our VM. And this is like compared to a ZK EVM, for example, you have more than 2,000, I guess. And this helps us to be RAM constrained. So you can run a Maiden proof when you only have 2 gigabytes of RAM. And yeah, this helps us to have very small proofs RAM-wise. Performance-wise, the prover itself, runs at these numbers basically, and the proof size is, I think this is an old number, but it's around 55 or 50 kilobytes to 100 kilobytes, depending on the program that you run. And the verification time is super fast. So but this is not different to SP1 or so. We aim to have recursive verification in under 65K cycles. And this is also what we aim to have for a normal transaction on the blockchain at the moment. And like 65K cycles we can do in like 1 second or so on a MacBook Pro. And in the future, like when we remove training wheels, then we hope we can get a transaction done in 8,000 cycles. But at the moment, the lion's share of this is actually signature verification. So that I verify a signature inside the VM is just like 80% of the cycles. For signature verification, because it's Dark-based, we need to use like a lattice-based algorithm, which is Falcon. And this is very good for speed, but it's not very good because like the majority of people use elliptic curve stuff still. And this is in a Stark-based virtual machine a bit harder to implement, but we will have pre-compiles for that from August on, I guess, and then like hopefully we can support the most common curves as well. Like to give you like a sense of the performance, basically here we benchmarked SP1 and Maiden with the same program, so it should check if a certain number is a prime number. And as you can see, like on the x-axis is like the size of the prime. So for smaller primes, it is way faster. And then like if the prime number is bigger than 1 billion around, then SP1 gets faster. And that is because the setup time, or like SP1, for example, or RISC-V zero-knowledge virtual machines, they need way more time to set everything up. And then they get faster, or in that case, SP1 gets faster if the program or the proof gets bigger. But yeah, we think we can make a transaction small, so to speak, and then it should be faster to run transactions on Maiden than when you would use like a RISC-V zero-knowledge virtual machine. And this is what we aim to do in the end. So we built this zero-knowledge virtual machine to prove transactions. And a transaction on Maiden is basically defined as the state transition of a single account. So the transaction is a program that runs on the Maiden VM, and this program describes how a certain account changes its state. And this is then provable, or I get a proof out of this state transition, and then I can send this proof to the blockchain. And this makes sense, like if I commit to the state, to the initial state of the account before, then I run this program in the Maiden VM, and I get as a result the new state of the account. Then this is all the blockchain needs to know to be able to verify that. And this is what we want to do, quite fast on consumer laptops. So the transaction program actually is like a stateless program running in a Maiden VM, and it gets an account in and like outputs the account in a new state. And in doing so, it can consume several nodes, like up to 1,000 nodes, and it can produce up to 1,000 nodes. And nodes are basically just the messages that accounts send to each other to trigger state changes or to transfer assets. So I can, like a node is like a ephemeral object you can think of that can carry an asset like 100 ETH. And if I want to send you 100 ETH, then I create a node, I change my state in doing so. This is one transaction. And then there exists a node with 100 ETH on it. and then like in a second transaction, you can consume this node, and then you have these 100 ETH. And this is what we, this is basically what we want to prove. And like node scripts and account code, basically, they are all been executed in a MineVM, and they are Turing complete, so you can encode, in theory, any logic into this transaction program. The important is that transactions are executed only against a single account, because it's defined as the state transition of this single account, and it can consume 0 or more nodes and produce these nodes. But yeah, this is basically what I just said. Like a transaction program is what we run in the MineVM, and this is what it is optimized for. And so we inject as public inputs the inputs that the verifier, in that case the blockchain, needs to know. We commit certain state commitments. So like, how is the state of the account before the transaction? What's the state of the blockchain, and what's the state of the nodes database, so to speak? So which nodes do exist? And we get like final state commitments out of it. And as the witness, we inject all the data that the MineVM needs to execute this transaction. So the real program code, the real state of the account, like not only the commitment to the state, but like what is the actual state, like the storage of the account and the assets and all these things we commit as a private input. And that's why like the whole thing is then in the end private, because it never leaves the consumer device. Yeah, and I just want to show you how it is, because it's coded in Rust. It runs in, yeah, it works. It runs in also in Wasm, and we can build it here. Like, this is not optimized. It's just like a, yeah, it runs just in the browser, and I could prove it. And it proves like a super simple program in 600 milliseconds. Like, here's the proof. And like, it's basically a super simple program that adds 1 and 2 together, and the output is 3. So that's correct. This is the proof for it, of the correct execution. That's the problem with dark proofs as well. Like even if the program is small, the proof is always big. But the good thing is also, if the program is long, the proof doesn't get so much bigger, so it grows logarithmically. But this is then, I can verify that. Oh, it failed. Never do a live demo. Okay. Okay, maybe there's a bug somewhere, but it should obviously verify that to true. Yeah, not sure what the problem is. But yeah, normally it works. Yeah, that's it.
So can you mention what type of target devices you're shooting for? You mentioned like 2 gigs of RAM, and then you're mentioning that these run on Wasm. So is the intention for people to use laptops, browsers, or is it like mobile browser? Like, what type of, like, it's just like my mental model of wallets like doesn't fit here exactly. So like, yeah.
Yeah, excellent question. Like, there are different target devices we need for different applications. So users will run their wallet in the browser, so it should be optimized for that, like for normal transactions. And then like applications, like a lot of logic on mine would live off-chain, and you would only commit to something on-chain then. So for more complex applications, like you can run a complete decentralized exchange off-chain, and that would then, I don't know, consume 1,000 nodes and create 1,000 nodes and run more complex logic. And this can then run on a more beefy machine, so to speak. And like, this would be, like, normal users should use like a MacBook Pro. This is currently our target for a transaction that should be in like 1 second or so. And in 2 years, we hope to have like 500 milliseconds or so for that. On mobile at the moment, it's not super performant. Like, it takes 10 seconds or so to create a proof. This is because like on consumer laptops, we can parallelize things. This is also like a quite nice advantage of stack zero-knowledge virtual machines. But we have a delegated proving mechanism, so you can like access your laptop at home, or like a dedicated server that creates this proof for you. But we hope that also on mobile phones we will get it to 1 second in the future. Another nice advantage is like if we stay to this 2 gigabytes of RAM for one proof, then there is also like hardware acceleration available from Fabric, for example, like these Fabric VPUs. And then like the cool thing is that they have exactly 2 gigabytes of RAM, so you need to upload everything only once and don't need to use the interface a lot of time. And so it can be, especially for recursive verification, super quick using these Fabric chips. But that would be 3 different machines that would all profit from these 2 gigabytes.
Thanks. You mentioned like decentralized exchange as a thing which would run its logic off chain. How do you then address the issue of like the sequencing? Because every transaction can only touch one account. So if like you have a bunch of them trying to send nodes to the same exchange, where does the sequencing happen? Is that on the Maiden chain or somewhere else?
Yes, that's an excellent question. Like that depends on the design. Like there could be different designs. Like on Maiden, we have client-side transactions, but there's also like a concept of network transactions. So the app itself, like the operator of the app, could sequence all incoming nodes, for example, in one transaction, because you can consume 1,000 transactions in 1,000 nodes in one transaction. So then you could sequence all incoming nodes yourself, or the operator could do that. But you could also build a completely decentralized exchange, and then you would not even have an account that does the sequencing, but every node would represent one order. And then, like, if you have a list of all nodes that exist, then you can just say, I want to consume node A, F, and Z, and then you just do it locally. So there is no sequencing. There would not even, like, the whole chain would be the order book. And yeah, but then you run into race conditions. So like there are pros and cons for like several designs.
Thank you, Dominic. Please, a round of applause for Dominic and for Gaylord and for Maiden. We are now taking a half-hour snack break. You can find snacks for snack break, I guess, in the co-working upstairs. And we come back at 2 for a number of other exciting talks. Please do not be late, and see you soon.
ATM.
Liftoff of mission 41B, the first flight in the orbit of Discovery, and the shuttle has cleared the tower.
Discovery, go and throttle up.
Discovery's 4 computers now have primary control of critical vehicle functions.
Let's go scale the globe. Build on what you know. Fuck your favorite code. Like a river, the open source flows. And this how the ETH global playbook goes. But thousands into Web3. The whole world has accessibility. Never compromise quality. Create modern web capture. We're ready to start beginning our next talk of Cryptography Day. Yeah. Because the artists of our time are hackers. It's why we got to remember this is a hackathon, not a conference.
Hello. We are coming back for the second part of Cryptography Day. And our next speaker is Alexander Dante Camuto from EasyKL. And he will take it from here.
Hello, hello. So yeah, my name is Dante. I am one of the co-founders of Ezekiel, which is a company that does verifiable machine learning. And one of the ways in which we do this is using zero-knowledge proofs, which is presumably why I've been called here to talk about ZK machine learning. And originally, I had conceptualized this talk as a technical talk to kind of like breach the topic of how we might combine like two frontiers of computing that exist today. So like extremely large AI models and ZK, both like big challenges in computing. How might we get like LLMs, which require already like hundreds of GPUs to perform inference to execute within a ZK circuit. And basically, although this is a pretty interesting direction to consider, and maybe we can cover it separately in a sidebar like after this talk, I think what the space really needs, to be honest, beyond just like the ZKML space, is more discussions on why we're doing what we're doing and who cares about this technology in the first place. And I think a few years ago, we were in a bit of a different boat. You know, it was unclear what was possible using ZK. But fast forward a few years, you know, we've burned a couple $1 billion in funding and acquisitions. And it might be time for us to answer some more difficult questions as to who cares about these things. And especially now that we have some pretty magical technologies like ZK VMs and ZKML libraries, I think this is a great time to reflect on these sorts of things. And in particular in this talk, I kind of want to motivate the existence of ZKML in the first place and why it's a worthy thing to develop. So there are some familiar faces in the audience, but it might help if I give some background as to who I am. So my background is in statistical machine learning. So I did a PhD on StatML, specifically like Bayesian machine learning from like 2018 to 2022. And while I was focused on being like a good principled Bayesian, other labs like at Google and at DeepMind were focused on much simpler but much more effective solutions. So taking existing non-Bayesian models and scaling them up in data centers, and it turns out that that was a much better approach, and I probably should have been doing that instead of studying everything that this guy had come up with. But yeah, I had worked pretty closely with a lot of folks in the NHS in the UK, so their healthcare service, and I was pretty interested in methods for privacy-preserving machine learning. So methodologies by which like people that interacted with AI models could have their data kept private, or if during training there were ways to like prevent the person that was training on top of a data set to see like identifying features of that data. And I guess one of the prevailing methods in the literature, and this is still the case, is something called differential privacy. The TLDR is that during training and inference, you add a bunch of noise to your data, which sort of preserves privacy. It's not great, but it also kind of destroys your model in the process. So that felt like extremely dissatisfactory. Luckily, my PhD supervisor at the time had worked on cryptographic methods for privacy preservation, particularly homomorphic encryption, which allows you to do ML inference on top of encrypted data. And this has much harder guarantees in terms of privacy preservation. So already this is like a much more satisfying framework for preserving privacy. I got interested, I checked out basically a few FHE libraries. I think at the time there was only like 2 or 3. I tried out Sunscreen, which actually is still an ongoing project, kind of great if you haven't checked it out. But this stuff was super slow. And this is kind of how I ended up finding ZK machine learning. So this group called 0x Park, which was this research org, had released this blog post where they had basically taken like a single layer of a neural network and stuffed it into a ZK circuit, had performed inference, and it was super, super slow, but it was kind of a cool, different paradigm for privacy preservation because you could basically punt the computation of inference to one of your users. They could prove that they had run a model on some sensitive data that they had, and then send back the proof and the results of that inference to you, and in so doing, basically preserve their own privacy. And by some like completely fortuitous events, I ended up meeting up with the 0x Park guys in the summer of 2022. They introduced me to my now co-founder, and we were off to the races afterwards. And so I ended up joining this project after my co-founder Jason had started writing some code which could like basically compile some like very rudimentary machine learning models into equivalent ZK circuits. And Jason, if you listen to this recording, I'm sorry, but I took his very rudimentary academic code, cleaned it up, and productionalized it and turned it into like a fully fledged compiler that still exists today. The library started to gain interest, and the ecosystem surrounding us started to grow. So when we started this, there was only a handful of projects interested in ZKML, and fast forward to today, there's a whole host of projects that are doing this sort of thing. Some of them using our stack, some of them are developing their own. But we're now at a point where the ecosystem has truly flourished, and I think it's important to answer the question as to like why all of this is worth this amount of funding and perhaps like our time and effort. And yeah, I guess as one of the first, if not the first, like full ZKML library, we've seen this sort of technology used in lots of different ways. So obviously there's lots of use cases in crypto, in DeFi in particular. So our company manages the hyperparameters for a bunch of AMMs and lending protocols. But I guess given the state of the industry of late, it might be worth considering things outside of crypto and who might care about these things outside of a blockchain context. So I've given myself the constraint of only talking about use cases that exist outside of blockchains. But yeah, so let's start with the world at large. Who cares about verifiable ML today? And what are the unique affordances that ZK gives in this regard? And unfortunately, and I hope I don't get roasted by a bunch of you after this because I know it's pretty controversial, I'm gonna use ZK to also mean like, loosely mean providing a proof that proves computational integrity and doesn't necessarily mean like it preserves the privacy of inputs. And yeah, although privacy is super interesting and is the thing that got me interested in this in the first place, I kind of want to focus on one core affordance just to keep things simple. And I think ML is one of the forms of computation where verifiability is the most needed. A lot of ML systems operate on top of like extremely sensitive data. They're given access to extremely important control systems, which is something I'll cover. And so generally they're in the critical pathway of a lot of systems in production. So it's kind of critical that we like secure them in some fashion. So one of the forms of verifiable computation that a lot of you interact with every day, if you have an iPhone, which some of you may have, is Face ID. So whenever you unlock your phone, this triggers a pretty complex verification system. There's an infrared camera, which was actually developed by the same team that built the Kinect. And using this like infrared point cloud, there's a machine learning model that runs on a separate part of your phone, a dedicated CPU, dedicated memory, something called a secure enclave, which is not accessible by the host kernel at all. So basically, the camera system captures a detailed 3D map of your face. This data is sent to this dedicated processor, the secure enclave, and inside this protected environment, a neural network computes a map against your originally enrolled face data, and this is encrypted and protected with a key that is only available to the secure enclave. So the host OS never necessarily sees this data, and all it sees is like a true or false result with an attestation that you are indeed the person that first enrolled using this phone. And what's kind of cool is that from a verifiability perspective, it's not just useful for unlocking your phone. Other applications can actually consume this output. So your banking application, you can log in using your face. Lots of websites support Face ID verification. But one of the main issues with this is that it isn't an arbitrarily programmable form of verification. So the secure enclave on your iPhone can basically just run a few neural networks. So one of them is for recognizing your face. If you move into the domain of like some more programmable trusted enclaves, you're sort of chained to specific hardware providers. So in particular, Intel is one of the big developers of trusted enclave setups. So like SGX, TDX, if you're familiar with it. And I think what's really interesting about ZK is that you can basically prove any arbitrary computation on any device retroactively, which is super cool. It's a great affordance because it's backwards compatible with a lot of systems. A lot of people, you know, they're sort of constrained with some hardware that they configured like 10 years ago. They can't necessarily buy Intel SGX or TDX, fit that into their company. So this sort of freedom with ZK, basically a software-based solution, is super interesting. And on top of that, there's the development cost, right? If you're building a trusted enclave, hardware is super tough. If you guys have done it, it's a super pricey development process. It can cost billions of dollars to develop these sorts of proprietary chips, a lot of patent filings to protect it. But with software, as you know, like it's a much cheaper development process. And the other thing is the rate at which you can fix things if things go wrong. So if hardware or some other thing is found to be vulnerable, it can take hundreds of days to patch a security vulnerability. Patches can be measured in hours as opposed to like a year or something. So there's already some clear benefits for like where ZK can reduce costs in terms of verifiability and security. So pretty interesting. And you can kind of see this developing with like something we discussed earlier, which is like Google, as opposed to Apple, doesn't have like access to a homogeneous hardware system. And so they're kind of turning to like software-based solutions for verifiability. And so this trend is already kind of starting to come to fruition for companies that don't have access to specialized hardware. All right, so some case studies that are not necessarily crypto related. Yeah, okay. I guess generally industries that are a good fit for these sorts of things operate in extremely adversarial settings. You're basically asking a company to like take their ML model and introduce some computational overhead on top to gain some additional security, which is the ability to verify its computation. So what are some of these industries? Given the nature of the companies that we interact with and the pilots that we're trialing, it's going to be a little bit redacted in terms of like the specific names that are involved. But obviously there's crypto, but some other things. Traditional finance is one of these industries where actually there are still some gaps in trust. So in a country which I won't name, there are 10 large banks which are processing billions of transactions per day. And regulations and commercial considerations mean that interbank transfers have only minimal data attached to them. So if basically an intermediary that is brokering like a bank transfer can see like who it's going to, who it's from, and the amount, and whether it's like a valid transfer or not. But the thing is, there's kind of a need for specific, like, this country in particular has a huge issue with like money laundering and mule accounts being created with banks. So maybe someone that is laundering money will create an account with bank A that is starting the transfer and another mule account with the receiving bank, and they will shuffle money that way through the system. But the data that the network sees isn't sufficient to basically determine if the transfer is fraudulent. So this particular network is trialing out ZK proofs where they ask the banks, the sending bank and the receiving bank, to run a specific fraud detection model using ZK, generate a proof that a transaction is no longer fraudulent or is not viewed as fraudulent with the system, and to send that proof to the network when they execute the transfer. And this is kind of interesting because this model wouldn't be able to, if it was run by the network, it wouldn't have enough data. Because of the ZK proof, the different banks can execute a proof on like more sensitive proprietary data that is siloed within their walls, and then they can execute this transfer in full. But yeah, I guess another setting where things are pretty adversarial is in the energy and oil and gas system. So I was speaking to an oil and gas exec last week, and yeah, they have a pretty interesting system. So they have a bunch of control systems. Some of them are increasingly run by basic ML models. And one of the things they realized is they thought the whole system was air-gapped and completely separated from adversaries. But it turns out that they had hired a third-party provider to build out the blowout prevention system. And the blowout prevention system on an oil rig is super important because it's one of the systems that prevents the whole thing from like bursting into flames at any given moment. But one thing they didn't realize is that this third-party provider installed a telemetry system that was connected to the internet, which could presumably give anyone access to the blowout prevention system and cause enormous amounts of damage. And the thing is, like, these sorts of systems are becoming increasingly connected to the cloud, which is kind of wild. And so they're increasingly available to adversaries. And in fact, they are one of the big targets for cyber attacks is anything energy related. And in 2008, actually, there were some oil pipeline explosions, which were related to cyber attacks. And these sorts of companies already spend between 10 and 15% of their entire budget on cybersecurity to try and secure this sort of system that they've built out. But yeah, it's not limited to oil and gas either. A lot of utility systems, whether it's like water systems or the energy grid, are becoming increasingly connected to the internet and are increasingly managed by control systems and ML models. And if you install verifiability at the level of the model inference, you can start to gain additional security in these sorts of systems because you have a guarantee that the model you initially deployed to control your system hasn't been tampered with, hasn't been man-in-the-middled, that sort of thing. Okay, but there's also some really interesting non-adversarial use cases. And one of the things that we discovered, we built out a large compute cluster to service some of our customers. So we bought a bunch of custom hardware, installed it in Dallas, San Francisco, Phoenix, some other spots in the US. And if you've ever worked with hardware, you know it's kind of like a weird thing at scale. Like out of the box, you unwrap a bunch of computers and they actually don't do what they're supposed to do. Like they execute instructions wrong, they do all sorts of things that are fucked up. And these sorts of things can be hard to detect. Another thing is that once you start running these things in production, it gets even weirder. Like we were running these things in super hot places, like Dallas, and cooling is hard. And at extremely high temperatures, you can start to get like RAM corruptions where like for some reason you stored an 8 and it becomes a 12 or something else. And it's extremely hard to detect. And what's interesting is that we're not the only people that have face this problem. This is actually a huge problem for large companies like Meta, Tesla. One of the interesting things too is that it's particularly expensive for people that are doing large training runs. So the Llama 3 paper actually has some really interesting stats. So when they trained Llama 3, they had close to like 500 job interruptions because of GPU corruptions. And because these things take so long to detect, these corruptions can sometimes require them to completely restart the whole model training run because it causes drift in the training and the training of the model, which isn't necessarily recoverable. And so if you're restarting training for a model that requires 16,000 GPUs, that can start to become particularly expensive. So detecting failure pretty early is actually kind of vital for them. And they've sort of installed, they've tried to like, they have some like monitoring systems, but they can take up to like 600 hours or something to detect like an issue with the GPU. And by that time, maybe you have to roll back training 600 hours or something like that, which is never all that great. But one of the interesting things about like our system is that we were able to detect hardware failures almost immediately because we were running all of our model inferences inside ZK proofs. And almost immediately, proofs would start to fail to verify, and we could trace it back to a specific GPU, excise that GPU, and then keep going with a reduced cluster, basically. But yeah, if you look at a transformer model, which is what a lot of these labs are training, it looks kind of scary as a diagram, but it's actually a really, really, really small set of operations. And so one of the things that we're working on actually is just verifiable versions of CUDA kernel for like a specific operation. So maybe you take matrix multiplication, you add Freivalds or something else or some other verifiable algorithm, and suddenly like within the GPU kernel itself, like within the operation, you can detect if something has been corrupted, and you can almost immediately excise a node. Rather than waiting 600 hours or having to restart your training run, you can basically detect failure almost immediately, which is kind of cool. And I guess to answer the question as to like why focus on transformers, well, there's from a computer science perspective, kind of interesting. It's like two frontiers of computing, very large models, great. But also like transformers are just increasingly eating up the whole ML space. So Stripe, for example, who used to use like random forest or some other small model for fraud detection, now have a transformer-based architecture for detecting fraud on all of their transactions. Tesla, which used to exclusively use convolutional neural nets for their self-driving system, now use transformers as well. Even like image generation models, which used to use UNet or some other architecture, now use transformers as well. And so they've sort of like become unreasonably effective as an architecture, and they're just getting deployed everywhere. And so if you want to have maximum impact in the space of ML, and if you particularly verifiable ML, you might want to try to ZK transformers in particular, because long term, presumably this is going to have the most impact. Luckily, these things are like, as I showed before, it's a small set of operations. They're mostly linear operations. So a path to getting there is like Groth flavored sort of things. And in particular, Raramos, Ultra Groth, I know some of them are here, has been particularly cool to see because addition is roughly free and they've added lookups on top, which makes it a little bit more suited for ML. There's some Freivalve flavored things, which I talked about in the CUDA kernels, and we have some other things coming out soon. But broadly, like, if you think about these systems holistically, there's some interesting integration hurdles. Like, ML models never exist like in isolation. Like, if you deploy a system into production, it's not just some ML operating on like some super clean data or something. You also have to like parse some really weird data format before you shove it into the model. And maybe for security purposes, you need to make that verifiable. And so maybe you need to reach for like a ZK VM to do that part, or a TEE or something else. There is compatibility with like existing ML tooling, which is kind of rough. Like a lot of people use things like Apache Spark and those sorts of things. So getting ZK systems into those sorts of like disgusting ML ops, sort of like DevOps things, is kind of rough. And I guess primarily like one of the big issues is like data attestation. Like ML models are particularly vulnerable to manipulation of their inputs. The classic example is like for self-driving cars, you know, if you like add a little bit of tape to a stop sign, it starts to think that it's like, you know, a green light or something, and it just drives right through it. So you need to make sure that like, if you're building out a system that needs to be safe from an adversary, you need to make sure that like every input that is fed into that model is attested to. And this is kind of hard to design for, and is really like where we do most of our work when we're integrating with like some of these use cases. But yeah, thank you. Sweet.
Just a quick one regarding your last slide. I mean, you obviously cannot prevent adversarial attacks, right?
Well, yeah, you don't necessarily prevent adversarial attacks, but you can set up a system where it's much harder to manipulate the inputs, right? So for example, it comes from like an attested to sensor or something. Do you know what I mean? Like a camera with like a dedicated, you know, a dedicated enclave or something that can attest to its inputs or something, that sort of thing. But if it's in the world at large,
there is no. Basically, as far as I know, adversarial attacks have no defense.
Yeah,
I mean,
yeah.
It's a huge space of attacks that cannot be attested.
Yeah, especially if it's like, if your data is being read in from the world at large, right? So if you're developing a self-driving system, you can't prevent someone from adding tape to a stop sign unless like it's the police that's preventing it. But yeah, it kind of depends. If your full pipeline is fully digital, like say for example, you're in the on-chain setting, like you can exclusively ingest data that exists on chain currently, for example, and it's like data from an AMM. But even then, you know, like AMMs can be manipulated, Oracle attacks, that sort of thing. So yeah, you need to consider these things very carefully, for sure.
More questions?
Why, you said that someone tried to put a layer of a neural net into a circuit.
Yeah.
It was very slow. I was wondering why is it slow? What is hard about a neural net to prove?
I guess it's partially like the scale of operations, right? Because like even like a fully connected layer can be like 200,000 operations. And so these things kind of balloon in complexity very, very quickly. So you just have a lot of operations that you need to prove over. Even a conv layer can be like millions of constraints alone. Yeah, by virtue of this.
Yeah, thank you. That was such an interesting talk. I was just wondering, when you're approaching these companies like banks or like gas and oil companies, how like easy do you find it to convey like what this tech can actually do, and like what have the friction points been in actually like developing those partnerships?
Yeah, that's a great question. I think initially we pitched it completely wrong, and that we would like enter a room and start talking about ZK, which actually none of these people care about. So talking about the affordances first, so talking about like the ability to verify and like the ability to secure a pipeline is kind of more critical. But if you've worked in security before, it's kind of a hard business because you're sort of waiting for like something catastrophic to happen for people to like really understand. And so there's certain industries where they're already paranoid about these things. So like the energy industry has been hacked, you know, many times before, and so they're well aware of these things. Finance as well has experienced a bunch of issues, but like, yeah, unfortunately, yeah, if you're selling a security product, it is a bit of a, you're sort of waiting for something bad to happen for your cause to be justified, which is kind of terrible.
I think we can take one more question. maybe 2.
Yeah, so I understand that nowadays some of the new hardware is designed for like 4-bit floating points. First of all, tell me if that's wrong. But is this stuff sort of ossifying? And I mean, do these decisions direct how we might design snarks?
Like for floating point operations? Yeah, for sure. I guess like I think you're talking about like 8-bit or the FP8 or whatever. For sure. I guess currently no, because we're trying to be as flexible as possible. But in the future, if we converge to transformer architectures exclusively, then perhaps, yeah.
So actually, it's the second part to her question before about the friction point when you have to talk with these companies.
Yeah.
So let's say, you go to the industry, to the energy industry, and something catastrophic has happened. Are they just eager to take anyone, or do you encounter further difficulties? Because I would assume, basically, how open is the market? How much competition do you have there, and what do they look for when they want to use your services?
Well, actually, I think the biggest hurdle is this slide, is like how flexible your stack is to integrate with like whatever legacy thing they have running. And that's actually really hard. So like a lot of it is like sales and a lot of it is DevOps, and those are 2 things that are pretty painful for sure.
Thank you. Thank you for your talk. I feel like we had the largest amount of questions for your talk today.
Oh, yeah.
So it sparked a lot of curiosity and interest. And we are transitioning to the next talk by Franco from Taseo on co-snarks today, tomorrow, and forever. And I think that co-snarks are very interesting today, because very often when we talk about if something is possible in ZK, very often the answer is, well, no, but we can do co-snark and then it's possible. So we a bit transitioned to the place where we just suggested to add co-snark to everything to solve a lot of problems. So maybe we can hear today what really co-snarks can give us and can do for us and what they can't. And yeah, welcome Franco from Taseo.
Okay, now it works. Yeah, thanks for the introduction. Also, I need to say I'm the first time at Zoo Berlin. I really like the vibe so far. Thanks for putting this all together. And also thanks for having me. Yeah, my name is Franco. I'm an engineer from Taseo. And I'd like to talk to you today about collaborative snarks or co-snarks. To be more precise, I'd like to talk about 3 different aspects. So where we stand with the technology today, what are the challenges we are facing currently in this moment, where we from Taseo think the technology should evolve to, and the challenges for that specific steps, and then at the end a small outline regarding research that we want really to get to know, and maybe also a small call for action if there are researchers in the audience. Yeah. So first of all, I'd like to talk a really small introduction to collaborative snarks. So we heard a lot of about zero knowledge proofs and ZK snarks already, but just really going fast over there. We have very nice properties that ZK proofs give to us. The first being, for what it is usually also talked about and where I got a lot of traction in the last few months and years, is that you can get a succinct proof of for computational integrity. What this means is that I can prove to you that I computed the function correctly, and you get you can verify that proof rather fast. It's way faster than recomputing everything on your own. And funnily enough, the name-giving property of zero knowledge proofs is usually not really that interesting if we are talking about scalability. It's that when I compute a proof, I can keep the input to that function can be kept secret. So ZK is, and I think most of you know at least what ZK snarks are, but maybe not so many people are familiar with MPC. MPC is a technology that is somewhat related to ZK. It's from the same ballpark of cryptographic primitive, privacy-enhancing technologies. And MPC allows mutually untrusting parties to jointly compute a proof together, and all the inputs and the intermediate values for that function are kept secret. So to summarize, CK, I prove to you I computed something correctly and potentially keep the input hidden. MPC, we all compute the function together, right? And I only know my input and you only know yours, and we don't leak each other certain information. So now what are co-snags? You might have guessed it. Now we just take these two primitives and merge them together. We marry them, and like in a real marriage, we get the best out of each other. At least that's what I've heard, how marriages should work. So yeah, my knowledge about marriage is purely theoretical, so take it with a grain of salt. And yeah, we at Tatseo, we think mostly about two specific use cases for co-snags. The first one is we call private proof delegations. It tackles the problem of client-side proving. Usually if you want to compute a proof on lower-end devices like smartphones or similar, you often run into performance issues. Additionally, operating systems, especially iOS or also Android, is very restrictive at what they allow apps to do. So if you're trying to do an FFT or an MSM in the background, usually your operating system can just shut you down. And with collaborative snags, you can tackle this problem. You basically just you let a set of MPC nodes compute your proof. So you just secret share your input, send it out into the void, and let an MPC network compute the zero knowledge proof for you. And because of the zero knowledge property, the witness stays private, and also during the MPC computation, nothing leaks. So that's the low-hanging fruit, so to say. The more interesting use case that we think about is called private shared state. The name is not super great. We are currently discussing whether we should rename it, but yeah, if you have any ideas, come to me after the talk. Private shared state allows to compose private state from different users. So if you're familiar with privacy-aware blockchains like Adstack or Alio, they usually have private state that you can modify and roll it on chain, which is already super nice. But what you can't do is that you can't write applications that use different kind of private states from users and push their state transitions on chain. So with co-snags, you can do that. You produce the proof and then can roll it on chain. So that was a small introduction about collaborative snags. It's a flash from the past, you could say. And now I'd like to talk about where we stand today at Tatseo with collaborative snags and what the challenges are that we are currently investigating. So we started out with two different kind of toolings. We started out with co-circum. It basically allows users to use their circum circuits and compute an MPC and get a collaborative snag out of that. We support the Graph16 and Plonk prover for snag chairs. It's fully compatible. We very much focus on Graph16. We spend a lot of time of getting the performance to a place where we're pretty happy with it. We support BN254 and BLS12381, always a little bit of a mouthful. And the other tooling that we're currently implementing is CoNoir. So similar to Circum, we now want to have Noir as the input to the proof generation. It's under active development in contrast to CoCircum, which is feature complete. You just can plug in any circuit and you get your proofs out of it. It's not yet feature complete, but you can already do a lot of stuff with Noir, with CoNoir. And we currently only support the Berettenberg with ultra-honk flavor. I don't know if you're familiar with the Berettenberg naming scheme, but it's kind of confusing sometimes. But yeah, it's we currently support the ultra-honk flavor. So what are the challenges that we are facing currently? For that, I need to maybe talk a little bit about how a proof generally is generated. You have two steps when you're doing a CK proof. The first one is the witness extension. So basically going from your input to your extended witness. But basically you have to evaluate your Circum circuit or your Noir circuit somehow. Then you get the extended witness and then you feed that into your prover. And this step, this witness extension, is usually super fast on the client side, in an ordinary zero knowledge proof, because you just basically you evaluate a function and get the extended witness out of it. But for MPC, this kind of reverses, because in MPC this get rather tricky because people don't write their CK circuits with MPC in mind, of course. And additionally, you basically need, as it's arbitrary functions, arbitrary circuits, you basically need a general purpose MPC VM to evaluate that. And if people don't write their circuits with MPC in mind, that can get rather tricky. Additionally, zero knowledge proof systems are not really designed with MPC in mind as well. You have some very nice properties for ZK. For example, lookup tables, RAM-ROM accesses, which you can do, which can help you speed up your zero knowledge proofs. But those are usually not super nice for MPC. So you kind of have this step reversed, because when you're doing an ordinary zero knowledge proof, you basically compute a witness, which is super fast, and then you do the proving, which is kind of annoying, especially for mobile phones. And now you just reverse that for MPC. Now you're in a situation where the witness extension that is usually not really talked about, a little bit kept under the rug, also for the CoSNAG's research papers, you suddenly in practice need to also evaluate that most likely. Currently, when we are talking to projects that want to employ collaborative SNARKs somewhere, and they have some complicated witness extension, we talk to them whether it's feasible to do the computation on the client, secret share the witness there, and then do the proving in MPC, but that needs to be fine-tuned for every specific circuit. So yeah, that's that's where our main challenge lies at the moment. That being said, I want to show you some performance numbers that we have for Graph 16. I hope you can see it. Yeah, it looks good. I'd like to point to the 2 to the 16 and 2 to the 17 constraint size. That is where most of the projects have the circuit size that we talk to at the moment. And for that size, we are in a sub-second proving range. For the Graph 16 prover, we are, so that's for CoCircum, we are fully compatible with SNARK.js, and we are faster also than SNARK.js, and we are comparable in speed with Rapid SNARK. And with that performance numbers, we are also pretty happy to now to launch a network for private proof delegation. It's called Tatsio Proofs. We already have a network of node providers, so it's decentralized already. And projects can register there, upload their circuits and their proving keys and so on and so forth, and let their users create proofs to retrieve proofs from the network. If you're interested in that, I'm here for the next couple of days. So if you want to chat about it or have some inputs or questions, you can ask me about that. So that was where we are standing today. So to recap, building some tooling and want to tackle the private proof delegation and facing the challenge of the witness extension. And where we think collaborative SNARK should go to is the more interesting, the cooler use case. It's the private chat state one. And for that, I'd like to talk to you, bring it to some thought experiment. Imagine you have Alice and Bob, and they want to play a game of cards, right? But Alice and Bob are in cryptography since, I think, 50 years or so, and they have big trust issues. So Bob says he only wants to play a game of cards with Alice if he is allowed to shuffle the deck, because Alice will cheat. Contrary, Alice just says the same thing. She won't be playing the game with Bob because she accuses Bob to cheat. So we have a problem. Of course, there is one easy solution. They can just ask their friend Charlotte if she can shuffle the deck for them. But Charlotte secretly thinks that she likes Alice way more and will give Alice a better hand. Or another thing that could happen, maybe Bob is going to Charlotte and ask her, yeah, I'll give you $5 if you just let me win. So also here we have a problem. Alice and Bob, yeah, they don't want to have that. So yeah, maybe you've guessed it. We can engage in an MPC protocol. Alice and Bob both sample some randomness. If we are working on a large enough field, it's virtually impossible to guess the number of the other person, so with negligible probability. And the MPC network takes both those random values and samples the randomness to shuffle a set of cards. So at the end of it, the MPC nodes outputs a proof that Alice and Bob can be sure that their randomness was correctly used in the shuffling of the deck, and also that the deck was shuffled in the previously agreed on manner. They then retrieve the shuffled deck and the proof of that. So now they're pretty happy. And the other thing that's really cool now, they can also prove to other entities that they have a valid shuffling of the deck. So this can be either their friend Charlotte or maybe some blockchain. So okay, now let's think this through one more time. We want to play a game of cards, right? And we already know we can shuffle a deck. But in a real game, just shuffling a deck is like, it's kind of boring. You don't really get that far with that. So therefore, when we're playing a real game, we distribute the cards only to the respective players that they belong to. Like for example, Alice has to draw 2 cards and Bob has to draw 2 cards. We can do that by verifiably encrypt that inside the zero knowledge proof so that only Alice and Bob respectively know their cards. And what we did now is that no one on the planet knows the structure of the deck. So Alice just knows her cards, Bob knows his, but he can't know what the next cards in the pile will be. And also the NPC nodes don't know that because it's secret shared, they can't reconstruct it. So what did we do now? We created some private chat state, and I wanted to highlight this because usually when we're talking to people, people can understand when you're having private chat state, that's like, I have mine and you have yours, we can compute a function on the top of that, and we are happy with that. So you can already do really nice things with that. You can build, for example, private dark pools or similar. But what we did here now is we created a completely new private shared state that nobody knows, but we know it's a valid shuffling of the deck. So if we continue drawing from it, we know it's valid, but no one can reconstruct it and no one knows it. So that's the really cool aspect of this private chat state. We have 2 things that we think we need to know, we need to have to enable that. The first, we want to have a universal front end. We very much focused for that to be co-noir. And yeah, there's some reasons for that. First of all, Noir is pretty good. I don't know if you've played around with it, but it makes a lot of fun. The shuffling of the cards, I actually implemented it the other day. It's super cool. Pretty happy that I didn't have to do it with Circum. People are already familiar with Noir. It's like, I think in the first talk today, we had like this slide. I thought I should have screenshotted it, but it's like, yeah, people were using Circum in the beginning and now they start transitioning to Noir. So we're pretty happy with the choice we did with Co-Noir and Co-Circum. The main challenge here is the interoperability with Barettenberg, with AdStacks Prover. Something that I admitted earlier is like when you're doing a collaborative snark, the verifier isn't aware that MPC is going on. So from the point of view of the verifier, you don't know that MPC happened. It is not possible to distinguish between a co-snark and the ordinary ZK snark. So when we say we want to be compatible with Barettenberg, we want to be able to leverage the existing ecosystem, the verifiers from Barettenberg, so that we can bring that to everything where usual Noir proofs can be used. I don't know if you played around with Barettenberg a bit, but it's rather complicated, and so there's a lot of engineering going on for us, and yeah, that's still, yeah, let's see how long it will take before we are fully compatible. And the other thing next to the universal frontend that we want to have is a network of node operators. We need a network similar to the one at the CO proof, a network that produces the co-snarks for the state transitions. But if you're not talking about, if you're having a private proof delegation, you just send there your circuit and you want to get a proof out of it, and the MPC node forget everything about it afterwards. Right, but for this private chat state, it's a little bit trickier, because if we have this set of cards somewhere written on chain, we additionally need, if we draw a card from the pile, we need a valid state update so that we can prove that this draw of the card is valid, that the next draw of the card can happen. And for that, we need the proof to output valid state updates. We need to produce commitments. We need to produce nullifiers. So we basically have to re-implement the whole stack for the blockchain that we want to bring private chat state to. So that's super, super annoying, because for ordinary collaborative snarks, if you don't commit to your inputs, you can cheat. So you don't really get this publicly auditable MPC that we're really interested in. So there's a lot of engineering and fine-tuning involved there. Additionally, we also need a DA layer for persistence, because if, for example, you have a three-party MPC setting and they have the secret shares of the decks and two-party drop out of that, you just lose the pile of cards. It's gone. So therefore, you need some sort of persistence so that if something like that happens, you can roll back to a state that is already, that we know is valid, and then reject the transactions. So there's a lot of also research necessary for that part. And yeah, that's the direction that we want to go over the next couple of months. And now also for the future, so more of open questions that we are currently investigating. So we implemented Grov16 and Plonk and Berettenberg with the ultra-long flavor, right? So there is a lot of other proof systems that we still can co-snarkify. It's, for example, GNARC, still Grov16, so that would be rather easy. The witness extension is kind of hard, but yeah, we'll see. Then you can do Merlin, you have Aleo, Leo. Then really interesting for us is the Berettenberg with the mega honk flavor. It's the next version of the ultra honk flavor, so to say. But if you look really closely, you will realize that those are all snarks with a trusted setup, so they're pairing based. So what about the other big player? What about co-starks? Yeah, there it gets kind of complicated because co-starks, the polynomial commitment scheme that you're having is usually is a fry-based, is a hash-based polynomial commitment scheme, and that remains a big challenge for MPC because MPC it really shines for linear operations. So doing things like FFTs or MSMs are super fine for MPC because they are linear. So you just evaluate, if you have 3 parties, you evaluate your FFTs or MSMs on the secret shares of your MPC from the MPC nodes, and you don't need to communicate at all. But if you're doing non-linear functions like hash functions, which are inherently non-linear, those are very MPC unfriendly. You need to communicate a lot. Even if you're going to things like Poseidon, we still have the problem of this non-linearity. Doing things like Ketrek is even worse, but also with Poseidon or more friendly constructions, you have the problem that you need to potentially compute thousands of hashes, and yeah, you can't really. That's just super bad for MPC. There's one thing you could do, a small trick. Instead of committing to the polynomial in MPC, each MPC node commits only to the shares of the polynomial it has. So you have basically for every MPC node, the MPC node commits locally to the shares. So you don't have expensive nonlinear computations in MPC, but everyone just does a plain fry commitment, basically. The downside there is that the verifier work changes and increases, and also what's also super bad is that the proof set, which is already, in contrast to CK snarks, not super nice for starks, increases linearly with the MPC nodes. So if you have 3 MPC nodes, you then suddenly, it scales linear with, you have 3 commitments in the proof suddenly. And the even bigger downside is that you lose the compliance with existing provers. With existing verifiers, right? Because when you're having a Stark verifier, it just doesn't expect that the verifier suddenly needs to do different work. It wouldn't even be able to pass the proof because the proof is just bigger than it expects. We can do another trick to solve that one as well. We can have another recursion step. So basically we need to build a co-Stark verifier in a Stark, and then you verify that Stark verifier, the co-Stark verifier in a Stark. So we have one additional step. But yeah, you see that gets really complicated and really messy fast. We also didn't implement that. There are basic ideas that are floating around. If one of you is bored or have some free time, please implement that and tell us how fast it is. We don't know when we have the time to do that. But yeah, that still needs to be seen if it's feasible at all. So what is the co-CK now in the future? And that's, as I said at the beginning of the talk, that's also maybe a call for actions if there are researchers in the audience. We have co-Starks, we have this blow up and recursion trick. Would be interesting if this is feasible, if we do it that way. We need some investigations there. Maybe sometime a Stark will come around without hash-based polynomial commitments. Then maybe it's more MPC friendly, and we'll see. The other thing that would be really interesting is to have co-snark proof systems so that we don't simply snark MPCify an existing proof system, but more have proof systems that already have MPC in mind, because as I said at the beginning, CK, you have a lot of nice improvements for plain zero knowledge proofs that have very bad MPC performance, like lookup tables, or this trick where you can do an unconstrained function outside of the circuit and then just constrain the result out of that. That's super bad for MPC, and would be nice to have proof systems that are designed for MPC and CK in mind, so that you don't squeeze the last little bit extra from CK that you get, but maybe have a more MPC-friendly approach. So yeah, that concludes my talk already. Thanks for your attention. You can follow us on Twitter and LinkedIn. I'm here for today and tomorrow at least. So if you want to chat, I'll be happy, and also I'd be happy to answer some questions. I don't know if we have the time, but okay.
Patrick always have a question. It's very good.
Thanks for the talk. So at the beginning, you gave the toy example with the deck of cards. Good. Now I'm thinking, if I want to do research in this, what applications, like real-world applications, I could have? Maybe not necessarily today, but maybe tomorrow. We had a talk, for instance, before about ZKML, where you give tons of examples about where you would use it in practice. And I'm just curious about which scenarios you really have in mind where you would really use this. Either in the space or even outside of the space, actually, that would even be better.
So basically in the space, everything that you can think of about applications that are not yet possible with plain private state. So one big example that's also used in academia a lot of the times is this private dark pool example, where private dark pool, it's like you have an order book. So like you say you want to buy or sell some tokens or whatever, and you want that to be privately, so that you secret share it in a network and say, okay, I want to buy or sell that token for that amount, so that especially if you're moving a lot of money, it can change the price of the thing that you want to sell or buy. And that's one of the things that's usually talked about in academia a lot, because
Makes sense. Thanks.
Thanks. I think this is an amazing talk where you're putting MPC and ZK proofs together. It's always really interesting. You said a lot about which kinds of like proof systems you're looking into, but you haven't said much about which MPC protocols you're basing this on.
So at the moment we support as a replicated secret sharing, so an AB3-like protocol and a basic Shamir one. For the proving, we have the Shamir and the replicated secret sharing, and for the witness extension, we solely have the replicated secret sharing because we need to switch between arithmetic and binary shares quite often, and therefore we are stuck with this, or stuck. We're using this AB3-like protocol.
Okay, and actually, you had that graph about proving time, and you said like sub-second proving.
Yes.
Can you say like the security model and like the number of parties in the MPC to get to this?
That's Shamir based, because Shamir is a little bit faster than replicated for Graph 16, because you don't have to necessarily have twice the work if you have a replicated secret sharing. So that's Shamir, 3-party setting with semi-honest setting.
I was wondering, what would a MPC VM look like, and why would it be, and in what would be different from the ZK VMs that are around?
So basically a CKVM, so now that's not my specialty, but usually you're proving with a CKVM some form of some form of state transition from the VM, right? So and for the MPC VM, you really have an instruction set that you just run through. So it's basically conceptually, maybe from naming similar, but conceptually it's a little bit different. So for the MPC VM, we need to just get an intermediate representation of the thing that we want to run. So we have like a proprietary intermediate representation for MPC protocols, and then just run all MPC VMs in parallel and output something. So you don't really have to have a proof for that, like you're doing in a CKVM setting, where you prove the state transition from the VM, basically. And for MPC, so it's basically like if you're writing your own programming language, so to say, you just put in some the intermediate representation and it outputs a value. And for this MPC VM, you have to do this in 3 different, on multiple parties. And the output there is the extended witness. So you have to be compatible with the witness that you want to compute. So for example, for Graph 16, you have to output an R1CS RCS vector. But the problem there is when you're doing a general purpose VM, you have the instructions like add or multiplications. And if you are not really careful about multiplications, when you don't batch them correctly, you get a lot of latency because you have a multiplication, need a communication round, multiplication, need a communication round. That's the big problem if you want to do it with a general purpose VM compiler.
Can you talk a bit about the overhead of private shared state, like how it scales either with the number of inputs or with the number of parties? And then maybe if you can give some numbers compared to like this graph, where I assume it's not private shared state.
So private shared state, the main problem that we are having is that we can't skip the witness extension, because for that specific part, what you're seeing there is the plain prover time and not the witness extension. And that's the main challenge. Regarding inputs, it doesn't really matter too much how many different private states you're having, because it's basically the input usually is also rather small, and when you're doing the extended witness, you have to fill the intermediate values, and those are usually much larger. So that's not really a problem. It scales, of course. We are currently mostly for this three-party setting in the semi-honest setting, because you can get really performant protocols out of there. If you would scale to more parties, you lose some of that. So it scales, of course, with that. So you lose some protocols. And you also get potentially latency, because if you need to communicate with more people, the latency potentially gets worse. But yeah, the main challenge, nevertheless, is still for private shared state, in contrast to the private proof delegation we have here, is that you have to compute the extended witness in MPC, because here you just can compute it theoretically on your device and send it to the MPC network, but it's not possible with private shared state, because yeah, the private state can't leave your device, otherwise it would leak. So that's the main problem. The shuffling, to give you some concrete numbers that are implemented in Noir with 32 cards, took approximately 5 seconds at the moment, but it's for something, as it's locally on my machine. That's also if we finally have more time to get the performance numbers up to where we want them to be. It's also only a single threaded prover at the moment. I'm pretty sure that we can get that also under 1 second, but yeah. But I mean, the shuffling is a really small example.
Thank you, Franco. I think we will proceed to the next talk.
Thank
A round
you.
of applause to Franco. And our next talk is by Hinton. Welcome again to the stage on ZK standards. Seems to be an important topic, as we hope that ZK will eat the world. So.
Thank you, Lisa. Yeah, so today I'm going to talk to you about approaching a standard for generic ZK snarks. So the first question you might ask is why? Why should we even care about standards? Is it going to be useful for our work? And the second question you might ask is how? With such a great variety of ZK snark protocols, with such rapid development, like every few weeks a new proving scheme, can we actually begin to standardize or like canonize any of these protocols? And yeah, both of these questions are very much like I don't have the answers to them, but I'll try and convince you at least that there are very good reasons to care about standards, and there are a range of plausible approaches we can take. So yeah, the first main motivating reason is adoption. For those of you who haven't heard, the EU Digital Identity Wallet is set to be rolled out next year, 2026, EU-wide. And currently their design is not privacy preserving. It's using a completely linkable data format. And for this reason, the EU Commission is looking into zero-knowledge proofs as a way to instantiate anonymous credentials, to have actual privacy for digital identity. But because they're working with very high assurance systems, because they're working across many different states, they need some kind of standard to provide them security assurances. So in response to this, Google announced that they would be integrating zero-knowledge proofs for anonymous credentials into Google Wallet. And they are very much targeting the digital identity wallet use case. So Google has published an IETF draft for standardizing their proof systems. And this is basically like a requirement for integrating and deploying at that scale. So this is the main reason why we should care. I think Dante just now mentioned a bunch of contexts that are like high assurance, security related, at industrial scale. So generally, when we're thinking about adoption at these scales in these industries, we need to pay attention to standards. This is the language that they're used to speaking. So yeah, I think the question of security is really not theoretical at all. In the wild, we've seen multiple insecure implementations of just, I guess, underspecified protocols. Like the Fiat Shamir transform is a well-known one, the frozen heart vulnerability, not hashing enough things into your transcript. And when we start to compose these primitives and start to use them in different contexts, for example, in small fields, we need to reason about whether or not their soundness and zero-knowledgeness properties still hold. So what standards can do is provide a set of guidelines for the secure composition of these primitives. So adoption, security, and lastly, I think that instead of ossifying or enshrining a specific proof system, standards, if done right, can actually make our protocols more modular and easier to upgrade. So if we target our standards to a higher level of abstraction, specifying interfaces and specifying how to compose them, then we can instantiate a secure variant of protocols without having to redo the whole standards process altogether. And so this is very much what Anya Lehman proposed at Real World Crypto, kind of a new approach to standards. The IETF is used to just monolithic end-to-end standards, specifying like all the algorithms down to the wire of each protocol. But in ZK Snark land, that is not going to work for us because there are so many variants of protocols, like even of Planck alone. And these change so rapidly that I think what's a lot more likely to work is a modular standard. So, or a meta standard, where we target a higher level of abstraction and then provide a sort of standards light specifications for each variant. I think for this audience, I wanted to mention as well a bunch of related efforts. So I think people working on benchmarks have very much had to contend with this problem of how to specify some common property across a range of proof systems. Because, yeah, you need to do that before you even start to compare them. So, for example, ZK Bench, they broke it into an arithmetic backend, a circuit backend, and a Joule frontend. And they bench each component separately. I think also formal verification is very much a related effort, because formal verification needs to express protocols and specs in a way that can be translated easily to theorems, that can be broken down, can be composed. So I've been looking a little at this effort called ArcLib. They're part of the verified ZK EVM effort, and they have this nice abstraction called interactive oracle reductions, which express IOPs in a more modular way. And yeah, it also, I think it also is related to, I don't know if you've heard of this effort called Pod 2. It's by Xerox PARC. And basically, it's allowing attestations and claims to be easily composed. So they express these relations in terms of inference rules. And their goal is very much to interface with legacy attestations such as ECDSA or RSA. So yeah, I think this is my attempt to convince you that standards are very relevant to what you're working on and will be helpful to your efforts, and in fact has a nice overlap with these efforts. So all this is sort of answering the why. Yeah, I have been involved with the standards effort for a few years now, and I think now more than ever, we have the impetus and the motivation and the energy to see this through. So now the second question is how? And I've alluded already to this meta standard approach that is quite different from how the IETF does it today. So I think you're all familiar with these sort of abstractions, these layers that make up our proof systems. And the idea here is not to pick any particular combination of them, but rather to specify the interfaces between them, and then allow implementers and allow individual variants to then do a standards light for their specific component. So I'll run through the existing work and our progress on each of these layers. So for arithmetizations, there's a group from zkproof.org working with some of the Zcash authors to specify Planckish arithmetization. And yeah, so this is just one of the components in the arithmetization layer. Yeah, but they have tried to basically specify the Planckish arithmetization at a high enough level of abstraction to allow for different relations, different constraints, like lookup constraints, copy constraints that are used in practice. So on the polynomial IOP layer, I think this is maybe one of the trickiest to standardize, and we are working on it now as well. In practice, polynomial IOPs compose of many sort of sub arguments, sub IOPs that reduce down to some kind of zero check at the end. So here, I think we overlap a lot with the formal verification folks, and we can use abstractions such as interactive oracle reductions to express the composition of these arguments. So polynomial commitment schemes, one level down the stack, I think are maybe the easiest to standardize. And the reason is that in the wild, we already see generic interfaces for polynomial commitments emerging. So for example, in ArcWorks, they have this generic trait, polynomial commitments, and they implement it for KZG, Marlin, Sonic, IPA, and so on. So realizing that there is a common interface and realizing that having PCSs as a self-contained module that you can swap out is actually something that is already very compatible with our meta standard approach. So we have published a draft IETF spec last month. And yeah, so in many ways for me, it was like first contact with the IETF community and understanding their priorities, understanding their processes. There are a lot of processes. And I think, yeah, the challenge for us is to understand how ZK snarks are relevant to the IETF community. Yeah, I think in the identity use case, there's clear justification. And there are other protocols that are core to Web2 or internet protocols, such as privacy paths, for example, that we could examine. This sort of proposal for a universal start verifier was also brought to my attention by Adrian from Maiden. So yeah, already there have been there's an underlying motivation in the industry to reach some kind of common standard. And in this case, a universal verifier would make on-chain verification of Starks easier. You don't need to redeploy for every variant of Starks. And another one of our colleagues, Michele, has been sort of fighting this fate for years. He's published an IETF spec for a draft for the Fiat Shamir transform with an accompanying library called Spongefish. And yeah, as we recall, Fiat Shamir is one of the trickiest things to implement securely. So, and Fiat Shamir is used in every non-interactive proof, basically. So yeah, this is a summary of the drafts and draft documents and specs we have so far. We've also been working with the W3C data integrity community group. So they're different from the IETF. They operate on a level higher. So basically they take the core protocol specified by the IETF and use them in applications on the web level. And so they have this sort of data integrity specification for verifiable credentials. And they already have a concept of some kind of base proof and some kind of derived proof. So you can think of the base proof as an ECDSA signature. And you can think of the derived proof as a ZK snark over the signature. So we found that already our abstractions fit very nicely with theirs. And they are very much open to exploring how to integrate generic ZK snarks into their standard. And this verifiable credential standard is widely adopted. It's one of the standards that the EU Commission is considering. So yeah, I think what I want to do is end with a call to action. With the audience I have here today, I think you are the people for whom we're writing the standard. We want our standard to be useful for your work. So if our standards are not compatible with your schemes, if you're using some kind of optimization, some kind of variant that does not fit our abstractions, we would really like to know. Otherwise, another way that we would love for you to contribute is to write standard slight variants for each of these components. So whichever PCS you're using, for example, to write the specific algorithms and serializations for that variant. Yeah, I think that's all I had. Thank you.
We can take some questions.
This is a really boring topic, so it's okay if there are no questions.
No, it's not boring. But otherwise, yeah, we can just transition to the next talk.
Thank
you so
you.
much, Hintong. Leave it there. Our next topic is folding dead? And I want to tell a funny story about folding. My first pop-up city was Zuzalu pop-up city. And in Zuzalu there was some pop-up paper reading sessions where Justin Drake and Ariel Gabizon discovered hypernova, if I remember correct. And the sentiment of this session was that it will change everything. This paper, this hypernova will change everything. And then it's like 2 years later, and it changed nothing. And there is, to my knowledge, one company that has implemented folding like for production goals. It's Aztec. So maybe today Liam will shed some light on what has happened with folding. Welcome, Liam.
Thanks. Yeah. So people probably heard about folding, and maybe you wonder why more people aren't using it. So yeah. I'll first motivate like why folding is interesting and if people aren't aware. So we probably all heard of SNARKs, succinct non-interactive arguments of knowledge. Just lets you prove knowledge of some witness for some circuit. The proof should be small and constructed without interacting with a verifier. So these are used all over the place, very, very useful. Probably all know about that. Yeah, so SNARKs can be used recursively, which makes them, or it's like a very useful sort of way to use SNARKs. You can take the verifier of a SNARK and encode it into a circuit. So right, I said SNARKs allow you to construct proofs of knowledge of satisfying inputs to circuits. The verifier itself is just a circuit, and there are some theoretical like issues with doing this, but nobody cares. We use it all the time. It's fine. Maybe they're very useful because they allow you to do a bunch of different things which you can kind of do independently, but add a lot of overhead, just very, very simply. So, for example, you can very easily parallelize proving. You can take a big statement, a big circuit, break it into pieces, prove the pieces separately, and then connect them all up with a tree of proofs. This is how a lot of ZKVMs work. It's very, very practical and useful. It also allows you to distribute proving to multiple people. So, maybe you want to keep, like, it's not a full kind of co-SNARK type thing, but like in some applications, say like a private blockchain, you have transactions and different people know their own private pieces. You can keep these pieces locally separated and then make proofs locally and then combine the proofs. So it'd be like a, recursive blockchain kind of construction. And then maybe most difficult to do without recursion is incremental proving. So you have maybe you don't know the whole witness when you start proving, and it's generated over time. And so in that case, you can prove and then prove the knowledge of the previous proof as you go. So this would be like proof of validity of a blockchain, say. Yeah, and so this kind of generic construction is very practical and used, more maybe even than folding. And The configuration people usually use is you have like a Stark or like a hash-based type proof with a snark-friendly hash function, and yeah, so this works. But in some cases, recursion is very inefficient. So elliptic curve-based proof systems like Groth16 or Planck, you have two different like sort of fields where your statement that you're proving lives, and then the verifier for your proof. They'll be different. So if you want to recursively verify elliptic curve proofs inside of other elliptic curve proofs on the same elliptic curve, you have to pay a pretty significant overhead. Even worse, some types of proof systems, like the circuit for verifying the proof is larger than the circuit that you're proving. So if you tried to recurse, it would increase the work. This is like bullet proofs or IPA or something. So, and then also if you didn't want to use Poseidon or something like that, it's probably not practical to do Stark recursion either. So this motivates the question, like, can we do recursion without running the whole verifier recursively? And it turns out the answer is yes. So like this is basically how the line of work that culminated in folding schemes started with Halo from the Zcash folks. And it exploits in a kind of a fundamental way like linearity of elliptic curve commitments. And they were able to recursively combine multiple bullet proofs, which, like I said before, don't even have an efficient verifier, in such a way that if you verify this final object, the input proofs are also valid. So a lot of people started working on this, and it turns out like you can do like much better even. Like if we're trying to reduce the prover work, you can get ultimately, you get like accumulation schemes or different types of accumulation schemes and then folding schemes where you can even avoid running most of the prover. You're basically only paying commitment costs while you're folding. So yeah, like there are many different folding schemes. Nova is the first to introduce the concept of folding, Sangria, Protostar, Protogalaxy, Supernova, Hybernova, Kilonova, Mova, Neutronova. Like there's lots of them. There's like so many different papers, and so yeah, people had a lot of fun researching this question. So what happened? Lots of research, lots of different ideas. We got it down quite low, the prover overhead, at least depending on how you count. It's basically just commitment costs, but not many people use folding schemes. This isn't a complete list, but like these are some people who tried to use folding schemes, and Lurk and Nexus both stopped. Aztec still does. O1 Labs uses Halo, which is not a folding scheme, but kind of related. I don't think there are that many other people using folding schemes in production. So why? There are, so like, if you start at the high level, which I think was sort of like what people were seeing at Zuzulu last, or however many years ago, it sounds great. You can do recursion without needing to run the verifier recursively, and so it just seems like a clear win. But it's more complicated than that. Firstly, folding requires homomorphic commitments. So this is like elliptic curve commitments, KZG, Pedersen, and the commitment costs for these commitment schemes are higher than Fry and hash-based commitments. I don't know exactly how much higher, and I think it's, you know, potentially a point of contention from different people, but they're definitely more expensive. So the folding verifier also lives in a different field when you're using an elliptic curve. So in order to make this efficient, people use two elliptic curves in a cycle, where the scalar field of one is the base field of the other, and so. This allows you to avoid non-native costs when doing the folding verifier recursively, but adds a huge amount of complexity to the overall protocol. There's also this problem when using folding schemes where you need to keep the witness. So in a proof, right, the proof is supposed to be small, and you produce like a snark protocol would have a proof that's not proportional to the witness size. When you're folding, you keep the witness around, and that allows you to avoid prover work, but if you wanted to distribute this across multiple people, you'd have to send them the witness, which makes it kind of impractical with how, like, as I understand it, continuations or like recursive ZK VMs work internally. Like if you split it across computers, that adds a lot of communication cost. Then there's also this like question of which part of the proof system landscape you're focusing on. I think that people lately have been focused a lot on big proofs for ZK VMs. And in that setting, the recursion cost doesn't matter that much, because if you increase the size of the like chunk, if you will, of like the overall statement that you're folding, the size of recursion is constant or effectively constant. So you can make the ratio arbitrarily small. So this is why folding might not, or probably is not used for things like proofs of really big circuits for ZK VMs. I mean, none of this is like, you know, impossible to overcome, but still not a lot of people use folding, so there's other issues. People don't actually want like a folding scheme, they want like a proof system. And so to go from a folding scheme to a proof system, you need more. You need IVC or PCD or some kind of recursive proof thing. In fact, you often don't just want IVC, you want like something more expressive, like you break it into pieces and you have some kind of shared state amongst the pieces. And this turns out to be like the hard part, in my opinion, of building these proof systems. Like the folding scheme itself is actually quite nice and could be why people worked on them so much. Yeah, so like this then interacts additionally with the need to use two elliptic curves to make the proof efficiently, to avoid the, and I should say like this isn't strictly a requirement. Like you could use one elliptic curve, and I think there are people who do this, but it adds huge overhead in terms of the recursion. But yeah, if you want to do it with two elliptic curves, you've got to use something like CycleFold or Goblin, which are themselves very complicated. In fact, like the original Nova implementation had a bug related to like this part of the scheme, because the paper, I mean, the paper is correct, but it's sort of maybe underspecified, so the implementation was broken, which is interesting. Yeah, and then like I mentioned kind of before, the three kind of points that I brought up about recursive proofs being interesting, two of them are like proving in parallel without, you know, a lot of additional complexity, and distributed proving. Both don't really work with folding. I mean, in order to make them work with folding, you would want something more like an accumulation scheme where you go and you don't have to keep the witness and send it around. So, yeah. There's both theoretical and practical. I mean, you know, they kind of interact, right? But issues with folding schemes. So what is happening now? I think elliptic curve folding can still make sense. And there's like one sort of niche that, you know, maybe it makes sense for, which is client-side proving on resource-constrained devices. The reason for this, which I'll mention later as well, is that when you break a proof into chunks, it's sort of the symmetric version of the reason why full recursion works well for ZK VMs, because the recursion overhead can be made very small relative to the chunk size. But if your chunk size has to stay small, then the recursion overhead can come to dominate. So I think folding can still make sense there. There's also a lot of research beyond the kind of like elliptic curve folding schemes that has been still ongoing these last couple of years without using elliptic curves. So you can do them with hash-based commitments now, which is really cool. And you can also do them with lattices. And both of these don't use the traditional kind of folding paradigm, because hash-based commitments are not homomorphic at all, and lattices are only sort of partially homomorphic. And then there's some work to sort of deal with needing to send the whole witness. I think of this as sort of situated between an accumulation scheme and a folding scheme, in terms of like an accumulation scheme sort of runs the PCS and compresses the witness. A folding scheme does not. So maybe there's some way to sort of sit between these two things and do some of the PCS, or like a less efficient from a size perspective PCS, and yeah. So it's still ongoing work. These schemes, I think uniformly have higher recursion costs. So I'm actually not sure what the recursion costs of the lattice schemes are, but for the hash-based ones, the recursive verifier is log-sized, and also linear in the security parameter. And they have more work beyond just committing to the witness, which is what elliptic curve-based folding schemes got down to. So for example, in the hash-based ones, you have to do queries into the tree, but the Merkle commitment itself is like a Reed-Solomon extension, or I think now they have them for general codes, but just an encoding of the witness, which costs more. And so these like increased costs, I think, reduce the marginal benefit over full recursion. So we'll have to see how that plays out. There are benefits, though. I mean, it avoids cycles of elliptic curves, which makes, I think, the overall constructions that will arise from these simpler. They can, well, at least the hash-based ones can work with small fields, which is where like Starks derive the vast majority of their performance from, as I understand it. The lattice-based ones, I don't think do yet, but I'm not sure. And both of them are post-quantum, which is cool. But, you know, very much like still research. So my conjecture about what will happen, like with folding as we go forward, is that we're probably not going to see folding for like ZKVMs or big proofs. Because, like I said, full recursion can be made arbitrarily cheap. And there are other approaches that people can use to make these things faster. So like using GKR, which is not particularly compatible with folding, makes a lot of sense for big proofs. And distributing it over computers, either for like increasing speed or, you know, hiding parts of the witness. Maybe that could be worked out. I think client side will see folding like deployed, and it will probably continue to be an interesting research direction. So we still need client-side proving, even though people haven't really been focused on it, it seems, as much lately, for privacy, among other things. And on the client, that maximum chunk size is a lot smaller. And because of that, the full like recursion overhead dominates if you wanted to do recursive Starks. And I think that these new like post elliptic curve folding schemes smooth out this trade-off space in an interesting way. So yeah, that's all I have.
Do we have any questions? No questions. Everything was exhaustive, mutually exclusive, and very clear. Thank you, Liam.
Thanks.
We are taking one more break now. What time is that? I think we are taking 20 minutes break. And there is one very important thing for people who are like staying at Zoo Berlin as participants, that there is Zoo Berlin swag upstairs, and it will be there until 6. So if you have an ambition to have it, you might use this break to do it. But yeah, we have 4 more talks. We will wrap it up at 6. So please come back at 4:10, around that, and yeah, take a break. Okay, we are going to continue and have our last 4 sessions. The next session will be on formal verification. Then we will have 3 more on proving Linux, on emulating OP-RAND in Bitcoin, and our favorite topic of everyone, zk-TLS. Please welcome Eduardo with a talk on formal verification.
One sec. How do I... How do you do this? How do I share my screen? Is it supposed to just work? Oh yeah. Nice. Okay. Cool. All right. Thanks everyone for being here. Thanks Lisa for inviting me to do this talk. If you guys want to look for my slides later, I have links in the footer. So, who am I? I'm Eduardo. I'm a developer. A couple years ago, built a ZK verifier for NEAR. Back then, we had a NEAR dev shop. We wanted to do a ZK protocol. Funny story, we were building a mixer 2 weeks before Tornado got sanctioned, so that was fun. And well, now I work in MEV, but I mean, it's cool now, but I still have a very big spot in my heart for like cryptography stuff. And whenever possible, I try to like find connections between the two. But this is not what this talk is. So why am I doing a talk on this topic, formal verification? And you may wonder like, wait, this guy doesn't even work on formally verifying ZK-VMs. Am I being scammed? Who let this guy in? What, he's saying exactly what's written in the slides? I think I might leave. But before you do, I just want to share with you my passion for Lean. I just love Lean. I think it's so neat. And here's a snippet of code of a little theorem I proved. Not sure you guys know what Lean is. I guess we'll get a bit into that. But essentially, it's a reasoning system. It's a theorem prover, a proof assistant, that was originally meant for formally verifying mathematics. So one of the biggest cornerstone projects they have is something called MathLib, which I guess has the goal of like having all of mathematics formally verified there. And I was doing a little combinatorics exercise, and I found this theorem who wasn't there. Essentially, it's about how many ways you can partition a set. It's pretty cool, pretty neat. I mean, doesn't really impact anything. It's something we know is correct, right? I guess the point of doing like formal verification is being sure about things we're not sure. But still, a little thing, found fun. So my bull case for formal verification is that like, I think it's something way more impactful than it seems. Like, of course, everyone gets is like for security, because then like, oh, your code is correct, there's no bugs, they can't steal your money, that's good, of course. But I think it's more than that. Like, for example, AI, right? So what's the biggest problem with AI? You spin up your cloud code, it's doing your code, and then like you want to trust it because the whole point's like saving you time. But then you go there and it's wrong and you have to review, have to refactor, and then you end up losing time, right? So suppose Claude could never make an error. Suppose like you give it an objective and Claude itself can know if it's correct or not. And then it's only going to stop and bother you to review once it's sure it's correct. So which is why I think we shouldn't be training AI. We shouldn't even bother to train AI on like Python or JavaScript or whatever. Or maybe we should, but like it's more interesting to me to imagine like what it could do formally verifying stuff, because the cost benefit of it is like a lot of cost, a lot of benefit. If you can commoditize any type of programming, why not this one, which is like very costly but very beneficial. And I guess this was like more of a hot take last year. Nowadays we have like some companies with agree with it. Like of course Lean has like their research group makes this one of their like main points of like curating data sets to train AI and stuff. And Harmonic is a company that's trying to make not symbolic AI, but like making AI trained for like reasoning and math problems. That's clearly useful. And yeah, I mean, that's more or less my point. But like why, I mean, what's the relation of this with cryptography? I guess we had some talks that briefly touched on this today. Cryptography is tricky. If you forget to do a check on the degree of a polynomial, then suddenly how many lines of code are useless because there is a bug and like it's unsound and like whatever. It doesn't even work. And also because it's critical, but like if it was tricky like HTML, like centering a div is like very tricky, but like it doesn't really matter if you don't center your div, right? But cryptography is different because like it's both tricky and very critical, right? Because we are dependent on it for like privacy, for security. I mean, we depend on it so often we don't even realize sometimes. So that's why formal verification is important here. You probably don't want to be keeping like rewriting your cryptography. So even though the cost of formal verification is somewhat high, even with like AI possibly helping you, still it's fine because like it's worth it to pay this cost for this thing. It's really important, right? And programmable cryptography especially so. Like I would guess a lot of people here, like the first real cryptography project they built was probably like something around ZK, maybe MPC. And like it really makes more accessible because before you would need to like be some sort of cryptographer and come up with like a specific protocol for doing your thing. So for example, the Google thing, like now everyone's citing it, right? So they had like the anonymous credential thing, which helps them optimize their circuits, like their protocol a bit. And before like we had widespread programmable cryptography, whenever you wanted to do something, you had to invent something like that, I guess, which was not very accessible. But like nowadays we have like more less formally trained practitioners. So if we can give them higher assurance that the thing they're building is correct, that of course is better. And yeah, so my point with doing this talk is like approximately like last year, I started thinking about ZKVMs and how they were done and like the search for like real-time proving. And I was like, I don't know if I trust this thing. Because, I mean, there's pre-compiles and then like you are verifying the execution of RISC-V bytecode and you are like generating the RISC-V bytecode by using like LLVM. And that didn't seem like very trustworthy for me. So I went, like I sat on this like little journey to understand like, are my fears correct? Like, is this really such a difficult thing to make right? Can we ever really trust ZKVMs if that's the case? Like, do we need a different ISA, which is simpler? Do we need, maybe we need to verify all the precompiles? Maybe like, what do we need to do to ZKVMs so we can trust they're correct? Because, yeah, they depend on complex compiler pipelines, the LLVM thing. Soundness bugs are catastrophic because, like, supposing you're not just using them for succinctness, and even if you are, right, people say, oh, the ZKVMs are not like ZK. Yes, so the threat model, definitely they are not zero knowledge. But like in practice, most of the time, you're not gonna be able to like extract from the succinct proof of a ZKVM. No one is gonna bother to like actually go there if it's not like really ZK and extract some knowledge, right? So like for debugging purposes, it's even if you are not using an actual zero knowledge protocol, like your ZKVM is like mangling your data enough where it's like hard to extract any information from it. So my point being, if there is like some soundness bug, it's very hard to realize it, especially if you are like verifying like any RISC-V bytecode anyone could have compiled, and like you don't have many certified compiler pipelines, and we'll touch more into that. So brief intro to ZKVMs. No, you guys already know this, but okay. So what we really need to know for the purpose of this talk is ZKVMs verify traces of computation. So you have all the steps, so you can like, I mean, again, coming to that point, like, oh, ZKVMs, most of them aren't really ZK, they're just succinct verification, yes. So you could like redo the trace if you're not really trying to hide any input, I guess. Most of them target RISC-V, so most of them like model von Neumann architecture. If you guys don't know, it's essentially the thing where we like have memory and like a controller, and then like you read memory, write to it. It's like essentially the von Neumann architecture, which most of our hardware is based on. And now a not so brief intro to formal verification. So essentially, I suppose you all know something or other about logic, but essentially we have some model like some axioms of things like true or false is true, and false implies anything and stuff like that. And you just compose enough of these things so you can like have a logical statement which is sufficiently equivalent to how you reason about something. And then you use this formal framework to reach correct conclusions about it. I guess you guys probably have the correct intuition about this part. It's more or less obvious what it means. But I will be touching a lot on like dependently typed languages, and maybe less people know about those. So essentially there is like this result in computation theory that says that computation is just really another language for logic. They're like equivalent. And like if you have for all x, then some proposition p of x, that's similar to having a function that takes any x and gives you a p of x. So essentially you can transform proposition into types, and the body of programs are the same thing as proofs. And this may become more obvious throughout the talk. And then we have this thing called the lambda cube. And the lambda cube is essentially like maybe you have all heard of lambda calculus. There's lots of different types of these. And there is one corner there, the lambda C. That's the calculus of constructions, which is where most of the dependently typed languages are based on. And the cool thing about them is like you can have types that depend on the body of your programs and depend on other types as well. So it makes it very expressive because at any time you have a computation, you can reason about this computation of the type system, which is going to become more clear why that's useful. So very useful paradigm in formal verification is proof carrying code. So I guess all of you guys must have, if you ever wrote C, C++, or like Zig or whatever, you probably had an index out of bounds error. But many times, like, and then you have Rust, which always checks for index out of bounds, and then makes a lot of programmers say, oh, Rust is so bad, I always have to pay for those index checks, even though when you know you don't need them because it's very obvious in this code, it's never going to access out of bounds. So this is an sample code in Lean, which is a very simple structure. Maybe there's a lot of syntax noise there. I should have maybe deleted the comments, I don't know. But essentially, instead of just using like an uint and indexing an array of that, you have your array has in its type its size, and to access any point in this array, you don't use an uint. You are forced to use a type which contains a number and a proof this number is less than the maximum there. So in this case, fin n, you have to give any natural number and the proof that this natural number is less than n, and then you can index your array. That's a pretty basic example of dependent types and proof carrying code, but I think all of you can like kind of get why this is very useful. And this proof thing is like a type essentially. So it doesn't really have like any runtime impact, but you can reason about it like during your development process in the type system. Another example is like from the partition theorem thing I was telling you guys about. So essentially a partition is just a list of subsets, but with a few properties. You don't want any of the subsets to be empty. You want all the subsets to be different, like completely different, like have no common elements. So normally if you want to like do some like partition code in some other language, you have to either assert those in runtime, which would require iterating the array, or do no checks at all. So some like maybe some clueless user of your library wouldn't know that invariant and wouldn't respect it. And so you either pay some runtime cost to verify the invariant, or you trust your user. Both of them are not so interesting, I guess. So you could do this, for example. And okay, so typo there. But what would it actually even mean to formally verify as a KVM? So that's like one of the first questions I had when I embarked on this little like study journey, which was like, okay, lots of ZKVMs publish blog posts saying we verified soundness. So that basically means that like whenever they accept an input, it's correct, like it actually satisfies the intended behavior of the circuit. There's also completeness, which is for every correct input, you do accept it. I guess that was mentioned here briefly in previous talks. But I mean, completeness is more obvious, like when you're testing, you can always just like check that it would be accepted when you're doing witness gen or whatever. So it's easier to catch completeness. But Soundness is tricky because it could be like an adversarial string. I'm not sure you guys were here for the fuzzing talk, but like sometimes you have some really weird inputs that cause unexpected behavior, and finding them is like really hard. So soundness is tougher. Then of course, like it doesn't really matter that you're verifying that the circuit's correct, because the whole point of having the circuit is that the circuit interpreted by like this backend, like you can run it on the prover, generate the proof, and then verify the proof. So you also need to know that this process that takes a circuit and produces the prover and the verifier is correct, which would be a more traditional, maybe cryptographic proof. Like there is maybe more previous literature on those things, because I mean that was always like kind of necessary to do. And then maybe the point I'm going to stress the most is the certified compilation pipeline, right? Because as we're going to see in a few slides forward, turns out that sometimes you're proving something that doesn't really matter because there are more steps further down the line that are like not trustworthy. So if you really want to have absolute certainty of like your ZKVM is correct, you have to think about, because you have lots of compiler outputs in the process. You have like DSL that generates circuits, and then from this circuit generate a prover, a verifier, and then like the circuit is your ZKVM, but your users are also compiling something that the ZKVM is going to interpret, right? Like some RISC-V bytecode. So there's lots of compiler outputs and lots of errors in this pipeline that could not be correct. Yeah, and then essentially, I guess it doesn't matter if your ZKVM is correct if it's super hard to code something correct in it. Like, I guess everyone knows that like constraint-based things are maybe sometimes tricky to reason about. So even if you have like your one important circuit that's like your ZKVM, you have so many users and their circuits are not as like their code is not as important, and maybe like in the end the DeFi protocol is gonna like be using like that code as well, right? And if that code is not formally reasoned, I mean, I guess you could just like shrug it off and say, oh, I verified my ZKVM. It's not my fault that the user made like shitty code. But then I guess if you are deploying this thing, you would rather hope that it's like somewhat easy for like this important privacy preserving protocols to also be correct, because they are also tricky to implement and stuff, I guess. All right, certified compilation pipeline. There's like one very important project called CompCert, and I don't expect you guys to be able to read the diagram. The point is just to show the diagram is big. And yeah, essentially CompCert is the first example of a certified compilation pipeline. Whenever you compile code there, they will give you a little like certification object that you can be sure is correct. In their logical system, they use, it's currently called ROC, but it was previously called COC. I guess it was the first language based on calculus of constructions. Now we have Lean, which is getting more popular, I guess. But still, lots of things, especially like for computer science compiler stuff, are doing in ROC. And yeah, lots of boxes and stuff. It's very hard to build a certified compiler. And yeah, so there is this very important paper for computer science, I guess 90s, 80s, I don't know. Reflections on Trust in Trust. Not sure you guys heard of it. Very interesting thought experiment of like, okay, what if we have like, back then everyone would like download Linux and Linux would ship like with a C compiler. So what if I'm distributing Linux with a malicious compiler that is exactly the same as the normal compiler, except when you're compiling the C compiler. And then when this malicious program realizes you're compiling the C compiler, it reintroduces the backdoor in that program. And the source code of the compiler would be okay, because like you're seeing the source code and like it's okay. But then you have this binary that's doing some weird stuff. And I guess nowadays, like years later, we have like lots of good security analysis tools that would see a weird code path in the binary anyways. It would eventually get decompiled and whatnot. But I guess the point of the paper was like, these things are really hard to notice and they could go unnoticed for long and keep propagating themselves. So how can you ever completely trust your entire software toolchain without having built it yourself? And even if you have, you probably didn't build the hardware and stuff. So the rabbit hole goes very deep. Okay, so yeah, on a similar note, these are some Twitter threads. I guess you guys won't be able to read much from them anyways, that talk about this. Like, if you're using LLVM to compile your Rust code to RISC-V and using that in the ZKVM, how can you ever hope that to be correct? Because everyone knows LLVM has lots of bugs, and if you didn't know, now you know. I guess I have a further slide like showing some data about it. But yeah, I mean, the rabbit hole goes deep. And the two guys are discussing, I guess if you really want to read it, you can check my slides later. Okay, so as I was saying, verifying cryptographic constructions, there's lots of tools for it. I think just for the sake of curiosity, like lots of slides in this presentation are just like showing code. I don't expect you to be able to understand this code. That's like niche language or systems. But I guess it's just like to satiate your curiosity on like how these things even look like. Like how does like a formally verifying code for a cryptographic protocol looks like. So I've very effortless copied some images from the respective websites of the projects. And this one is Tamarin. So it's nice because you can see some logical symbols there, but it also helps you make this diagram which supposedly clarifies what you're doing. This is a squirrel, cute name. Squirrel is nice, like you can hear, like I took some code from their examples. This is like modeling a YubiKey thing. And I mean, of course, there is like some things you have to parse there, but more or less like descriptive, right? And then here it's like proving some properties, monotonicity, for example. I really like that they have like this like rich text kind of thing. Probably better to read. Okay, and then after certified compilation pipelines and verifying your cryptographic protocols, I guess you would verify your circuit for soundness and completeness. So this is another image I copied from someone else, Risk0, thank you. And so they are showing that most of the bugs in ZKVMs are in the circuit, I guess makes sense. Integration would be like all those like other things that I'm talking about are like an existential threat. I mean, still 9% is a lot, but most of them come from the circuit. And in the circuit, again, I guess reinforces the point. It's easy to catch completeness bugs, so completeness would be over-constrained. So like, you have a correct thing that can't be proven because you have an extra constraint that doesn't make sense. And soundness would be under-constrained because you have one last constraint and now a false string can be verified as correct. And I guess most of them are under-constrained bugs. But still, regardless, the point is like, to be completely sure, you'd have to eliminate all of them, right? But okay, so until now I've been showing you things in niche languages that like you probably never messed with before, but you know very well that like the ZKVMs are not using them, at least not like mainly using them. You know they're all made in Rust because they made sure to tell you about this in the presentation. And so how do you reason about your Rust code then? And then that's how we start talking about extraction. Extraction. So there is this like security lab Veridize, and both Risk0 and SP1 worked with them to prove the correctness of their circuits with respect to determinism. And here I have some more lean code. This is like some lean pseudocode actually, because not from any real code base. But essentially determinism is akin to like injectivity. So like and my pseudocode is incorrect, by the way. But yeah, regardless, if like you would expect, like you would prove that like with some inputs frozen, these other inputs, like if they both verify, they're both the same input. And then you are gonna like freeze all the inputs and say, I expect like this one to like be injective, or like there is only one solution. And then you run this like symbolic tool that's gonna like lots of paths and figure out if it's really the case your thing is deterministic. But yeah, it's like one property is a very important property because again, like, but it's not the only property you want to prove about your ZKVM. Okay, so finally some compilation pipeline. I stole from Risk0 again, thanks. I mean, it's no favoritism. I would steal from SP1 too, but they had no images. So before I was showing you some lean code and saying, oh, lean code is perfect because if you code in this thing, you can never do wrong code if you really try. And then this extraction thing, I guess I didn't really say what it was, right? So extraction is essentially you get the AST. AST is essentially like one of the first compilation steps of any compiler. You just like parse, and after you parse, you have the AST, which is just like a nice little data structure with like all your things with less syntactical noise. And then you put this AST into another system, which is gonna like interpret it in a different way, but more easy to reason. And then the idea of extraction is after you do that, I mean, you don't really need to write everything in the niche languages, because you can write them in the normal language and then parse them and then like just prove them there, but then you don't actually lose performance. But the problem, I mean, so the nice thing is like, since you are extracting something from some point, right? You already did some steps in your compilation pipeline and you get some compilation artifact and you extract that. So the good thing is any bugs before that don't really matter, because like if you have bugs before, they're gonna show up when you verify the extracted thing. The bad part is like that thing is still not the code you're gonna run. It's some intermediary representation of the code you mean to run. So if you have bugs down the line, and it's usually down the line where optimizer compilers kick in and introduce bugs in your code. So it doesn't solve everything. I guess you could just like use extraction to like prove properties and then use that proven stuff on a certified compiler pipeline from there onwards, and that would be completely safe. But regardless, I guess like the point is like a very good cost-benefit trade-off for like just extracting code rather than doing everything in Lean or Rock. So essentially, stonks. Another example of extraction that now this is not a ZKVM, but is a ZK circuit, so I guess we can like take some of the lessons here. So I guess all of you know WorldCoin. And even though they got a lot of flack for like being existentially unsafe, like how can I trust this orb? They try to like make it clear that they are worried about privacy and security. And one of the things they do, they have this like Merkle tree batcher. So essentially, after you get your commitment to your identity that's like unlinkable publicly, right? But like you can't really like, if your identity was banned or if your identity is like, you cannot prove that you belong to any other identity. So if something happens to this identity that like is anonymous, right? Like, or rather pseudonymous, you can do nothing about it. So it's like Sybil resistant, but anonymous, right? And so they have lots of these operations, like the most essential operation of their network, like doing insertions in this Merkle tree and deletions in this Merkle tree. And they want to prove that's correct. And so Ray Labs, I don't know, they have this proven ZK thing, which allows you to prove properties about extracted NARC circuits. And so here we have more interesting properties than rather just determinism. We have, well, I guess I can show them. I have lots of codes. Oh yeah, but let's look at some extracted code first. This is how it looks like, just like you would never write this by hand. But that's the point of the extraction tool. And then like, I guess even if the extracting tool has like some error, you wouldn't even be able to see, but then the whole point is they're gonna prove everything from this point onwards. So, I mean, it doesn't really add any security assumptions to the thing, but do this. And like, you would have to like configure your Lean compiler, your Lake build system to allow for more recursion, because I mean, these things are just so big. But, I mean, this is generated by the machine, right? You're not writing this. And the theorems you write there are very cute. So here's an axiom. So a very standard thing in cryptography, you just assume your hash is injective. Of course, you could always derive a contradiction from this because the hash is not injective. And a simple counting argument, like you're hashing, I don't know how many bytes to way fewer bytes. So, but assuming this thing, if you're not actually trying to prove a contradiction, it's very hard because you're not going to be able to derive a hash collision, right? So unless you're really trying to prove the thing wrong, it's a safe assumption to make, essentially. And then they derive that like, if you assume this like sample, like better understood higher level Ketchak circuit is injective, you can derive that the extracted circuit is injective, which is neat. And here, so I guess like, this makes a lot of sense when you read their report, because like this code, like the semantics code, though it's like in Lean, not like natural language, you can clearly see that like it matches their specification in the report. So I guess that's like one of the nice properties about like be coding in such high level language, even though this is just like if then else. And then essentially you just prove that like the behavior of your circuit is equal to the behavior of your semantics. Another standard technique in formal verification. We have the same thing here for insertion. And yeah, they also, I mean, this is more trivial, right? But they just test the Poseidon hash in one input. And I mean, probabilistic, if it's correct in one input, is probably the same function. Jolt. Jolt has some formal verification efforts too. Slightly more interesting than the other ones, which were just determinism, which is just like a simple static analysis tool. So Jolt, they defined their lookup table semantics, and they extracted their circuit that's coded in like a template language in Rust 2. Through this framework where you can reason about the semantics. And then they compare their overall thing. So Sail is essentially another like cryptographic like formal tool that has like lots of different systems, and it has like a RISC-V model inside of it. And yeah, essentially, thanks Jolt for the image. You just do this, you extract the thing, and then you have a RISC-V model, and then you have a lean backend for Sail, and then you prove the two things are the same, which is I guess similar to the thing we were seeing on the WorldCoin thing. But okay, I guess my point is like lots of these efforts are very specific. I guess once you define a semantics for a thing like Jolt, you can do more interesting things with it. But some of the other ones we were seeing like RISC-V, RISC-0, and SP1, they made like a whole project just to extract like one property, and they can't really do anything more with that because the tool like PyCos, the tool was just to prove determinism. So like they do all this thing of extracting and then running PyCos and then prove one property. I guess like my overarching point with this talk is like lots of cool things are happening with the dependently typed languages and the theorem provers. And the nice thing about them is they're composable. Supposing you already have like enough of an ecosystem on them, you can like reuse things from one project into the other, and eventually it's gonna become way like ever increasingly so easier to formally verify your new creations. Yeah, so about like leanifying the pipeline, I guess this example doesn't have the pun about lean, but it's still about making the pipeline shorter. So Powder, it's a compiler for ZK circuits. It allows you to define custom ISAs, and the idea is that, well, it's akin to LLVM, but for like Rust circuits or no, ZK circuits. And one cool thing it does is it has some auto optimization feature where it can like symbolically reason through your constraints and your ZKVM architecture and output more optimized circuits than the one you inputted. And that's obviously good. They have a blog post explaining some benchmarks with this. It's kind of surprising. And the good thing about this is that like this whole process of like inferring what parts of the circuit you can throw off, what constraints are like redundant, is like a very logical process. You could model it and like prove it's correct, or like at least give like a list of the optimizations you applied so people can like later check they were sound. So it's like an interesting idea, and maybe like the end goal of this could be to like not have precompilers anymore because we have this static analysis tool that produces code with similar performance. So about lean libraries in ZK, we have lots of them. It's funny because their names are like, it's very easy to get confused with them. Like trying to write this talk was really hard for me because, well, I guess zklib is now arclib, which makes it easier. But before you had zklib and libzk, which are two completely different things. But yeah, arclib is, I guess the previous talk mentioned this briefly. Arclib is for verifying IOPs, which is more like in regards to that point of proving the cryptographic protocol is correct. We have clean, which is a circuit DSL, but it's embedded in lean, so you could like prove theorems about it. We have zklean, which is very similar, but made by Jolt for their project. We have proven ZK, which is the thing that Ray Labs use to analyze the WorldCoin thing. We have EVM model. We have EVM semantics in Link 2. And probably have way more things. It's just hard to Google for these things because their names are so, I mean, look at this. So yeah, and the good thing is like they are all in this integrated like formal system, and you can probably like even interrupt between these things really easily if you really want to. Like, oh, I want to copy this code that's written in this circuit DSL with this other one. You could probably prove their equivalent if you really want to, and then like just lift results from one to the other. So it makes way less repetitive work, like ecosystem-wide, to like keep improving things. And then we have Argument, which I really love their thesis. They wrote Lean and Lean, and then ZK proved Lean. And so the whole point of this is that like, if you guys haven't coded Lean, it like takes a while to compile the libraries because like, I mean, you're proving so many little details about every random thing, so it takes a long time. But what if it was like really easy to prove? What if like you could like just prove things all the time and it's cheap and stuff, and like ZK allows you to do that? And not only that, you could also like prove things and like be actually ZK about it and not like just prove any logical proposition and hide some inputs. That's obviously interesting. And also, it could be the solution to have like a truly end-to-end certified compilation pipeline. Like, of course, not really, because the Lean compiler itself is not certified as of now. But I mean, it's a good step in that direction. And also, like, if you use this as your ZK VM, your programs, you would be able to like host them there and like prove properties about them. So like, instead of like just accepting a commitment, like just verifying an input with a commitment to a program that like you know what it is, you just like say, I don't know which program is it, but I know it's a spec. So you could even hide the program, but like still prove that like it does what you expect it does. That sounds useful too. Yeah, here's a diagram of them. Like their idea is like this. You could have like end-to-end stuff. In the end, you have Binius. And at some point, 1 minute, fuck. Also, they have this really cool point where like hardware, software-based isolation costs a lot. So if you could ZK prove to your kernel your software is not malicious, you could eliminate this, which is pretty dope. You can do it too. AIs are really good. I think they secretly trained AIs in Lean. They're way better than they were last year. You could probably try to learn it. There is this thing called natural number game, really easy. Google it. Learn type theory is super neat, and maybe contribute to MathLib. Thanks.
We do not have time for questions.
You can find me later if you really want.
Yeah, but then he will talk at least for an hour, so be careful. Now we are going to have a talk about ZK Linux. And I think it's very interesting because when you are talking about ZK proving something that is not like Ethereum block or something like blockchain optimized, we usually tell that there is huge overhead and like everything is inefficient and infeasible. And then someone has proven Linux, and it's kind of weird. So please welcome Karsten Waldemar Monk with his work on proving Linux. Please applause.
Are you seeing anything on the HDMI? No, it is. This is as good as it gets. Okay, so I'm Karsten. So have you ever had one of those kind of mad scientist moments where you think, well, what's the absolutely craziest thing that you can do with this technology? And when it comes to ZK, and just for good measure, this talk was originally given in 2023. So this is why it's 2025 now. So running the EVM at that point was kind of like the most ambitious idea of running a ZK. But basically, I'm here today to kind of like present something even more ridiculous, which is proving the execution of real Linux inside ZK. okay? Which is pretty crazy, right? And we're going to use a few different building blocks for this. So one of the building blocks is what's called the Cryptography machine. I don't know if anybody of you know it, but it's basically an open source RISC-V emulator. It's fully deterministic, as in you can basically stick in a disk image running Ubuntu inside it, RISC-V Ubuntu in this particular case, started from a particular point, it would always end up in the exact same point. So it's a fully featured like RV64 GC ISA. And after today, you guys might actually understand what that actually means. And I can basically put Ubuntu 24.04 inside it. And yeah, it's quite cool. So this emulator is not a proof of concept. It's something that's been developed since 2018. One of the kind of like standout features is that every single piece of the machine state, kind of much like a ZKVM in this particular case, can be Merkleized at the 64-bit word level. And also on a page level, like 4K or something like that, but that's a different thing. It's persistable, so for example, you can pause the machine just like in a video game, save your progress, and resume right off where you left off. And even the virtual machine itself saying, okay, I want to take a break, and let's say receive some input from the outside. And this is a very, very not so humble opinion that the ultimate runtime for ZK apps is basically a general purpose processor that can pretty much run a full 64-bit operating system. We are not there completely yet, and I'm not condoning anything that I'm presenting in this talk to actually be running in production, but hey, it's cool. So I'm going to presume most of you know about RISC-0, but just very, very simply, it's kind of like a RISC-V microprocessor. It's verifiable using the ZKVM. It basically allows you developers to write ZK proofs almost like you would code for a normal computer. And you might start seeing a couple of weird things here. So for example, it's a 32-bit RISC-V ISA. There's around 192 megabytes of RAM. Those kind of things. Another kind of like nice feature is that you can use continuations. This in 2023, this was kind of new, continuations, but nowadays it's pretty much standard. Basically, you can pretty much run your code as long as you want, and your code, you can recurse it, you can use online services and those kind of things. So yeah, that's basically RISC-0 kind of like in this particular case. So how exactly do we fit a full 64-bit address space that can be, let's say, an 8 gigabyte RAM Ubuntu machine with a full root file system inside a 32-bit guest in this particular case? And I'll kind of get to that in a moment, how we exactly fit this ball inside a car, right? So here's kind of like the game plan, because what we actually want to prove is that we are starting from a particular machine state. We run X amount of RISC-V 64-bit GC cycles, and it becomes a new state. So because it's Merkleizable, basically this is a state hash, right? And what I was doing in this experiment was basically including sufficient amount of the Cryptography machine code inside a RISC-0 guest, so you can pretty much run an entire RISC-V cycle execution in there, right? Wait. Okay, and then here's kind of like the trick how we have the 64-bit address space, because, well, we have the state hash, right? So basically what we can do is basically give Merkle proofs of every single state access, because the Cryptography machine, when it's actually executing, it will actually be able to record every single memory access that it's doing and putting into a log, essentially. And then basically we can pretty much make execution proofs about that this is actually how the machine is supposed to run. And well, then we basically see how much can we actually fit inside, let's say, one RISC-0 segment, or let's say how many instructions do we need in order to kind of like fit it in. So then we prove we iterated from the initial machine state, eventually onto a final state, and then we basically take all that thing and try to run Linux inside it. And so I come from the embedded Linux world. So basically, taking an existing piece of code that goes into a strange environment, like, for example, RISC-0, it doesn't have libc, it doesn't have standard lib, it doesn't have an allocator as such. Well, it does in Rust, but for various good reasons. But for C++ code, it doesn't exist. And basically, what we went in and did was basically cross-compiling the C++ code into it. So the Cryptography machine is special because it's essentially a library with a front end in this particular case, and we can basically combine all the object files into one single object and basically bridge it into the Rust crate. So basically we took C++ code, shoehorned it into a Rust guest, and basically made it work. And we kind of like, this is from the newest version of this, basically being able to pretty much relay steps inside this guest replay with particular logs, how many cycles we want, and kind of like verify that indeed we started out in this root hash and we ended up in this root hash. And kind of like, this is how it is nowadays, that basically you can take a Cartesian machine on your normal computer and basically ask it to generate a complete step log of the execution, and then basically take that, combine it with something like RISC-0, CLI, so basically saying that, hey, okay, so this is the starting hash to win, because we always know what this machine containing, let's say, a Linux kernel with this hash or root file system with this hash, we always know how, let's say, the machine looks like. And basically, we can then go in and create a ZK proof of that and basically verify the receipt afterwards. So, as you might note here is that this is this step log. You can imagine with a Linux boot up, which is like 27 million big cycles, in this particular case, RV64 GC cycles, it can be quite big. But actually, what you can do is pretty much, let's say run in parallel these executions, saying, for example, A to B, and then underneath we go B to C, because we can kind of run those fast, and we don't need to prove them at the same time. And this is basically what we got working in 2023, that we actually started seeing the damn Linux kernel actually booting inside of RISC-0 proof, right? And this is a bit of a Frankenstein-like contraception, but it is actually possible. So the next thing about performance in this particular case is let's say this is napkin calculations. This particular case, don't rely on this for anything like business decisions or anything like this. But basically, to prove 1 million RISC-V GC cycles, we need 720 million RISC-0 cycles. So 720 times slowdown. Of course, it's kind of like expected when you're essentially running an emulator on top of a ZK VM, right? But nowadays, 1 million RISC-0 cycles is around 739 milliseconds on RTX 4090, according to the datasheet at least. I don't know if this is true or not, but I presume there's people here that can agree with that. And of course, what we can do is, of course, something is evaluating this execution of saying that we have these memory slots and so on, and the actual, let's say, Merkle proof verifications, and we can actually run these in parallel as well. So just because it runs kind of like a little bit slowly, in this particular case, like 4 hours to prove a Linux boot up, it is something we can actually put out in much more parallel across the GPU farm in this particular case. Of course, there's items about, let's say, privacy in this particular case and that kind of stuff, but when you're offloading into a cloud, but essentially it is something that you can actually get that down to, let's say, with 64 GPUs, potentially down to, let's say, 3 to 4 minutes for proving a Linux booting up, right? Of course, this doesn't talk about anything about the kind of like the workload inside the, let's say, the virtual machine. You might be, for example, running Java, and of course, it's kind of like cost things. But in 2023, when we did this originally, it took us 2-3 days. So basically, there's been massive speed up of ZK technology since then in actually being able to run this stuff. And this is actually even with us adding memory proofs that we didn't have back then. So of course, there's kind of like things you can kind of like start imagining can actually improve this. For example, you can imagine, let's say, particular kinds of operations. You can kind of like use just-in-time compilation, kind of like starting to optimize and so on. But like, if you're having a particular job that you're doing, for example, and you're booting up the Linux kernel, you don't need to prove booting up the Linux kernel multiple times, right? You just need to prove it up booting once. And then you take that state and then basically slice out a new root file system and put it in. And then you continue running. So once you have proven a Linux kernel booting, you never need to prove it again, unless you change the version, right? Of course, there is the slightly abusive things you could potentially do with this, because who among us has not wanted to run PHP in ZK? We can run Doom. I think this is kind of like pretty normalized by now. People can run Doom. It was not back then. MongoDB, Minecraft, Windows ME if you wanted to, because you could just slap another emulator on top of everything, right? I have run FreeDOS and this stuff. One of the kind of more useful thing could be, for example, let's say, and this is of course going to take a lot of proving power, but you could potentially run a Rust compiler in there. Why not? And what I mentioned before, start from already ZK proven Linux boot, or for example, let's say a particular function that is written for Linux, and you're just proving that one piece of processing because you already proven everything that happened before that. Proof of exploit. This is of course useful because you can pretty much execute anything inside of RISC-V Linux. And something that I like myself is I can have a public verifiable machine, but at some parts of the execution I want to have private. For example, a little bit like an Intel CPU is switching into SGX mode to actually work with that. And yeah, so if you want to see more about this work in progress, because we have kind of continued on this for our ZK fraud proofs, there's a branch called RISC0 on this URL where this is happening, and it's actually working quite nicely nowadays. If you want to contact me, well, this is information, and I want to say thank you to one of my developers, Yelzaveta Timchenko, because he ran in October 2022, way before these experiments, the first cycles of a RV64 GC inside RISC0 before continuations, which was a really nasty business in this particular case. And from the Cartesian Machine team, Marcos Pernambuco-Mota, who has basically, let's say, productized this thing out. So yeah, this is pretty much it. Any questions?
We have 5 minutes for questions.
Yeah, I have one question. Are you like out of guest transpiling like the 64-bit RISC-V into 32-bit IM, or are you like, do you have like an interpreter running in the guest?
I think the best, so the question was if we had like transpiling the 64-bit code into 32-bit code. This is something you would do if you want to do just-in-time translation, right? Or kind of like pre-generate some gadgets, those kind of things. We're not doing that. We're just basically running an interpreter that works completely deterministically in this particular case. So you can generate all the proofs and all those kind of things outside the environment. So it's not that fast, but 720x plus good technology, we can start getting there. And the most important thing here is to understand that we can actually, let's say, if you can write it up in a Python script, your prototype, technically speaking, you can show this actually works in ZK now, right?
So I saw that benchmarks slide, and I think it's a little bit outdated by like, 20, 30x. But I think the use cases are so cool. Are you guys working on any specific use case right now? Could we expect a demo of anything?
So this particular use case, we are going to use this branch here that you're seeing here. They're being used in part of ZK fraud proofs, optimistic ZK fraud proofs. So that's what they're going to be used for, because like it's much more expressive what you can do inside a ZK fraud proof settled into Ethereum compared to, let's say, interpreter that's the last step in an optimistic fraud proof that is just very, very restricted. You can basically start making even, let's say, outside information access or pre-image oracles, those kind of things happening in a ZK proof. So this is what it's particularly used for here.
More questions? No more questions? Thank you, Carsten.
Thank you.
And we are having one more talk. And please welcome again Alexander Kurbatov and talk about emulating OP-RAND in Bitcoin. I do not think we have mentioned Bitcoin today. So nice diversity. Welcome, Alexander.
All right. Yeah, my name is Alex. I'm lead of cryptography at Rarimo protocol, and between digital protests, I'm playing with Bitcoin from time to time. And yeah, so it's like topic isn't related to what actually Rarimo does, but that's like a funny thing, how you can emulate verifiable random functions in Bitcoin. So yeah, there are a lot of like methods how you can scramble randomness in different blockchains. First of all, you can use centralized oracles, but yeah, this is not very reliable. Next one is like proof of work. So that's how consensus in Bitcoin works. You cannot predict the hash value of the particular block, and you cannot predict what the following task you need to solve. And you can use a proof of work to generate some random numbers and reuse them in the future in your blockchain. The next one is like commitment and reveal scheme. So you can be committed for some secret and reveal that after like particular point of time. And if nobody can predict what exactly you generated initially, so nobody can predict what could be an output of the specific function. Then Chainlink uses verifiable runtime functions. Additionally, you can use verifiable delay functions, and a lot of proof-of-stake based platforms are reliant on that. Additionally, you can use, for example, threshold BLS signatures and yeah, some like other deterministic signatures also like to scramble the randomness with relying on some federation. But unfortunately, all these methods aren't available for Bitcoin. And what could we use to scramble randomness in Bitcoin transaction? An answer was nothing. Actually, yeah, fortunately I was wrong, and Robin Linus posted like a very large script how you can take several bits based on commitments of like Elisa and Bob, but the script was extremely large, so you would like pay a lot of money for sending this kind of transaction. 1 year ago, I told to touch Dria, and we also brainstormed how you can create a game that allows you to create a randomness within like using this commit and reveal scheme. And fortunately, that's like possible. Why we can do that directly in Bitcoin with the current Bitcoin script and with the current transactions? First of all, you cannot derive the randomness from like validator nodes or like from miners. That's not like possible. Additionally, Bitcoin script cannot inspect data out of like this specific like Bitcoin script. So it can operate only with like script states. So you cannot scramble, I don't know, for example, hash value of the block and reuse that in the transaction. You cannot, covenants right now aren't possible to implement. So you can operate only with limited states within like the specific state machine. Additionally, you cannot control determinism of ECDSA or Schnorr signatures in Bitcoin right now, so you need to generate additional random value and reuse that for the signature, so nobody can like constrain this process. And additionally, the biggest problem is every party, so every transaction counterparty can calculate all values and states between opcodes. So we finally don't have any opcode in Bitcoin script that allows you to generate something random. But you can create a play. You can create a game between like challenger and acceptor and build a kind of probabilistic payments. So what the operand operator is. There's not like additional Bitcoin opcode. There's not like some function that requires update of the Bitcoin protocol. That's interactive like game between challenger and acceptor, and it works very close to commit reveal scheme. So first of all, challenger needs to generate several scalar values, and so one of them will be used for forming like the final address. At the same time, acceptor doesn't know which scalar was used for that, and he tries to detect and he tries to guess this value. It doesn't require any update of Bitcoin protocol. It additionally allows you to realize some like probabilistic payment, and it requires only 3 transactions, and for external auditors, they will be the same as regular Bitcoin transactions. So you cannot detect that the specific transaction used operand. And yeah, there is like one additional component you need to use. You need to cover some processes with proofs. And we have implemented that with Nor. How it works? What's the main building block? Just imagine you have a situation where yeah, there are like 2 counterparties, Alice and Bob, and each of them has 1 Bitcoin, and Bob must be able to spend his 1 Bitcoin only in the case Alice spends her output. In this case, you can build like the first very primitive game between them. Alice can generate a random scalar value and create like a public point, just like by multiplying the scalar to group generator, and then form the final address. So this like address is a hash value, hash 160 opcode from this like public point. And then by multiplying this hash value to additional group generator, it can be the same. Alice can create a commitment. This commitment doesn't like reveal the public key Alice has, but it allows Bob to form the specific address by like summing his public key with this commitment. So when Alice generates this commitment, she needs to provide the proof that the following relation was executed. So she proves that hash function was executed correctly, and additionally that the result of this hash function multiplies this hash value to group generator leads to the commitment. And if the proof is correct, Bob can add commitment to his public key and convert that to regular Bitcoin address. After this transaction is created, it can be propagated to the network, and Alice, in this case, use pay-to-public key hash approach. How it works, if you want to like to spend pay-to-public key hash address, you need to reveal the public key and additionally provide the signature. And if Alice does that, it means she reveals initial public key she used. Having this like initial public key, Bob can reconstruct like the commitment. More precisely, having the commitment, Bob can subtract Alice public key from that and derive appropriate value. So Bob can derive like this hash of the public key and reuse that for correct signature construction. If we are trying like to implement that with operand protocol, how it usually works. Challenger, so Alice generates the set of scalar values, it's A1, A2, etc., etc. Then she creates a first round commitments for each value, so it's just like public points. And only one of this value will be used for forming like the final Alice addresses. So she needs to hash all these values additionally to receive second round commitments. And then again multiply them to group generator and receive public values that will be provided to the Bob, to Bob. And Bob needs to select one value which will be added to his public key. So Lisa just generated a lot of components, all of them public, but Bob cannot recognize which like public point was used for final Alice address. And after that, Bob needs to select one of these like H values, sum that with his own public key, and form the final address. Then, when Alice tries to spend their address, she needs to reveal appropriate public key value, as we describe it with pay-to-public key hash protocol. So when Alice spends her output, it means she needs to like she needs to publish her public key, and it can be subtracted with like from the final commitment. By the subtraction, Bob can detect which like Bob can detect like the public value that was used for forming like the final address. And having this value, he can hash that again to receive like the second round commitment, multiply that to group generator to receive like the third round commitment, and finally to check if appropriate scalar value was selected properly. Yeah, and we have implemented like kind of symbols game where Alice can generate two scalar values and derive appropriate public keys, and then Bob needs to guess which exactly public key was used for constructing this transaction. So Bob cannot predict this like scalars because they are generated by Alice, and at the same time Alice cannot know which public value was used for forming the final Bob address. And they can send the list of transactions on chain to like complete this protocol. So initially, Alice, for example, Alice has 5 Bitcoins, Bob has 5 Bitcoins. Alice generates the first transaction where she spends her current output and creates the address the next way. She creates the address by adding her public key to commitment she created previously. Then Bob needs to create a new transaction that spends the previous output plus additionally his 5 Bitcoins. And he can create output conditions which require our signature of like new Bob's public key, or Alice can spend that after log time. It means if Bob was successful with guessing appropriate public key, he can spend that. If he cannot, so Alice can spend that after, for example, 1 week. All right. What you can do with that with the future? Initial idea was you can constrain some program, so you can represent the state of a particular program by a scalar value and derive a commitment upon that and set each commitment to Bitcoin output. In this case, you can control program execution by appropriate Bitcoin transaction outputs. Then you can create probabilistic payments. Just imagine that somebody needs to send 1 Bitcoin to you, but at the same time, he has only output with 100 Bitcoins. In this case, you can create a probabilistic payment, and you will receive this 100 Bitcoins only with 1% of probability. It can be used for Lightning Network, for example, if you don't want to pay to all intermediates like between the sender and recipient, you can override outputs like to making this probability higher and higher. What are we doing right now? We're gonna like support pay to taproot addresses, so it will be very useful. And we need to do something like better than 1 of n probability, because right now Alice generates like the set of scalar values, for example in this case n scalar values, and Bob can guess only with 1 of n probability. Okay, you can find our NOR prover for that, an additional paper. That's it.
Do we have any questions? No questions.
Good, thank you.
Thank you so much. And we are having the last session of the day. Oh yeah, I can see you. I was looking for Silue if he has arrived. This is a session on zk-TLS. I think the sentiment on zk-TLS was changing. First it was like, wow, zk-TLS will change everything. Then the next it went down. It was like, it seems that zk-TLS doesn't work. And then people were like, okay, now unclear. So maybe today we will learn something about where we are today with zk-TLS and what awaits for us in the future, please welcome on the stage Silve from Highly, moderating this pair chat/panel, Matej from vLayer, and Ron from Opacity, who messaged that he's here. I will message him. You can sit down on these awesome chairs.
They look pretty cool. I'm gonna take the orange one. This one
I
looks
think
sick.
in general this space looks super cool. The team that was organizing it did a great job. It was completely empty room. They brought everything and organized it in the most cozy way possible. But I'm talking and not messaging.
Who has heard of zkTLS before? Quick check. Yeah. Great. For the record, it's like half of the space. 1/3. Yeah.
Oh yeah, true, because people can't see the room.
Okay, let's do this check. Who thinks that zkTLS is incredibly cool and changes the world completely?
Who thinks it's the best thing? It's better than curing cancer. Not a single hand was raised.
Who thinks that zkTLS is some shadowy technology that probably doesn't work and is just marketed?
Not as. For the record, Elias from Kakarot raised his hand and promptly lowered it. Elias has been thoroughly doxed right there. Are there any questions you'd like us to cover? I've got some questions already, like high level, how it works, etc., etc. Is there anything that you folks would like this panel to cover specifically? Any from Kakarot is raising his hand. Okay, yeah, we've got you. We've got two versions of that question. So the question was, what is zkTLS? Jacob from ReZero. Okay, so history lesson on the different names of zkTLS. We can do this. Okay, so full etymology of zkTLS and its many occurrences, and what are the trust assumptions? Let me write this down. I think there was another question over there by the gentleman in the orange t-shirt. Great color, by the way.
I will look for Ron. I don't know where is he.
Noting. So trust assumptions, etymology. Hey, Ron. Layers. And what was the first question? Different types.
Okay, we are good to go now. This is our last session for today. Please, again, a round of applause for Silve, Matej, and Ron to talk about zkTLS.
Alrighty, last session. We'll try and make it entertaining. So please, everyone, take a big breath because I see you. I've been sitting in these bean bags and I know the effect it has on your body. So please, just get the energy flowing a little bit and let's get going. So I will let you, lovely gentlemen, introduce yourselves because I asked you for your titles and I forgot it already. We'll go from left to right.
Hi, I'm Ron. I'm a protocol engineer at Opacity. I'm also chair for the Crypto Commons Association and a member of Bread Co-op.
And I'm Matej from vLayer Labs, running all the research at vLayer.
And I'm Silve, co-founder and CEO of Highly. All right, so we're gonna do the wired thing. Explain zkTLS to a 5-year-old. Ron, that one's for you.
So I'm working on a 1 minute and 30-second explanation of it. I'm willing to like set a timer and attempt that one.
Okay, let's do this one.
Okay.
Fuck it, we'll do it live.
So before the S in HTTPS, nobody would put credit cards online. You wouldn't, because somebody could sniff the McDonald's Wi-Fi and just get your credit card. So the corporations decided to solve this problem, and in a way that befits corporations, what they decided to do was add plausible deniability so that everything is encrypted, but in a way that really benefits them because they can deny whatever they send. So let's say if you Google Heimlich instruction maneuvers, and then Google sends you the wrong Heimlich instructions, and you end up killing somebody, you actually cannot sue Google for that, because you cannot even prove that Google sent you those instructions. The way this works is that when you request something from Google, it's like a room opens up between you and Google, and it has a lock on it, and you and Google have the same key. So Google can take that key, open the door, put in a message, lock it. You can come in, unlock it, read the message, and so on and so forth. However, because you both have the same key, when you try to show a message in the room to a third-party observer, they can't actually know whether the user unlocked the room, put in a fake message, and then locked it, or whether Google unlocked the room, put in a genuine message, and then locked it. The way we get around this with ZK-TLS is the first part, MPC-TLS, where we have the users split their key with a bunch of other nodes. That's 1 minute and 30 seconds.
That was pretty good. Was pretty good. Round of applause for Ron, who tried it.
But that actually wraps up the thing.
There's like 10 more seconds.
Okay, okay, go on.
So the nodes are looking over the shoulder of the user and are seeing what's being put in the room. The only party with the full key is Google. So any message that the nodes see in there, they know either they put it in there or Google put it in there. The user does not have the full key, so cannot do so. And then we add ZK on top of this key sharing thing to allow the user to obfuscate anything that they sent into the room, so they can preserve their privacy.
That's cool. That's cool and really quick. And all right. I mean, it all boils down to the symmetricity of TLS. I like to give a screenshot analogy when explaining ZK-TLS in 30 seconds or to 5-year-old. So if any of you in this room wanted to prove me to brag that Sam Altman follows him or Justin Bieber liked his Instagram post, you would show me a screenshot, right? And I won't trust any of you. I love you guys, but I won't trust your screenshot. And I like to think of ZK-TLS, which works just as Ron put this, as a kind of signed screenshot, as a kind of trustworthy, proven way of showing your web activity. Is it Instagram? Is it Twitter? Is it Revolut? Is it whatever? It's the internet. But there is a check mark on any of your web activity, thanks to the working around on TLS symmetricity.
It took me a lot of time to try and understand what exactly was hard in what you guys were doing, because it was like, isn't this what TLS is supposed to do? And then I realized, oh, okay. And I posted.
No, actually, the corporations don't want to change it. That's the problem, right? There is an RFC to change TLS to make it work this way, but none of them are incentivized economically to do it because they're sitting on this data.
I love the meme with what if TLS was asymmetric?
Yeah, it was a solar punk future, like remember what they took from you.
There's also this like communist meme where it's like when ZK-TLS sees data, our data.
Yeah, yeah, the Bugs Bunny meme. Let's take a step back and answer Jacob's question, who's now looking at his phone. Boo him. Let's take a step back and think about a bit like the history of like ZK-TLS and all a bit of its iteration. In my understanding, it started in the Bitcoin days. Is that correct?
Yep, it is. So I like to, when talking ZK-TLS or talking the protocol itself, I like the thing that I'm selling the blockchain idea, the blockchain technology, without causing any blockchain-related stress.
So like Coke Zero?
Yeah, like Coke Zero. Like there is no blockchain anxiety and there is pure blockchain-ish technology in there.
You mean like speculative shitcoins, basically? Yeah.
I mean high-end cryptography, and that's related to the blockchain days that Sylv mentioned, because the OG protocol, the OG zk-TLS protocol, is TLS notary, which is, as an idea, older than ETH, because the first post in Bitcoin forum dates back to 2013. The Dan, who is still on board in TLS Notary, posted about the idea of signing P2P transfers, so fiat to P2P, fiat to Bitcoin transfers. And back in 2013, that was just an idea. Then it evolved into a protocol called Page Signer. Is there anyone from TLS Notary in the? Okay, yeah, I thought so. So correct me if I'm wrong, but then it was Page Signer, then it was TLS Notary, compatible with the next generation of TLS protocol, and finally it was brought under the umbrella of privacy scaling explorations a few years back, which resulted in alpha releases. Right now we have like alpha 11, alpha 12, yeah, and that's the zk-TLS core. That's the MPC TLS path that brought us here. Like parallel to this evolution of TLS Notary, we had the Deco paper from later bought by Chainlink. We had Reclaim paper, the proxy architecture developed like in parallel. We had very recently the great academic effort from Primus Labs, ex-Pado Labs group, who developed the framework called Quicksilver, which is right now the go-to zk-TLS part in both TLS Notary and Primus. So that's why there is a lot of names, because there is both like the protocol path led by TLS Notary, and there is both a huge academic path from Deco through Primus to Reclaim through all these paths. So yeah, Ron, want to add to that?
I'm just saying, like, it seems like ETH Foundation created a whole avenue for a new set of business use cases, and I can't wait until the other chains will adopt it and then shit on ETH Foundation for not having a business sense.
As God intended.
Yeah, and that's a great thing. That's what I meant by Coke Zero reference. So this no blockchain anxiety thing is that the whole technology is blockchain agnostic. You can just sign your Instagram post with TLS Notary. This has nothing to do with Ethereum, with Solana, with, I don't know, Berachain. You don't need that. But if there wasn't Ethereum, if there wasn't the problem with Bitcoin trending in 2013, we wouldn't have that.
So let me put on my disgruntled Cloudflare 40-year-old engineer hat on, which is a terrifying person that you never want to meet at a crypto conference, who looks at you like, why should I trust this? How does it work?
Trust me, bro.
Trust me, bro. Yeah.
I squint harder. My wrinkles show.
Yeah, so maybe let's stick to the, because that was the question from the audience, that we have three modes of zk-TLS protocols. So one is MPC TLS mode, developed by TLS Notary or led by TLS Notary. The second one is proxy TLS, which essentially do not use any of multi-party computation. And the third one is so-called TE TLS, which is kind of proxy TLS, but with TE. And what we have here is all about security versus performance trade-off. So if I were to explain this to security researcher, I would stick to MPC TLS part. And that's what Ron said, that the only party in the zk-TLS connection over MPC TLS who has the full keys is the server. Then the client key in TLS is split between the client and the notary, so neither of them can play with the data requested and responded from the server.
So then, as an engineer, I look at you and I say, why should I trust the notary? What makes it especially...
So you're not trusting one notary, right? When you trust the TEE, you're basically like, I trust Intel, and I trust that there's a man with a gun looking over the machine.
As
when
an
you trust
engineer,
the
I
proxy,
smile.
you're trusting a bro somewhere in there. And like when you trust a decentralized network of nodes, you can go to the engineer and you can say, listen, this thing was ratified by like $500 million of security. I can tell you that it is possible that these $500 million were compromised. However, for this $80 transaction, that is not likely. If we're talking about settling like poly markets with MPC TLS, then we really need to make sure that the proportion of security is way bigger, is parental to what is being secured, right? As long as there is that ratio, then it is very unlikely that the data is compromised. And you're not trusting me, you're trusting this network of distributed nodes that are also slashable if they attempt to lie.
So it's not trust me, bro, it's follow the money, bro.
Yeah, trust but verify, yeah.
Attributable default?
You want me to drop like alpha on slashing, MPC TLS slashing?
So question from...
Catch me after the talk.
Question from Elias, attributable fault.
Yeah, it is attributable.
Seems that it is.
Yeah, but I think that we're just starting to see the ecosystem mature enough to build like slashing, like on EigenLayer, for example. Other restaking providers are not feature complete yet. We can talk about how this works like at a low level at the restaking provider level. We can talk about how it can work within a protocol sense. MPC TLS is unique in that if you have honest nodes spin up and a user try to like convince them that it is wrong, they will never be able to fool an honest node. And to give you an intuition on the basis of that, you can build like attributable behavior and crypto-economic like slashing mechanisms. But I'm not going to go super in depth on that here.
Slight tangent on a question that everyone asks all the time. Where's the ZK in ZKTLS? Because I really want it on the record somewhere that we answered that fucking question so that I can just reference this video whenever someone else asks me.
Okay, so I answered this question quite a few times. And the ZK in ZKTLS is known of the non-interactive ZK you all know and you all speak about since 10 a.m. It's not Snark, it's not Stark, it's completely different spice of ZK, and it's called interactive ZK. Normally, none of you care about interactive ZK because it involves interactiveness. It involves the communication between two parties, which tends to be slow. But in TLS, we have this interactiveness on the table as a default. We need to communicate with the server. We need to communicate with the notary so he can sign. So we can use the interactive ZK so the notary can prove that the encrypted transcript from the server, which he cannot see because he has only the part of the key, but he can prove that this particular transcript matches the real transcript that the client has got. And this must happen in ZK because none of the parties can see the notary cannot see the plain text like ever.
Yeah, so just to break that down maybe in more layman's term, like you can choose to have the nodes go over the shoulder of the user and see every little detail, but the user can also choose, and this is actually pre-ZK at the MPC level, the user can choose for the nodes to see essentially what you would see over the McDonald's Wi-Fi network. So the user can choose to basically stream to the notary this encrypted payload, this hidden payload, right? And then they can perform the ZK on top of that to not only selectively disclose what is in that encrypted data that is actually probably viewable by anybody who's sniffing networks, but prove specifically conditions on what is there in the ZK way that we all know and love.
Yeah, and we need that ZK in ZKTLS for that signature, basically. And this needs to happen in ZK because we don't want this notary or this node or this proxy or this network of proxies, whatever we call them. We don't want them to see our data. So that's the privacy requirement out there. So this needs to happen in ZK. And that's the Quicksilver that I mentioned.
Well, just actually, but like maybe somebody is like a huge, cryptography freak in here and knows that you can do like redactions with raw MPC TLS. We need the ZK part to do like the private conditionals, right? Like, do I have a bank account that has a balance that's above $1,000 without revealing how much I have, which is billions?
I hope you two big brains can help me build a conviction somewhere. It's useful specifically with like a more technical crowd to give a sense of the range of possibility of zk-TLS right now.
Risk score.
So can you give me from what is possible to what is absolutely impossible to what is difficult but will be possible in the future?
RIS score is pretty difficult to do, but theoretically you can have somebody ZK TLS prove all their like dating app chats, have an LLM inside of a ZK VM, prove that all these chats accredit you some sort of like RIS score that you cannot fake.
RIS ZK score.
Pretty cursed use case. I think we don't need
RIS 0.
Things that are like the easiest to do, I would say public data is very easy, very interesting. Private user data gets more difficult. On-chain is more difficult than just like Web 2 to Web 2. Web 2 to Web 3 is more difficult, especially on like the integration side of things. I think journalism is a great use case that is pretty low effort that I'm looking for adoption for journalists to be able to leak like sources credibly. Also, immutable government data caching. So you can have an immutable record of what the government reports on you at any given point in time. Yeah.
Yeah, I also love all the OG dance idea from Bitcoin Forum use cases, which is fiat to crypto transfers.
ZK-P2P, right?
ZK-P2P, yeah. Hey, who used ZK-P2P in the room? Yeah, that's my favorite way to buy crypto. And it uses ZK-TLS from the very beginning. So it's basically an implementation of the original idea of DAN. And I love how simple it is. So you simply prove your transaction from traditional bank or from Parabank. And you put it into the box, and then your crypto is arriving from the same box. So that's one for me. Every other use case involving the KYC, so the governmental use cases that Ron's mentioned, but also if you could reuse KYC you've done for the bank multiple times for multiple providers, for your gambling provider, for your another bank, for your another DEX, SEX, or whatever. Yeah, so if you want to reuse KYC, the ZK-TLS is there for you. Yeah.
I'd love to give some like 3 products that have like PMF already built with ZK-TLS. EarnOS lets you do like cross-brand promotions for users without the other brands consenting, basically. Lets the users sell their own data. Earnify lets users prove their like hours worked and then get a loan against the hours work on a daily basis instead of on a 30-day risk cycle. With
If I may double click on this, for example, we tried using ZK-TLS and we had a very basic.
Who's we?
At Highly Over, like we wanted to build a small app, and we wanted to do something which is the more hours you listen to Taylor Swift on Spotify, the more Taylor Swift coins you earn. And we realized that sessions or time-based ZK-TLS is actually trickier because indeed, you can get whatever the API is giving you, but if you do not have an API, correct me if I'm wrong, but if you do not have an API from Spotify that specifically tells you you have listened to Taylor Swift or artist Taylor Swift for that many minutes, you cannot infer it because you cannot do ZK-TLS over sessions. Is that correct?
You have to aggregate it.
You would have to aggregate.
You will.
Yeah. This actually, there is some interactivity composition that you can do to make this easier to do. So you can basically like have the nodes know that there's a bulk of requests incoming and to ratify them as one.
Yeah, so that kind of addresses your question about what can't you do, and there's a lot of issues with scalability, performance, and so on, so on. Over last couple of weeks, I heard a few times that zk-TLS has become a commodity, and you can just get the protocol from the shelf and use it. And it's not that simple.
It's really
Ron,
not that simple.
I guess you would agree with me while working on that. It's not a commodity yet.
I had to talk somebody down from doing like a n to the third implementation using zk-TLS, like an 01. I think it is very unintuitive how to use these things. I think we're still building out like the infrastructure to have everything be feature complete. It's a work in progress, but the incentive for it is there, is allowing the user to own their data, disrupting these markets, like with payday loaning, where they got a lot cheaper, letting like TikTokers get direct bounties from advertisers through daylight, all built on opacity, by the way.
Yeah, so yeah, that's a great point, and about the performance, you would love to notarize the high payloads, for example. And you don't want to wait for it for a couple of hours or to eventually break. So yeah, there's a lot to be built, but there are already use cases that we are ready for. So just to give you all an example, if you are bragging a bit down there, we were in Prague 2 weeks ago, and we've seen 50 hackathon projects built on V-layer zk-TLS implementation. So people want to prove things. Builders want their data on-chain. We've seen like a couple of, I don't know,
also seen some pretty crazy
GitHub.
ones that should not be using zk-TLS at all.
Yeah, 100%. 100%. But getting your Strava data on-chain seems appealing to a lot of builders. Like people want this, and now they have a way to do this. Getting your GitHub on-chain is now possible. So we are talking a lot about intellectual property, about proving that you own some IP. And for us here in this room or broader in the space, the code is most valuable IP we have, yeah, probably. And you can prove it. You can prove that you are owner of the GitHub repo and then get incentive.
Will somebody
for
make
that.
an easy tool to do like on-chain bounties with GitHub already in zk-TLS? I've been waiting for that for years, honestly.
Yeah.
I think there's a funny parallel to draw there. Let's go back to the early days of Facebook. Like, I don't know if you've done this experience recently, but it's absolutely horrifying. Go to your Facebook wall, if you're old enough, obviously, and scroll down to when you started it, and then you realize that I was just constantly posting stuff over there, like everything about my life, and now you look at how you use it, and you're like, why was I doing this? So to your point, Ron, like there's some stuff where you should not be doing it. So I would like a sentiment from both of you, an intuition on what are people doing now or want to do with zk-TLS that in 10 years is going to be a very big mistake. Proof of Riz?
Proof of Riz.
There's really cursed stuff that you can do, like creating a market where people sell gossip to each other over DMs. There's stuff that's like more morally neutral. That's like, should we make a, you can prove that somebody is sexually harassing you through DMs, through some like regex or LLM interpretation without revealing who you are.
So we have like a chaotic neutral.
It's on my Twitter, yeah. I didn't put all the evil ones in there. I've seen people using zk-TLS to just do straight up Web 2 to Web 2 things that don't make sense. Like your AI chat companion bot who is like zk-TLS powered to like the algorithm that recommends you content, and then it like comments on people's like really tragic posts in politically tense times.
Neutral.
Definitely, if it's Web 2, no financial trust needed, and the data is like public, I don't know why you would build that. Yeah.
Yeah, and actually proving things is cool as long as you have something to prove. So it's, proof of reserve is cool as long as you have reserve.
How are we doing on time over there? Lisa's sleeping, so I'm waking her up.
We have 8 more minutes.
8 more minutes.
That's a lot of time.
That's a lot of time. All right. Questions to the audience because I'm a lazy motherfucker. Hey, Elias, go for it again. He has a mic. Hey.
How is the UX looking on mobile?
Straight for the jugular.
Yeah, so we support mobile. We're actually mobile first. I think like I'm not a Web 2 developer. You need low levels of cryptography libraries. Hit me up. But otherwise, it's hard for me to comment on it. But I know our team believes that there's a lot of like business use cases in the mobile first.
But how can you listen to, like, imagine I use Instagram on my phone. How can I initiate a notary connection with that Instagram app opened?
Yeah, so you're not gonna be going to your raw Instagram app, but you're gonna be going through like a user journey of like the initial app, and then it's gonna pop you over. You're gonna do whatever Instagram things you need, and you're gonna come back.
Initial app being the ZKTLS app in this context.
Sorry, what?
Being ZKTLS app or
you said
the client's app?
You don't start from.
So let's say the ZKTLS consumer app, and the user is a user of that consumer app.
Yeah. So just to add maybe on top of that, because the mobile is very important, and the other way of running ZKTLS is through browser extension. So I believe that UX for mobile is way better, especially with, I don't know, app clips on iOS, where you don't have to install any kind of app. And another good thing in running the ZKTLS in mobile, speaking about TLS Notary, is that through mobile you run the native Rust implementation, which is faster than the WASM implementation for browser extension. So it makes a lot of sense to prove on mobile.
Sweet. I'll preface this. I do love the idea of ZKTLS and everything.
Oh boy.
I'm curious, you know, all three of you can answer, to be honest. Like, what is the biggest ZKTLS myth? You know, I think I go on crypto Twitter right now, and like everyone's acting like it's like a silver bullet. I guess sort of like a parallel answer is like, you know, personally, anytime I see someone trying to run an LLM inside of a ZK VM, I get sort of skeptical, right? We're not there yet.
Yeah.
So what is that for ZKTLS?
So the three modes of ZKTLS were brought here initially. So TE, proxy, and MPC. And I skip the TE mode. But for me, the myth is that when you are using proxy and generating your proofs in like 2 seconds or 3 seconds, you are not losing any security at all. So that's the narrative, that you can use proxy in as secure a way as MPC TLS. And that's a myth. I'll bring only one argument here, but through the MPC TLS, when you're running TLS Notary, this notary do not see not only any data you download from the server, but he doesn't see the server at all. So he do not know if you connect to the Google or Instagram or whatever you connect to. And in proxy, the proxy has to see. So there's a like privacy breach on the architecture level that's often overlooked. So I only discuss this in very deep tech conversations, that there is a fundamental privacy issue with proxy mode. And it's overlooked on Twitter like all the time. So that's my take. Ron?
Yeah, I think something that's kind of like buried is that there needs to be either like a strong motivation, let's say for the government use case, right, of like civic rights people that want to maintain this and continue to, you know, decode the data. Because you can imagine naively that I can run every single web request through MPC TLS, but then to interpret that and to be able to derive from that cryptographically, oh, this means that the government did recognize me as a citizen, and then like a couple months later they changed it arbitrarily, you would need to have either a profit incentive, right, to maintain decoding this data, or some other strong incentive that people will belabor to make it verifiable. So it's not like, you know, if you spin up RizCore and like 20 people use it and nobody's willing to pay for it, you're not going to be able to continually maintain it when they change the app and so on and so forth.
Another one. As builders on this space, where is the frontier, and what would help it kind of like accelerate? Like if we solve these top 2 or 3 problems, like what is that silver bullet for you as builders that would help accelerate?
An event, right? Yeah.
Can you expand?
What?
Like right now we're doing like M of N, and N of N would be much better. So if there was some like major cryptography breakthroughs where you could do MPC in a way that could be distributed to like 120 nodes that are doing the MPC with the user in real time in like great like latency, that would be the best. Right now we have to like aggregate it.
To give an intuition, what's the overhead? The more you...
It's very dramatic.
It's huge. It's huge. I think we got Tasio guys over here, or we don't, but they tried to evaluate how much overhead the second notary introduces, and it's huge.
Like the third. Like the third.
Like the third, yeah.
They do. I think they do have a paper out that it is possible to do it without timing out the TLS protocol, which is by default 30, but then like Google is like 18 for the handshake. So like that frontier would be great if there's any cryptographers who want to hop on that in the crowd.
Yeah, that's right. But also I think that the second thing is polishing user experience, because we talk a lot about developer experience, but we want the end users to use our app, our browser extension, and generate this proof without friction. So our focus is to polish the UX up to a way and polish the protocol down there. So the proof generation takes up to 15 seconds or 20 seconds. So as long as the attention span of the user, which is very short, can be held. Yeah.
Any more questions?
If I can piggyback on your question and get a little bit philosophical, and you correct me.
You have 1 minute to go.
I have 1 minute.
philosophical.
Okay, Rob God thing. I think it's also a question of, so there's this idea of like having data wallets that currently there is no way for an end user to actually custody their own data because we just don't hold data. I have a wallet, and there's very few amounts of pieces of data that I actually carry with me and that I have full custody of, except my like family pictures, and even these are on the family cloud. So would you think that having an affordance for users, something like ZooPass, because we're at Zoo Berlin, so obviously we need to reference that one, would be something that's interesting as an affordance for people to carry, like export their data, carry it around with them, and maybe do something with them?
We're building that soon. TM.
Oh boy.
Yeah, I think the idea of data unions from academic, combined with like the academic field, has been something that's been explored of like how can we unionize at the user level, and it's been theorized about many different ways where society might transition to something like this. I think that ZKTLS like enables that. I mean, I support anybody who's doing that. Right now, the corporations are just having at it and harvesting us like relentlessly. Some things that you would need to do it is like to be able to keep that data in an encrypted and distributed way, be able to retrieve it. There's some very, very hard, complicated problems there, but it'd be a net benefit to humanity. Maybe it would even reduce the amount of brain rot and like ads and like shady algorithms that were served.
So scrollers of the world, unite. You have nothing to lose but your algorithms.
Just to add on top of that, I've seen in Prague hacker building the verifier on the card terminal from the shop, and he was able to verify a web proof, verify ZKTLS web proof on the card terminal. So he could have a data wallet on his phone and then just tap it in the shop to prove that he's 18. It's
Thank
crazy
you so
cool.
much. Thank you so much.
Cheers,
to a
thank you,
very
everyone.
charismatic panel.
Thank you.
You are free to leave.
Thanks.
And we have done it. We have finished 7 hours of cryptography content. Thank you so much, everyone, for coming. Thank you, speakers. Of course, there is all interest in cryptography is impossible to put into one day. That's why we also have a bit of cryptography tomorrow, the day after tomorrow, the day after tomorrow, and also even on Saturday. To give you like, there will be like 1-2 sessions per day, but tomorrow we will have a panel on 25 ZK EVMs, too few or too many, and a session on lattice-based snarks. The day after tomorrow, we will have a session on quantum cryptography and session on FFTs and session on technical education and how to explain cryptography in TikTok. And the next day we will have a session on I/O. And the next day we also will have a session on I/O, as well as a session with Hudson Jameson on how to stay sane working in crypto. Everyone is welcome to come and join. And again, thank you so much for being here. I think it was a very, very cool day. I enjoyed it a lot. Thank you.